if our entire reality is a simulation? If so, could time simply be a programmed construct, a line of code within a vast, artificial universe? This concept forces us to question everything, even our most fundamental assumptions about the passage of moments. We often take time for granted, but it shares a surprising similarity with another constant in our lives: color. The colors we perceive are not inherent properties of objects themselves. Instead, they're creations of our brains as they interpret wavelengths of light. Could a similar process be happening with time? Perhaps our sense of temporal flow is a construct, a way for our minds to impose order and meaning on an otherwise timeless universe. Consider the vibrant world of color that surrounds us. A juicy red apple, a field of yellow sunflowers, clear blue of a summer sky. At first glance, these colors might seem like fixed properties of the objects themselves, yet the reality is far more complex. Colors don't exist independently in the world. They're born within our minds. Our eyes detect different wavelengths of light, and our brains translate those signals into the rich tapestry of hues that shape our visual experience. This process isn't merely about biology. People with different forms of color blindness perceive the world in distinct ways. Animals with different eye structures experience an even wider range of colors, some even seeing wavelengths invisible to us. What we call color is highly subjective, shaped by the unique capabilities of our sensory systems. Just as our perception of color is a creation of our minds, could the same be true of time? Perhaps the feeling of time ceaselessly flowing forward, the division of our lives into past, present, and future, is merely a way to make sense of change within the universe. Maybe, like color, time emerges from the interaction between our consciousness and a reality that may be fundamentally timeless. The idea that time may be an illusion isn't new. From ancient philosophers grappling with the nature of change to modern physicists unraveling the fabric of space-time, the question of time has persistently challenged our understanding. Today we're going to delve into this enigma, exploring the scientific discoveries and philosophical riddles that hint at the possibility that time, as we experience it, may be nothing more than a grand cosmic deception. Time feels inescapable. It permeates our lives, from alarm clocks jolting us awake to the relentless countdown to birthdays and deadlines. We measure our existence in seconds, minutes, and years, accepting this flow of time as an absolute, unyielding force. For centuries, this intuitive understanding of time was reinforced by the ideas of Sir Isaac Newton. He envisioned the universe as a vast stage with time serving as a universal clock, ticking away at the same steady rate for everyone and everything. But then came Albert Einstein, and our understanding of time was forever shattered. Einstein's theory of relativity revealed that time isn't a rigid constant, but a flexible participant in the cosmic dance. It bends, stretches, and warps depending on how fast you're moving and the strength of gravity's embrace. Imagine two identical clocks, one placed on Earth, the other aboard a spaceship hurtling near the speed of light. Bizarrely, if you could compare them, the clock on the spaceship would be ticking slower than the one on Earth. This mind-bending concept is time dilation. The faster you travel through space, the slower you travel through time. This isn't some abstract theory. It has real consequences. Imagine twins separated at birth. One stays on Earth, the other becomes an astronaut who spends years traveling at immense speeds. Upon their reunion, the spacefaring twin would have aged less than their Earth-bound sibling. Time would have literally passed slower for them due to the effects of time dilation. Time dilation may seem like science fiction, but it's a fact of our universe that engineers have to account for. GPS satellites, orbiting high above Earth and traveling at significant speeds, experience time slightly slower than we do on the ground. Their onboard clocks have to be adjusted to stay in sync, ensuring the maps on your phone remain accurate. Einstein's revolutionary theories upended our understanding of time. Suddenly, time wasn't a steady constant, but a dynamic player in the cosmic drama. This scientific upheaval sparked a resurgence in philosophical debates about the very nature of time. If time dilation and warped space-time are real, how do we reconcile these concepts with our everyday experience of time's constant flow? Let's explore some of the profound questions that emerge at the intersection of physics and philosophy. One central debate centers on the existence of the past and future. Presentists argue that only the present moment has any real existence. The past is a collection of memories, the future a realm of possibilities. Eternalists take the opposite stance, viewing all of the time, past, present, and future, as equally real and unchanging, like a vast unfurling tapestry. The growing block universe model attempts to bridge these two views. It posits a fixed past, an open future constantly branching into possibilities, and a continuously expanding present moment as our experience unfolds. These seemingly abstract philosophical debates have profound implications. If only the present exists, how can we learn from the past or plan for the future? If the future is already set, does that negate free will? The way we conceptualize time shapes how we understand our place in the universe and the choices we make within it. Perhaps the most unsettling implication of the block universe is the challenge it poses to free will. If the future already exists, laid out like a vast network of paths, are our choices truly our own? Or are we merely tracing a predetermined route? Our sense of agency nothing more than an illusion? This paradox forces us to grapple with the question of what it means to have control over our destiny within a universe where all moments may already be written. Can the block universe coexist with genuine free will? Some philosophers argue that even if our actions are fixed within a timeless expanse, we still experience the act of choosing and the consequences of those choices. Others suggest that true freedom might lie in accepting the predetermined nature of existence and finding meaning within that framework. Why does time seem to relentlessly march forward, never backward? Physicists and philosophers grapple with different arrows of time, each offering clues to the irreversible nature of events. The thermodynamic arrow is one of the most well-known. It stems from the second law of thermodynamics, which states that entropy, a measure of disorder, always increases in a closed system. This explains why eggs break but never unbreak, and why ice melts but doesn't spontaneously refreeze. These irreversible processes give us our sense of time moving in one direction. But thermodynamics isn't the whole story. Our minds create a powerful psychological arrow of time. We vividly remember the past, yet the future remains a mystery. Even the universe itself provides a cosmological arrow, as it continues to expand outward since the Big Bang. These diverse arrows raise a perplexing question. Is the flow of time a fundamental property of the universe, or a byproduct of how we experience the relentless unfolding of change? The bizarre realm of quantum mechanics throws a wrench into our traditional understanding of time and space. Consider the phenomena of entanglement, where two particles become linked in a profound way. Imagine a pair of gloves, one for your left hand, the other for your right. If those gloves are separated and placed in boxes on opposite sides of the planet, they remain intrinsically connected. If you open one box and find a right-handed glove, you instantaneously know, faster than any signal could travel, that the other box contains the left-handed glove. In the quantum realm, particles can become similarly entangled, their properties inextricably linked. Measuring one instantly affects the other, even across vast distances, seemingly faster than the speed of light allows. This paradox hints at a universe where connections might exist outside our usual understanding of linear time. Theories like loop quantum gravity go even further, suggesting space-time itself isn't a smooth continuum, but made up of tiny, indivisible chunks like the threads of a cosmic tapestry. If true, time might not be a fundamental force, but rather an emergent property of this deeper structure, a byproduct of the way these fundamental building blocks interact. These mind-bending theories force us to question the very nature of reality. Could it be that our experience of time's relentless flow is an illusion, born from our limited perspective within a universe that may operate on principles beyond our current comprehension? Perhaps the past, present, and future we perceive are merely convenient ways for our minds to organize the chaotic dance of existence. The true nature of time remains one of the universe's greatest enigmas. Is it a fundamental force woven into the fabric of existence, guiding the destinies of planets and particles alike? Or is it a grand illusion? A convenient fiction created by our own limited perspective? Scientific discoveries and philosophical paradoxes hint at the possibility that our experience of time's flow may be profoundly different from the true reality of the cosmos. If time doesn't exist as we perceive it, what does that mean for free will and our place within the grand story of the universe? Are the past, present, and future simply emergent constructs in a reality governed by laws beyond our current grasp? We may never possess the definitive answers to these questions, but the very act of pondering them reveals the profound beauty and endless mystery of existence. While the relentless march of the clock and the turning of the calendar may shape our daily lives, perhaps true freedom lies in embracing the timeless wonder of a universe that continually defies our understanding. Imagine a canvas of moments woven with the threads of time, matter that stretches endlessly in all directions, capturing every choice, every event, every heartbeat. What if you could navigate this intricate fabric? What if you could go back in time, look into the future, or even change the course of history? Time, it governs our lives, but it remains one of the most mysterious phenomena in the universe. We measure it, we chase it, but can we control it? The concept of time travel has intrigued humanity for generations, inspiring countless works of fiction and sparking rigorous debate. But what can science say? Can time travel ever move from the pages of science fiction to the annals of scientific fact? Einstein's theory of relativity opened the door to this possibility by suggesting that time is not a constant, but a variable that can be manipulated. In addition, there are black holes, cosmic phenomena so powerful that they can distort not only light, but time itself. Did you know that astronauts aboard the International Space Station age slower than humans on Earth, even if only by a fraction of a second? This is not science fiction. It is a proven consequence of traveling at high speeds. So let us journey through the corridors of time. We'll explore the science, paradoxes, and limitless possibilities that may one day make time travel a reality. Welcome to a journey through time. Long before the advent of science as we know it, humankind was fascinated by the heavens and the passage of time. Ancient civilizations paid attention to the stars, sun, and moon, creating elaborate calendars and methods of measuring time. Transported to the modern era, this fascination has found a new canvas: film and literature. The concept of time travel has been a recurring theme, offering both escapism and a platform for intellectual curiosity. In 1895, H.G. Wells wrote the novel The Time Machine, which, by the way, not only popularized the term time machine, but also introduced the idea that time could be navigated like the dimensions of space. Then came Back to the Future, a pop culture powerhouse that took the concept of time travel and made it accessible to a whole new generation. Who could forget the DeLorean, the magnetic condenser, the flux capacitor, and Doc Brown's charming eccentricity? But it's not just a Western phenomena. The allure of time travel knows no cultural or linguistic boundaries. From the Japanese Steins Gate to the Soviet Ivan Vasilievich changes profession, the theme of time travel resonates around the world. So what is it that attracts storytellers to this concept? The allure of rewriting history? The excitement of the unknown? Or perhaps the philosophical questions such journeys raise? It's a desire fueled by a mixture of nostalgia and anticipation, a longing to revisit cherished memories, or leap into the promises of tomorrow. And as we stand on the cusp of scientific discoveries that could turn dreams into reality, the question becomes more important than ever. Could we? Should we? And what if we did travel through time? The blackboard is the canvas on which the abstract becomes possible. Here, equations like E equals mc squared are not just symbols. They're keys to understanding the universe. But can they unlock the secrets of time travel? From silver screens to living room TVs, time travel has been portrayed in countless ways. But let's peel back the layers of fiction and delve into the science that can make time travel more than just a plot device. Meet space-time, the four-dimensional fabric of our universe. According to Einstein's theory of relativity, this fabric can be bent and deformed by mass and energy. But can it be torn or twisted to create a path through time? Time dilation, a consequence of Einstein's theory, suggests that time can flow at different rates depending on the speed of motion or the gravitational field. For example, astronauts on the International Space Station age slightly slower than people on Earth. Experiments with particle gas pedals and atomic clocks have provided empirical evidence of time dilation. It's been observed that particles traveling near the speed of light decay more slowly than their stationary counterparts. In addition, there are wormholes, hypothetical tunnels in space-time that could theoretically allow time and space to be shortened. Although somewhat speculative, the math suggests that they are possible. Leading physicists and cosmologists have voiced their opinions on the matter, offering theories that range from plausible to downright bizarre. Some even suggest that quantum mechanics, the science of the very small, may play a role in making time travel possible. And let's not forget black holes, the mysterious titans of space. Their enormous gravity is so strong that it distorts not only space but time itself. Could these cosmic phenomena be a gateway to other times? The scientific community is far from consensus. Time travel raises questions that challenge the very foundations of physics, from the nature of reality to the concept of causality. They say time goes forward, always forward, and never backward. But what if we could leap forward, skipping years, decades, or even centuries? The idea might not be as far-fetched as it seems. When it comes to slowing down time, speed becomes the main parameter. According to Einstein's theory of relativity, the faster you move in space, the slower you move in time. So, could extreme speed be our ticket to the future? Believe it or not, time travel to the future has already been done, albeit on a minuscule scale. Astronauts aboard the International Space Station experience time dilation and age a little slower than their counterparts on Earth. Let's turn our attention to the twin paradox, the famous thought experiment that takes time dilation to a new level. Imagine twins separated at birth. One travels through space at near light speed, while the other remains on Earth. Upon reunion, the space twin will appear younger. Achieving speeds close to the speed of light would greatly enhance this effect. However, such speeds are currently beyond the reach of our technology. Not to mention the energy requirements would be astronomical. Scientists and engineers are wrestling with these problems, researching propulsion technologies that could, one day, make near light-speed travel possible. But even then, can the human body withstand such a journey? Imagine a future where time dilation capsules are as common as airplanes, allowing people to jump into the future to glimpse advanced civilizations or even avoid catastrophes. Will knowledge of the future be a gift or a curse? And what will it mean for the concept of free will? From science fiction to science articles, wormholes have captured our collective imagination. These hypothetical tunnels in the fabric of space-time may turn out to be the cosmic shortcuts we've been dreaming of. But what are wormholes, and could they be the key to time travel? Imagine folding a piece of paper so that 2 points touch, and then poking it with a pencil. In space-time, the wormhole would be that pencil, creating a straight path between 2 distant points. This concept gained traction in the scientific community thanks in part to Carl Sagan. While writing his novel Contact, he consulted with physicist Kip Thorne to explore the scientific possibility of using a wormhole for interstellar travel. Today, physicists are delving deeper into the math of wormholes. While the general theory of relativity allows for their existence, the equations also assume that they collapse too quickly for anything to pass through them. Theoretically, by introducing some exotic matter, for example, it could counteract the gravitational forces causing the wormhole to collapse, keeping it open long enough for something or someone to pass through. The portrayal of wormholes in popular media often glosses over these complexities. They're usually portrayed as stable, luminous vortices. But the reality, if they exist, can be much more volatile and unpredictable. Despite the lack of empirical data, the study of wormholes is a dynamic area of research. Scientists use computer modeling and indirect observations to understand their properties and potential uses. Imagine the possibilities if wormholes could be used for time travel. One end could be anchored in the present, the other in the future, or the past. The implications for research and even for preventing global catastrophes are staggering. Wormholes open the door to questions not only about where we might go, but when. And as we approach the potential discovery of these cosmic shortcuts, we must ask ourselves, are we ready for the responsibility associated with such power? In the world of the very small, where particles are also waves, and reality itself seems blurred, lies the quantum world. Could this region of uncertainty hold the keys to unlocking time travel? Quantum mechanics challenges our everyday understanding of the world. Take the two-slit experiment, in which particles behave as both particles and waves. This duality suggests that, at the quantum level, the fabric of reality is much more malleable than we thought. Great minds like Richard Feynman and Niels Bohr have delved into the mysterious world of quantum mechanics, a theory that's been incredibly successful in explaining the behavior of matter and energy at extremely small scales. Some physicists suggest that quantum mechanics may offer a basis for time travel. Quantum tunneling, for example, allows particles to pass through barriers as if they're ghosting through walls in the two-slit example. Can a similar principle enable time tunneling? Quantum computing is a new field that uses the principles of quantum mechanics to perform calculations at speeds unimaginable to classical computers. Some speculate that quantum algorithms could solve equations related to time travel that are currently too complex for today's computing machines. The concept of quantum entanglement adds interest. Imagine two particles cooked together in a certain way. Once entangled, these particles become interconnected, forming a single quantum system. The truly stunning aspect of entanglement is that the state of one particle instantly affects its entangled partner, regardless of the distance separating them. This could be across the room, or even across the galaxy. Change the spin of one, and the other instantly changes. Albert Einstein famously called it spooky action at a distance. At first he didn't like this idea because it seemed to violate the limit of the speed of light set by his theory of relativity. Since then, however, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Could such an effect at a distance make a difference to instantaneous time travel? While the intersection of quantum mechanics and time travel is still in the realm of speculation, it is a hotbed of scientific research. Researchers are studying everything from quantum loops in time to the role of quantum gravity in the early universe. Imagine a future in which the principles of quantum superposition could account for multiple timelines or realities. What if you could exist in a superposition of past and present? Could quantum mechanics be the final piece of the puzzle in our quest to conquer time? Moving on, let's move from the world of the microscopic scale to the grandiosely large one, black holes. Mysterious titans of space whose gravity is so strong that not even light can leave them. But could these celestial phenomena hold the secret to time travel? Enter the concept of closed time-like curves. A closed time-like curve, or CTC, is a path in space-time that loops back on itself. Theoretically, an object or even a person traveling along a CTC could end up in an earlier point in time. The idea was first proposed by physicist Kurt Gödel in 1949. Gödel's solution to Einstein's field equations suggested that rotating universes could contain paths looped in time. However, these solutions required certain conditions, such as a universe filled with rotating matter. Although Gödel's model is considered physically implausible in most cases, it has opened the door for other scientists to explore the concept. The main challenge is to find a scenario in which STSSs could exist without violating the laws of physics. One such scenario involves rotating black holes, known as Kerr black holes. Massive gravitational and rotational forces can theoretically twist space-time into loops, creating CTCs. But there's a catch. Most models predict that the center of a rotating black hole, known as a singularity, will be ring-shaped rather than point-shaped. This ring feature could potentially serve as a gateway to the CTC. However, powerful gravitational forces could also create a barrier, known as the Cauchy horizon, beyond which the laws of physics are violated. The study of CTCs and black holes is fraught with paradoxes and uncertainties. For example, if CTCs exist, they can lead to paradoxes in which cause and effect are reversed. This has prompted some physicists to propose the chronology defense hypothesis, which suggests that the laws of physics prevent such paradoxes. Imagine the possibilities and dangers of approaching a rotating black hole. Would we ever be able to navigate safely through such a treacherous region of space-time? And if we could, what would we find on the other side? Another universe? Another time? In addition to black holes and closed time-like curves, there's another cosmic mystery that could potentially open a path through time: cosmic strings. These hypothetical one-dimensional cracks in the universe may be remnants of the Big Bang itself. Cosmic strings are thought to have formed in the early moments of the universe as they cooled down after the hot and dense state of the Big Bang. These strings would have been thinner than an atom, but incredibly dense, and would have had a tremendous gravitational pull. Although still theoretical, cosmic strings offer intriguing possibilities for time travel. Physicists J. Richard Gott and William Hiscock have made significant contributions to our understanding of these mysterious objects. Gott suggested that a cosmic string traveling at the speed of light could theoretically distort space-time enough to create a loop allowing time travel into the past or future. However, the existence of cosmic strings is still a matter of debate. Their detection would require astronomical observations on scales that are currently beyond our capabilities. Moreover, if they do exist, harnessing their power for time travel would be a challenge. Now, let us return to quantum entanglement. We've already explored how entangled particles are connected in ways that transcend ordinary spatial distances. Can they be bound in time? Some theories suggest that entangled particles can be used to transmit information not only in space, but also in time. Imagine a future in which quantum entanglement is used to create a kind of quantum internet that allows instant communication across eras. The intersection of cosmic strings and quantum entanglement is a frontier of theoretical physics rife with unanswered questions and untapped potential. Researchers are exploring how the two phenomena might be connected and what this might mean for our understanding of time travel. Imagine a scenario in which cosmic strings are manipulated at the quantum level through entanglement. This would represent a merger of the very large and the very small, a meeting point of cosmic and quantum scales that could revolutionize our concept of time travel. As we venture into the realm of time travel, we face many paradoxes and riddles. These are not just intellectual exercises. They are fundamental questions that can make or break the possibility of time travel. First of all, this is the grandparent paradox. Imagine going back in time and not allowing your grandparents to meet. If they never meet, one of your parents will never be born, and therefore neither will you. But if you are never born, how would you even be able to travel through time? The grandfather paradox raises questions about causality and the nature of time itself. Some theorists suggest that such paradoxes can be resolved through the existence of parallel universes, where each solution generates a new timeline. Another confounding bootstrap paradox is named after the popular expression, pulling yourself up by your bootstraps. Imagine going back in time to give Shakespeare a copy of your works, which he then claims as his own. Where, in that case, did these works originate? The bootstrap paradox creates a closed loop of cause and effect with no apparent origin. It challenges our linear understanding of time and suggests that cause and effect may not be as simple as we think. Another paradox, the paradox of predestination, is when a time traveler's actions in the past lead to the very event he was trying to prevent. This raises questions about free will and determinism, and whether we can ever really change the course of history. The study of time travel paradoxes is not just a playground for philosophers. It's a serious area of research in physics and metaphysics. The resolution of these paradoxes may shed light on time travel. While we stand on the threshold of scientific discovery, the future of time travel remains a mystery shrouded in paradoxes, theories, and cosmic phenomena. What was once the realm of science fiction is gradually approaching the realm of real science. From cosmic strings to quantum entanglement, from spinning black holes to closed time-like curves, we explored the theories and possibilities that could one day make time travel a reality. Current research is paving the way for new experiments, new technologies, and perhaps even a new understanding of the structure of reality. But as we teeter on the edge of cosmic horizons, one question becomes more important than all others. Are we ready for what we might find? Time waits for no one, but what if we could wait for time? For years now, there's been a concept that defies the very laws of physics as we know them, a dream that has spawned countless stories and science fiction fantasies. This mystery is the search for a warp drive, a technology that could potentially allow us to travel vast distances in space, faster than light itself. Imagine a journey where time and space constraints yield to the power of human ingenuity, where the farthest corners of the universe suddenly become accessible. This isn't just science fiction. It's a puzzle that scientists have been piecing together for decades, ever since physicist Miguel Alcubierre proposed a theoretical model in 1994. Alcubierre's model, a bold combination of imagination and Einstein's theories, offers a way to bend the fabric of space-time itself. But what lies behind this bold idea? Is it a mere flight of fancy? Or could it be the key to unlocking interstellar travel? Today we explore the tangled web of problems and breakthroughs surrounding warp drive. From the mysterious nature of negative energy to the tangled horizon problem. So let's dive into the depths of one of the most intriguing scientific quests of our time. The quest for the warp engine, science or fiction? In the heart of Mexico City, Amidst the hustle and bustle of city life, a young mind was fascinated by the mysteries of the cosmos. We're talking about Miguel Alcubierre. Born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and led him to the prestigious University of Wales, where he delved deeply into the fields of general relativity and cosmology. In 1994, while working at the Max Planck Institute for Gravitational Physics in Germany, Alcubierre made a breakthrough in world perception that challenged our understanding of space travel. Inspired by the iconic science fiction series Star Trek, he posed a bold question. Could the laws of physics allow for a real warp drive? Let's break down the Alcubierre drive. Imagine a spaceship that does not move through space in the usual sense, but sits in a space-time bubble. This bubble, or deformation bubble, is the key to the Alcubierre concept. According to Einstein's general theory of relativity, massive objects distort the fabric of space-time. Alcubierre hypothesized that if we could manipulate space-time in a controlled way, we could create a warp bubble. The space in front of the bubble is compressed, pushing the bubble forward. Behind it, space expands, pushing it from behind. Inside this bubble, the spaceship remains stationary, but the bubble itself moves, allowing the ship to move faster than light without violating the laws of physics. This idea doesn't involve moving the spaceship at high speed. Rather, it's about moving space around it. It's like putting a surfboard, a spaceship, on a wave, warp bubble, and letting the ocean, space-time, carry it. However, the Alcubierre model is not simply a manipulation of space. It requires exotic matter with a negative energy density to stabilize the warp bubble. This exotic matter is one of the many theoretical obstacles scientists face as they try to turn the Alcubierre drive from a fascinating theory into reality. Delving deeper into the practical aspects of the Alcubierre drive, we're faced with huge challenges that stand between theory and reality. The first of these is the scale of energy and mass requirements. It was originally thought that creating a warp bubble would require an amount of energy equivalent to the mass of the observable universe, an unimaginably huge amount, far beyond our current technological capabilities. However, the field of theoretical physics is constantly evolving. An outstanding achievement was when physicist Chris Vanderbroek proposed modifications to the shape of the warp bubble. These adjustments dramatically reduced the energy requirement to about the mass of 3 suns. Still a colossal amount, but a significant step down from the original estimates. The second major obstacle is the need for exotic matter and negative energy. In the Alcubierre model, this exotic matter is crucial to stabilizing the warp bubble and making it function as intended. Negative energy is a peculiar and controversial concept. It's a concept in physics that can distort the very fabric of space-time. It's not just the absence of energy, but an actual physical quantity with negative characteristics. In the context of Alcubierre drive, negative energy will counteract the effects of normal positive energy, creating the conditions necessary for the existence and stability of the warp bubble. Negative energy, in the context of Alcubierre drive, is indeed a complex and somewhat elusive concept in physics, and it's important to distinguish it from the more familiar concepts of gravitational potential energy. In classical physics, the concept of negative energy often refers to gravitational potential energy. For example, the gravitational potential energy of an object in a gravitational field, like a planet, is considered negative energy because it takes work to move the object from the source of gravity to a point where this energy would be zero, for example to infinity. This form of negative energy is the cornerstone of our understanding of gravitational interactions in the universe. However, the negative energy required for the Alcubierre drive is different. In this context, negative energy refers to a hypothetical form of energy whose energy density is less than zero. It's not just an accounting tool or a way of describing potential energy in a gravitational field, but rather a real physical substance or field with exotic properties, such as repulsive gravitational effects. This type of negative energy is not something we observe or well understand in the context of known physics. However, the existence of negative energy and, by extension, exotic matter remains a topic of intense debate and speculation in physics. Although phenomena such as the Casimir effect suggest the possibility of the existence of negative energy under certain conditions, harnessing it on the scale required for warp drive is a challenge. These challenges, the enormous energy requirements, and the need for exotic matter, underscore the monumental task of transforming Alcubierre drive from a theoretical model to a practical reality. They represent not just technological obstacles, but fundamental questions about the nature of the universe and our ability to manipulate its basic forces. As we move forward into the world of warp drive technology, we face another obstacle known as the horizon issue. This issue is at the heart of the Alcubierre drive design and poses serious problems for its practical application. In astrophysics, the horizon is often referred to as the boundary beyond which events cannot affect an outside observer. The most famous example is the event horizon of a black hole, the point of no return. Beyond this horizon, the gravitational attraction is so strong that nothing, not even light, can leave it. Similarly, in Alcubierre drive, the horizon is the boundary of a warp bubble. Inside this bubble, the spaceship is cut off from the rest of the universe, just as the interior of a black hole is isolated from the outside world by its event horizon. The horizon problem arises from the unique structure of the warp bubble itself. In the Alcubierre model, the spacecraft is located in a region of the space-time plane surrounded by a warp bubble that compresses space at the front and expands it at the back. This manipulation of space-time allows travel at speeds faster than the speed of light, but with a critical limitation. It isolates the spacecraft from the rest of the universe. Imagine being inside this warp bubble, the very mechanism that allows you to travel vast distances in space also prevents you from controlling the ship or interacting with the outside world. Communication signals, navigation commands, and even visual observations are all prevented by the bubble's boundary. Passengers and crew will not be able to control the spacecraft, correct its course, or even stop the journey once it's begun. The implications of the horizon problem are profound. It implies that a spacecraft driven by warp would essentially be traveling on a one-way, uncontrolled journey. This raises practical questions about using such technology for exploration or travel. How do we get to specific destinations? How do we avoid collisions with celestial objects, or adjust our flight path to meet unforeseen circumstances? Moreover, this problem implies the need for a pre-established infrastructure, similar to an interstellar highway, with mechanisms to create and control the warp bubble from the outside. Such a requirement adds another layer of complexity to the already difficult task of realizing warp drive technology. While the horizon problem represents a significant engineering challenge, it is important to recognize that it doesn't invalidate the fundamental scientific validity of the concept. Theoretically, the principles underlying the warp drive remain unchanged and plausible within the framework of the general theory of relativity. As we delve deeper into the complexities of Alcubierre drive, we encounter another major problem. The radiation problem. This problem is twofold. It involves both the accumulation of radiation at the front of the deformation bubble and the potential effects of Hawking radiation within the bubble itself. First, let us consider the radiation accumulating at the front of the warp bubble. As the bubble moves through space at a speed faster than the speed of light, it inevitably encounters interstellar particles and cosmic radiation. These particles and radiation, unable to bypass the warp bubble, accumulate near its front end. Such accumulation poses a significant risk. When the warp bubble slows or stops, the collected radiation and particles will be released in a burst of energy. The intensity of this release could be catastrophic, not only endangering the spacecraft and its passengers, but potentially damaging any nearby objects at the destination. Moving inside the warp bubble, we encounter the second aspect of the radiation problem: Hawking radiation. This theoretical radiation, predicted by Stephen Hawking, arises from the effects of quantum mechanics near the edges of black holes. In the context of Alcubierre drive, the intense warping of space-time around the edge of the bubble could create conditions similar to those at the event horizon of a black hole, potentially generating Hawking radiation. This radiation could have harmful effects on passengers inside the bubble, exposing them to high levels of energy and particles. The implications of these radiation problems are profound. Not only do they pose serious engineering and safety challenges, but they also raise questions about the feasibility of long-duration travel using Alcubierre drive. Ensuring passenger safety and spacecraft integrity in the face of these radiation hazards is a critical area requiring further research and innovative solutions. It is a challenge that requires ingenuity and a deeper understanding of the interplay between quantum mechanics, the theory of relativity, and the harsh reality of space travel. When we turn our eyes to the current state of research in warp drive technology, we find ourselves in the thick of scientific research. Recent years have seen a flurry of theoretical papers and articles that break new ground in this field. One notable development has come from the work of physicists who've been revisiting the energy requirements of the Alcubierre drive. Based on earlier advances that significantly reduce the estimated energy requirements, recent papers have proposed various methods to further optimize the geometry of the warp bubble. These improvements are aimed at making the energy requirements even more feasible, approaching the realm of possibility. Significant contributions to the field have been made by researchers such as Harold White, who was instrumental in the experimental work on the feasibility of deformation bubbles and space-time manipulation at the NASA Eagle Works laboratories. Another area of active research is exploring alternative theories that could circumvent some of the limitations of the Alcubierre drive. For example, some physicists are exploring the possibility of using solitons, solitary waves that retain their shape while traveling at a constant speed, as a basis for creating stable strain bubbles without the need for negative energy. There's also growing interest in the role of quantum mechanics in warp drive physics. Researchers are delving into the quantum aspects of space-time and how they might affect warp drive mechanics. This includes studying the effects of quantum entanglement and the potential use of quantum fields to stabilize the warp bubble. Recent theoretical advances also include the study of the effects of warp drive technology on causality and the fabric of space-time. These studies are critical in addressing potential paradoxes and time travel scenarios, ensuring that the concept remains grounded in physical laws as we know them. Little by little, the dream of warp drive technology is moving ever closer, from the pages of science fiction into the realm of scientific possibilities, driven by the tireless efforts of researchers around the world. As we ponder the future of warp drive technology, we find ourselves at a crossroad of assumptions and possibilities. The realization of warp drives, a concept once confined to the realm of science fiction, depends on several key developments and breakthroughs. First of all, the theoretical problems associated with warp drive technology need to be addressed. This includes finding viable solutions to the enormous energy requirements, the creation and stabilization of warp bubbles, and the safe management of radiation risks. Advances in areas such as quantum mechanics, exotic matter, and energy manipulation are critical to turning these theoretical possibilities into practical reality. Beyond the scientific and technical obstacles, the advent of warp drive technology brings with it many ethical and practical considerations. The ability to travel vast distances in space at unprecedented speeds would revolutionize space exploration, opening new horizons for humanity. However, with great power comes great responsibility. The ethical implications of such technology must be carefully considered. This includes the potential impact on space ecosystems, the responsibility to explore and possibly interact with extraterrestrial life, and equal access to this technology among nations and peoples. In practice, warp drive technology would lead to new methods of resource utilization, new ways of conducting scientific research, and even the possibility of interstellar colonization. This would fundamentally change our relationship with space, from one of exploration to one of habitation and utilization. For now, we look forward to a future in which stars are not just points of light in the night sky, but destinations within our reach. This future promises uncharted territories and unprecedented exploration, beckoning us to continue our quest for knowledge and discovery. Our universe hides a mystery that's long captivated the human mind. A question that bridges the gap between the known and the unknown, the simple and the complex. Here on Earth, life thrives in a continuous movement of order and chaos. Every form of life is evidence of a hidden order, a pattern woven into the very fabric of existence, from the smallest microorganisms to the largest mammals. But what if the complexity of life, the very essence of our existence, could be explained not only through the lens of biology, but also through a mathematical framework? This is the territory of assembly theory, a groundbreaking concept that transcends traditional science. It's a journey into a world where math and biology converge to reveal the hidden architecture of life. Imagine a universe in which the secrets of life, from the simplest molecule to the most complex organism, are encoded in mathematical language and are waiting to be decoded, where the line between living and non-living is blurred, giving birth to new possibilities and new understanding. Let's explore how this revolutionary idea is changing our perception of life, evolution, and the cosmos itself. And maybe we can even get closer to answering the ultimate question: what is the true nature of life in the universe? Since the dawn of civilization, mathematics has been the language of the universe, a tool for deciphering the mysteries of nature. But how does this language of numbers and equations relate to understanding the very essence of life? At its core, assembly theory offers a simple but profound idea. The complexity of life can be measured and understood through a mathematical prism. Think of life as a jigsaw puzzle, where each piece represents a molecular building block. Assembly theory seeks to show how these pieces come together step by step to form the complex structures that define living organisms. Each step in this assembly process represents a leap of complexity, from simple atoms to complex proteins. The theory introduces the concept of the assembly index. The assembly index, the cornerstone of this theory, measures the number of steps required to build a biological structure. It's a numerical value that captures the essence of complexity by quantifying the immeasurable. But how does the standard model of physics fit into this? This standard model theory of physics describes the fundamental particles and forces that govern our universe. It seems completely separate from the complexities of biology. However, assembly theory bridges this gap. In the field of assembly theory, the standard model lays the foundation for understanding forces and interactions. It's a bridge between the microscopic world of quarks and leptons and the macroscopic world of living things. Another important element of the theory is the concept of studying dynamical systems, phase space. This is a mathematical concept used to describe all possible states of a system. In the context of assembly theory, phase space allows us to map the path of the assembly of life. From a single point representing the simplest form of life, phase space expands, branching out into almost infinite possibilities, each pathway representing a different route that life can take. In this limitless mathematical landscape, the paths of evolution and its complexities unfold. This mathematical framework gives us a new perspective on the complexity of life. It's not just about the particles and forces described by the standard model, but how these elements combine and interact over time to create the diverse pattern of life we see around us. This is where the chaos of random molecular interactions gives way to the order of living structures. So let's ask ourselves this question. Are the complexities of life simply the product of chance, or is there a deeper cause? Let us consider two sharply contrasting concepts, complexity and entropy. Entropy, a measure of disorder and randomness, seems to be at odds with the complexity we observe in life. How do these opposing forces coexist in the natural world? It's here that assembly theory offers a revolutionary perspective. So, central to assembly theory is the assembly index, a revolutionary tool designed to measure the complexity of life. Think of it as a cosmic ruler, measuring the steps required to assemble a biological structure from its simplest components. Imagine a single molecule as the starting point on this scale. As you move up the scale, each step represents a more complex assembly, from molecules to cells and beyond. The higher the index, the greater the complexity, and the less likely it is that the structure could have arisen by chance. Now let's delve into the interaction between entropy and complexity. Entropy, a concept rooted in thermodynamics, suggests that systems naturally tend toward disorder. However, life defies this tendency, evolving from simple origins to a variety of forms combined into the complex ordered structures we see today. How does assembly theory resolve this apparent contradiction? It suggests that life is inherently a process of overcoming entropy. Through the lens of the assembly index, we see the complexity of life is not a challenge to entropy, but a journey through it. Consider the early Earth, a primordial soup of simple molecules. Over millennia, driven by the laws of physics and chemistry, these molecules began to assemble into more complex structures. Each step along the way marked a victory over entropy, a step toward greater complexity in life. Rethinking evolution through assembly theory, we see it not as a mere biological process, but as a mathematical inevitability. The emergence and evolution of life became a story of increasing complexity, a story written in the language of mathematics. Let us now turn to a very trivial question, but one that shines in a new light. Are we alone? The search for extraterrestrial life has captivated our imagination for centuries. Now, thanks to assembly theory, we have a new tool in this cosmic quest. Assembly theory offers a unique approach to detecting alien life. It's not about scanning the sky for radio signals or analyzing light spectra for the presence of oxygen. Instead, it's about understanding the complexity of molecules and structures that may indicate life. Imagine scanning the atmosphere of a distant exoplanet or the surface of a moon in our solar system. Using assembly theory, we could analyze the molecular complexity of the samples in search of patterns that indicate the presence of life. The higher assembly index, the more likely it is that these molecules are the result of life rather than random processes. However, the road to discovering alien life is full of challenges and limitations. One of the biggest obstacles is our understanding of life itself. Our definition of life is based on what we know. Life on Earth. What if it doesn't meet our biochemical standards? Another problem is the vastness of space. The universe is vast and our ability to explore it is limited by current technology. Even with the most sophisticated telescopes and probes, we can only analyze a tiny fraction of the cosmos. Moreover, assembly theory, while powerful, is still in its infancy. It's a new approach, and its application to the search for extraterrestrial life is uncharted territory. There are questions about its applicability and accuracy in different environments, especially those that are very different from terrestrial environments. Despite these problems, the potential of assembly theory in the search for alien life is enormous. It could redefine our understanding of life in the universe, opening new doors in astrobiology. So assembly theory offers a new way of looking at life, not just as a biological phenomenon, but as an emergent property of cosmic complexity. Imagine the early days of our planet, a world in motion, a crucible for the chemistry of life. Here in this chaotic environment, simple molecules began the journey of assembly, a process governed by the laws of physics and chemistry, but leading to something much deeper. Life, according to assembly theory, emerges when these molecular structures reach a level of complexity that allows them to store and reproduce information. This is where chemical memory, a crucial step in the evolution of life, comes into play. Chemical memory is the ability of certain molecular structures to retain structure. In other words, we can say this is the blueprint for life. In the world of assembly theory, this is where reproducibility becomes key. The ability to reproduce these patterns, to pass them on from generation to generation, is what drives the evolution of life. From the simplest RNA molecules in the primordial soup to the vast diversity of life we see today, each step in this evolutionary journey has been a step up the assembly index. Each increase in complexity represents a triumph over the entropy that governs the universe. But the story of the origin and evolution of life is not just a story of increasing complexity. It's also a story of resilience and adaptability. Life has found a way to thrive in the most extreme environments, from the depths of the ocean to the fringes of space. In the realm of scientific discovery, every new theory is scrutinized and debated. Assembly theory, a concept that promises to revolutionize our understanding of life and complexity, now stands at a crossroads, being questioned by critical voices such as Dr. Hector Zennel. The critique presented by Zennel raises fundamental questions about the future evolution of assembly theory. Covering an impressive 18,000 words, the article will require time and thought, taking approximately 1 to 2 hours of dedicated reading. This is not a cursory look at the topic, but a deep dive into the heart of the scientific debate. For those who are interested, we leave a link in the description to both articles, the study and the counter-arguments to it. Looking to the future, the role of assembly theory in scientific research remains uncertain. Will it be able to adapt and overcome these challenges? Or will it remain a footnote in the history of science? Despite the disagreements, one thing is clear. The debates surrounding assembly theory have initiated a conversation about the nature of scientific discovery. They emphasize the need for transparency, rigor, and humility in pursuing knowledge. In the end, the impact of assembly theory on future research may not lie in its specific claims, but in the lessons it teaches us about the scientific process. As we explore the mysteries of life in the universe, such theories will come and go. But the quest for understanding, the quest to unlock the mysteries of our existence, will always remain at the center of the interest of scientific research.
When you look at the night sky, you can see thousands of stars using nothing but your eyes, far from the lights of cities. In fact, there are many more stars in the sky which are too faint for us to see. Every single star that you can see is a part of our Milky Way galaxy, our heavenly home that has captured people's attention for ages. The shimmering band of stars, dust, gas, and dark matter that makes up the night sky captures our attention. These elements are all held together by gravity. As we navigate through the cosmos, an intriguing enigma emerges. What is the Milky Way truly like? What makes it up? And where does our solar system exist in the Milky Way? Astronomers have been baffled by these fundamental questions for many centuries, and finding answers was no easy task. But beyond its luminous beauty lies a tapestry of mysteries waiting to be unraveled. Join us today as we embark on an amazing adventure around the Milky Way, uncovering its mysteries, wonders, and majesty. You're probably somewhat familiar with our solar system. If nothing else, you probably already know that it contains 8 planets, in addition to the Earth, the Sun, moons, and several other celestial bodies like asteroids and Pluto. However, there is a lot more beyond the solar system of which you may not be aware. From Earth, we can see roughly 6,000 stars without the use of a telescope. Even while that seems like a large number of stars, it represents a very small portion of the total. In fact, for every star you can see, there are more than 20 million you cannot see. The majority of stars are either too dim, too far, or obstructed by clouds of cosmic dust. While the Milky Way galaxy contains all of these stars, there are other larger galaxies as well, including the Andromeda Galaxy. Every galaxy is a system made up of various stellar remnants, interstellar medium, and star systems. Astronomers believe there are 100 billion galaxies in the cosmos, yet they are not sure. Intergalactic space, which contains a thin gas, lies in between the galaxies. Given the size of our solar system, and the fact that it is only one of many in our galaxy, it is understandable why the universe is thought to be infinite. This truly helps to put into perspective how tiny both Earth and humans are in the big picture. Through the use of radio and X-ray telescopes, scientists have been able to gather information during the past century about the composition of the interstellar medium. They have shown that it is made up of extremely diffuse ionized hydrogen atoms, dust, and cosmic rays scattered throughout thick gas clouds that are thought to be the birthplace of new stars. But because of the Sun, all 8 planets, and a far-off disk of debris known as the Kuiper Belt, its precise nature just outside our solar system has remained mostly unknown. The Kuiper Belt is located between 30 and 50 astronomical units from the Sun. 1 astronomical unit is equivalent to the distance between Earth and the Sun. The heliosphere, a massive protective bubble created by the solar wind, surrounds them all. This bubble buffets against the interstellar medium like an invisible shield, keeping out most dangerous cosmic rays and other material as the Sun and its surrounding planets hurtle across the galaxy. Without the heliosphere, life would certainly have evolved differently, and maybe not at all. The area where the Sun's magnetic bubble ends and weakens is known as the interstellar space border. The heliosphere, a magnetic bubble, is full of plasma or ionized gas. The solar wind, which pulls magnetic field lines away from the Sun, blows material into the heliosphere. With its own magnetic fields and charged particles, the plasma in the interstellar medium exerts an inward push on the heliosphere's edge, creating a complex and dynamic structure there. When the solar wind encounters interstellar space, it begins to weaken and slows to approximately 62 miles per hour. It was previously traveling between 370 and 430 miles per hour. The termination shock is the point at which this happens. The heliosheath is the area in the heliosphere where the solar wind continues to slow down after the termination shock, while the heliopause is the outermost point of the heliosphere. The solar wind stops and gives way to interstellar space at the heliopause, which is located around 11 billion miles or 18 billion kilometers from the Sun.
5, 4, 3, 2, 1. MDS, we have ignition, we have a liftoff.
Since the beginning of human space exploration, only 2 probes have made it to interstellar space, or the area outside of the solar system. After launch in 1977, Voyager 1, the first spacecraft, took more than 30 years to reach the heliopause, a limit that scientists believe marks the beginning of interstellar space. It was an amazing accomplishment, sending back vital information via a medium unaffected by the Sun. As we exit the solar system, we will reach Alpha Centauri. The triple star system, which is the closest star system to Earth, located at about 4.37 light-years away in the constellation Centaurus. It is a triple star system consisting of 3 stars, Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri AB is a binary star system made up of Alpha Centauri A and B, which are Sun-like stars, classified as Class G and K, respectively. These 2 main stars have an apparent magnitude of -0.27, making them appear to be a single star to the unaided eye. Only Sirius and Canopus are brighter than it, making it the brightest star in the constellation and the 3rd brightest in the night sky. Alpha Centauri B is smaller and colder than Alpha Centauri A, with 0.9 solar mass and less than 0.5 solar luminosity. While Alpha Centauri A has 1.5 times the luminosity and 1.1 times the mass of the Sun. The 2 have a 79-year orbital period around a shared center. The distance between A and B fluctuates from 35.6 astronomical units, or roughly the distance between Pluto and the Sun, to 11.2 AU, or roughly the distance between Saturn and the Sun, due to the eccentricity of their elliptical orbit. In the Alpha Centauri system, Proxima Centauri is the star nearest to the Sun, located approximately 4.2 light-years from Earth. Robert Innes, a Scottish astronomer, made the discovery of the star in 1915. Proxima Centauri is a red dwarf star, which is the most common kind of star. It is roughly 7 times smaller than the Sun, and a little more than half as hot at 3,100 kelvins. On the other hand, our Sun is 5,772 kelvins. As a matter of fact, this little star is just 50% larger than Jupiter. Red dwarf stars have long lives because they consume hydrogen fuel very efficiently. Proxima Centauri is expected to remain in its current state for more than 4 trillion years. Although the Alpha Centauri system can be seen in the constellation Centaurus, Proxima Centauri is usually not visible to the human eye. Proxima Centauri orbits the other 2 stars in the system, Alpha Centauri A and B. Proxima Centauri takes 550,000 years to complete an orbit of A and B. With an apparent visual magnitude of 11, Proxima Centauri is the dimmest of the 3 stars. This star emits light at a slower rate than the Sun, with a luminosity of 0.17%, that of the Sun. However, Proxima Centauri is categorized as a flare star, which is prone to massive solar flares, because its brightness can vary by more than 1 magnitude in a matter of minutes. These flares, which occur multiple times a day, have the potential to be powerful enough to make Proxima Centauri visible to the human eye. The greatest solar flare ever observed in the Milky Way galaxy was released by Proxima Centauri in 2019, glowing 14,000 times brighter in ultraviolet wavelengths than normal. Even though Proxima Centauri will live longer than the Sun, it will eventually meet the same fate. Proxima Centauri will end up as a burning white dwarf star because it does not have the mass to turn into a neutron star or a black hole when its hydrogen supply runs out. As of 2022, astronomers have detected 3 planets orbiting Proxima Centauri: Proxima Centauri B, C, and D. These are the closest planets outside the solar system. Red dwarf stars are small and cool. Thus, planets can circle quite close to them and still be classified as being in the habitable zone. This is the range of distance from a star where a planet's water, if any, could be liquid and potentially support life. Proxima Centauri B was discovered in 2016 and estimated the planet to contain about 17% more mass than Earth, and thus likely to be a rocky planet as well. Proxima Centauri B is still within Proxima Centauri's habitable zone, despite being far closer to its star than Earth is to the Sun. It orbits Proxima Centauri every 11 Earth days at a distance of about 0.049 AU, over 20 times closer to Proxima Centauri than Earth is to the Sun. Proxima Centauri B is most likely tidally locked like our Moon, with one side always facing Earth, given that it is far closer to its star than Earth. It is therefore possible that liquid water exists on the opposite side, but its habitability is unknown due to the extreme radiation and flares from its host star. Proxima Centauri B feel the gravitational pull of their stars much more strongly than we feel the tidal effect of our Sun. Here on Earth, the Moon exerts more tidal force than the Sun, also because it's so much closer. And tides don't just pull on the ocean, they can also move air. It's possible that the tidal pull on the atmosphere of Proxima Centauri B is up to 500 times stronger than that of Earth's atmosphere. It's likely that Proxima Centauri B is getting close to the maximum tidal force that a planet can withstand and still retain a solid surface. However, Proxima Centauri B's climate and weather are mostly unaffected by its extremely high tides. Situated just outside of the habitable zone at around 1.5 astronomical units from the red dwarf is the mini-Neptune exoplanet Proxima Centauri C, which is around 7 times the size of Earth, and orbits its star once every 1,900 Earth days. First thought to have been discovered in 2019, the super-Earth planet, it appears to shine much brighter than expected for that size, indicating that it may be shrouded in dust clouds or circled by a ring system. The projected planet's estimated temperature by astronomers is extremely cold, probably close to minus 233 degrees Celsius. This makes it uninhabitable due to its distance from its star and large mass. The gravitational pull of Proxima Centauri C caused its parent star's velocity to wobble, which led to the star's initial detection in 2019. In 2020, pictures from the Hubble Space Telescope from 1995 were used to confirm Proxima Centauri C existence. It is therefore one of the rare exoplanets with visual confirmation. A third planet was discovered in 2022 around Proxima Centauri. The exoplanet, known as Proxima Centauri D, orbits its star at a distance of roughly 3% of Earth's distance from the Sun and contains about 25% of Earth's mass. Every 5 Earth days, Proxima Centauri d completes one orbit around its star due to its relative proximity to it. It is among the lightest exoplanets that scientists have yet observed. Furthermore, in 2021, scientists detected what may be the first indications of an exoplanet circling Alpha Centauri A, also known as Rigil Kentaurus, in the star's habitable zone called Candidate C1. It is estimated that C1 has a mass between half of Saturn and Neptune and orbits Alpha Centauri A at a distance of roughly 1.1 AU. Using direct thermal imaging, C1 was found. With an elongation of around 0.1 arcsecond, it looks to be as bright as a giant planet. This is consistent with the orbital motion of a planet in a 70-degree orbit. The fact that C1 is situated in the habitable zone of Alpha Centauri A and may be a mini-Neptune or super-Earth makes the discovery of this exoplanet much more interesting. We are almost certain that planets similar to Earth exist in Alpha Centauri. But the main question is, could humans ever actually live there? The most challenging obstacle in our quest to set up a new home in the Alpha Centauri system would undoubtedly be traveling a huge distance to reach these 3 stars. Even though Alpha Centauri is the nearest star system to Earth, it is still more than 4 light-years away. That comes to roughly 23.5 trillion miles or 37.8 trillion kilometers. We would need a far faster spacecraft or another means of transportation to cover such a great distance. NASA claims that the Space Shuttle Discovery, which was discontinued in 2011, had a top speed of about 17,500 miles per hour. Still, reaching Alpha Centauri would take more than 148,000 years, even at this steady speed. NASA estimates that even when the Orion spacecraft, the crew capsule linked to the Artemis program, is prepared to carry people, its maximum velocity will be approximately 20,000 miles per hour. This won't significantly cut down this travel time to Proxima Centauri. That's even if either of these vehicles was designed to journey out of the solar system, rather than just making relatively short trips to the Moon or Mars. As we have already discussed, the only spacecraft to make it out of the solar system thus far are Voyager 1 and 2. Even at their top speed of over 35,000 miles per hour, it will take them nearly 40,000 years to travel 2 light years to reach the indistinct boundary between Proxima Centauri and our solar system. That implies that it might take these spacecraft more than 80,000 years to reach close to the star. After all, it takes light more than 4 years to reach Alpha Centauri. A spacecraft needs to be extremely tiny and robotic in order to reach a distant star in a reasonable amount of time, like within a generation. Furthermore, it still needs an incredibly strong energy boost to get up to speed. And that is the basic concept behind the Breakthrough Starshot project. By creating a light sail-equipped nanocraft called Starship that would be sent into Earth orbit. The mothership would release the tiny probes one at a time, which would then ride the beams of a colossal ground-based laser array. The main challenge, though, is the Earth's atmosphere, which distorts laser and incoming light and makes it challenging to apply the force required to move a spacecraft forward. Much more potent lasers on the ground would be able to keep a close focus on the space mission thanks to small lasers mounted on satellites that would evaluate atmospheric impacts in real time. To send out the vessel at any given time, the required lasers need an astounding 100 gigawatts of power, which is equal to the total US electricity usage. But the lasers only need to operate for 10 minutes at full power. They plan to employ 100 million lasers to distribute the electricity across an area of 1 kilometre square. The Starshot team is determined to push the boundaries of space exploration. When the lasers are switched off, the object racing through space will be travelling at a stunning 20% of the speed of light, more than 130 million miles per hour, or 216 million kilometres per hour, with a diameter of little over 10 meters. This spacecraft could reach to Alpha Centauri in about 22 years. But it might be significantly slowed down by the sun's gravitational pull and interstellar debris. It will take 4 more years for the spacecraft's signals to reach Earth, even if they make it to Alpha Centauri. Alpha Centauri is moving toward Earth, but very slowly, and doesn't pose an immediate cause for concern. The distance between Alpha Centauri and Earth as of 2024 is approximately 3.26 light years. It will be at its closest in 29,700 AD, when it will be approximately 3 light years away. Over the course of a human lifetime, the slow change in distance will have no noticeable impact on Earth or the solar system. Space is a remarkable place. We're learning new things about it every day. Leaving Alpha Centauri behind, we travel on to the Barnard Star, the second nearest star to the Sun, at a distance of 5.95 light-years. It has the name Edward Emerson Barnard, in honor of the American astronomer who made the discovery in 1916. With an estimated age of 11 to 12 billion years, or roughly twice that of the Sun, Barnard's star is an old star, and most likely a thick disk member of the Milky Way. Red dwarfs that are young or middle-aged often spin fast enough to produce powerful magnetic fields, which can result in flares that quickly double a star's brightness. But Barnard's star was too old to show this kind of behavior. However, on July 17, 1998, Diane Paulson and her colleagues at NASA's Goddard Space Flight Center revealed that a flare similar to this one had been released by Barnard's star. At the time, the star's spectra was being obtained using the 2.7-meter telescope at McDonald Observatory by William Cochran of the University of Texas at Austin. His hope had been to find alterations that would point to the existence of planets in orbit. Rather, he saw emission lines in the spectrum, which showed that the star might be flaring. 4 years later, Cochrane team's investigation revealed that the star's hot blue flare was similar to those from younger red dwarfs, even though it was quite old. The temperature of the flare was at least 8,000 Kelvin, which was more than twice as hot as the 3,100 Kelvin temperature of the star. As Barnard's star gets closer to us, its distance from us is decreasing by 0.036 light-years every century, at an incredibly fast speed of 108 kilometers per second, or 67 miles per second. Its closest approach to the Sun will be at a distance of just 3.85 light-years by 11,800 AD. In terms of its proper motion, Barnard's star is also the fastest-moving star in Earth's skies. Another feature that makes Barnard's star unique is the largest proper motion of any star, which is approximately 10.4 arcseconds per year, or the equivalent of a lunar diameter every 180 years. Since of this and its relative closeness, it is an ideal target for exoplanet searches, since any systematic variations in its motion across the sky brought on by planets in orbit would be more noticeable. Finally, a planet was found around Barnard's star in 2018. The planet orbits the star at a distance of roughly 60 million kilometers or 37 million miles on a 233-day orbit, with a mass at least 3.2 times that of Earth. The planet is not in the habitable zone due to the star's low brightness, and any water on its surface would probably be frozen. As we go farther away, around 8.6 light-years away, near the constellation of Orion, we will find Sirius, also known as the Dog Star, or Sirius A, which is the brightest star in Earth's night sky. With a mass twice that of the Sun, Sirius has a diameter of 1.5 million miles or 2.4 million kilometers. The star Sirius would outshine our Sun by a factor of more than 20 if it were positioned next to it. Within the Canis Major constellation, Sirius is a binary star. The star's name comes from the Greek word Sirios, which means glowing or scorching. With a surface temperature of almost 18,000 degrees Fahrenheit, Sirius has a bluish tint and is 25 times brighter than the Sun. It is clearly visible in the winter night sky of the northern hemisphere. The ancients were familiar with Sirius due of its extreme brightness. Nevertheless, astronomers were taken aback when Sirius B, a companion star, was discovered in 1862. The star is visible to the naked eye. On the other hand, Sirius B is 10,000 times fainter than Sirius. Thanks to data from the Hubble Space Telescope, astronomers were finally able to estimate the mass of this faint object in 2005, despite the fact that it is extremely difficult to observe from Earth. Within 20 light-years of the Sun are around 131 objects, including stars, brown dwarfs, and sub-brown dwarfs. Only 22 stars are bright enough to be seen without a telescope, meaning their visible light must be at least 6.5 apparent magnitude, the lowest brightness that can be seen with the naked eye from Earth. The known 131 objects abound in 94 stellar systems. Out of these, 103 are main sequence stars, consisting of 23 typical stars with a higher mass and 80 red dwarfs. In addition, scientists have discovered 21 brown dwarfs, one sub-brown dwarf, Y08550714, which is possibly a rogue planet, and 6 white dwarfs. White dwarf are stars that have used up all of their fusible hydrogen. A red dwarf candidate, known as Schultz's star, and a companion brown dwarf, passed near the edge of the Oort cloud around 70,000 years ago. At this moment, it is approximately 22 light-years away from the Sun and has likely triggered a comet storm that will take over 1 million years to reach the inner solar system. The Kuiper Belt object's orbits were impacted by its passage. Some other stars, such as the G-type star HD 7977, have also been researched. It had its close pass around 2.8 million years ago, and it is currently located about 247 light-years from Earth. Of course, past interactions aren't the only thing to consider about. There will be more stars in the future. In the next 15 million years, 694 stars are predicted to approach the solar system at a distance of less than 516 light-years, based on data from the Gaia telescope's second data release. 26 of them are likely to arrive within 3.3 light-years, and 7 more within 6 light-years. Due to the sheer number of stars that must be surveyed, this number is probably much higher. For example, a star that was approaching the solar system 10 million years ago would be 600 to 6,000 light-years away from the Sun today, whereas millions of stars are now closer to the Sun. Gliese 710, a star, is among the most well-known instances of a close future passage. It is an orange star, around 60% the size of the Sun, located in the Serpens constellation. This star is heading in our direction at a speed of 51,499 kilometers per hour, or almost 32,000 miles per hour. In 1.29 million years, it will pass the Sun at a distance of around 10,520 AU. It's over 100 times the distance to Pluto, which orbits the Sun at an average of 39.5 AU. But it still has the potential to disrupt the solar system. If humans are still around on Earth at that point, we don't have to worry about any disruptions to our orbit. If Gliese 710 has any effect at all, it might only have it on the outer solar system. It shouldn't have any impact on anything inside 40 astronomical units. But still, it could possibly cause disruptions to the Oort cloud because it has a very high probability of going through it. For millions of years, comet showers would result from that, heading toward the Sun. This might lead to roughly 10 comets visible to the unaided eye every year. Searches for stars that are close to the Sun could not only be an opportunity of finding ancient comets, but also of predicting an intriguing future for observers on Earth millions or even thousands of years from now. The local interstellar cloud, which is around 30 light-years large, is where the solar system and the other stars and dwarfs are now moving within or close to it. The local interstellar cloud is, in turn, contained inside the local bubble, a cavity in the interstellar medium about 1,000 light-years across, and has an odd peanut shape. Our Sun was far away when the bubble first formed 14 million years ago, but about 5 million years ago, the Sun's path made its way into the bubble. Interestingly, star formed on the surface of the bubble, but not inside it. There are 7 star-forming regions around this bubble. Because of this local bubble, life has become possible on Earth today. As we go farther away, we will reach Orion constellation, around 1344 light-years away from Earth. 1 light-year is the distance light travels in a single year, about 6 trillion miles or 10 trillion kilometers. The Orion constellation is one of the 88 modern constellations and is named after the hunter in Greek mythology. It contains over 60 stars, including Betelgeuse, a red supergiant star located at around 650 light-years away. This is one of the largest known stars, with a diameter of about 767 million miles or 1.2 billion kilometers. It's about 700 times the size of the Sun and has a mass between 10 and 20 times that of the Sun. Because Betelgeuse may have less than 300 years of fuel left in its core, there has been continuous discussion throughout the world on whether or not it would explode. The star's core will collapse into a black hole as it burns through those final drops, blasting out the star's outer layers at speeds of up to 25,000 miles per second or 40,000 kilometers per second. Astronomers refer to this blazing demise as a supernova explosion, and in Betelgeuse's case, it will be a breathtaking sight for observers on Earth. Those layers of gas and dust will shine in our sky for several weeks, comparable in brightness to the full moon, because the star is only 650 light-years away from Earth. The issue is that most astronomers do not think Betelgeuse is quite ready for a big explosion just yet. Astronomers normally expect that it will blow up in the next 100,000 years, or soon on a cosmic time frame, not a human one. The other famous stars in this constellation is in the line Orion's belt, which consists 3 stars located around the middle of the constellation Orion. These are Alnitak, Alnilam, and Mintaka, from east to west. The belt is perhaps the most recognizable feature of Orion because it is visible all around the world. These three supergiant stars separately are thousands or tens of thousands of times brighter and several times more massive than the Sun. Despite these stars look closer to one another in the sky, they are actually light years apart. Orion's belt is mainly used by astronomers as a celestial landmark when searching for M42, also known as the Orion Nebula. M42 is located below the belt and is one of the most visible Messier objects for beginner astronomers, as it is easy to locate and view with a telescope or pair of binoculars. Looking at it is like looking into a celestial nursery where new stars are born. One of the largest gas and dust clouds in our Milky Way galaxy is the Orion Nebula. It is approximately 2 million years old and located about 1,300 light-years away from Earth. Because the magnificent nebula has an apparent brightness of +4, it is even visible with the human eye. On the astronomical magnitude scale, +6 is the faintest object that, in the best lighting conditions, is visible to the human eye. This massive nebula, which has a diameter of between 30 and 40 light-years, could be giving birth to 1,000 stars. Within the nebula is a young open star cluster, whose stars are still only loosely connected by gravity after having formed together in the gas cloud. It is sometimes called the Orion Nebula Star Cluster. An international group of astronomers suggested in 2012 that this cluster in the Orion Nebula might have a black hole at its heart. Through small telescopes, you can see the 4 brightest stars in the Orion Nebula, known as the trapezium. The Orion Nebula is illuminated by the light of the young, hot trapezium stars. In terms of star lives, these stars are young, having only the age of approximately 1 million years. An infrared picture of the Orion Nebula was taken by the James Webb Space Telescope last year. It shows an explosion of dust, stars and clouds in red, purple and blue against a background of dark space. Additionally, 540 planetary mass objects with masses ranging from 0.6 Jupiter masses to Jupiter itself have been discovered by James Webb within the nebula. Among these planetary mass objects, the most fascinating are the Jupiter mass binary objects, which aren't separate objects orbiting in space by themselves. Our Milky Way galaxy is a spiral galaxy. A spiral galaxy is a galaxy that looks like a flat, rotating disk with a bulge in the center and spiral arms that extend outward from the bulge. While there are many minor arms and just 2 major arms in our spiral galaxy, astronomers used to believe that there were 4 major arms. Scientists have found that just 2 arms, wrapping off the ends of a central bar of stars, dominate the Milky Way's beautiful spiral structure. These discoveries were made possible by NASA's Spitzer Space Telescope using infrared imagery. The 2 major arms of the galaxy, Scutum Centaurus and Perseus, are visible at the tips of a thick central bar, while Norma and Sagittarius, the 2 now demoted minor arms, are situated in between the major arms and are less distinct. Although the minor arms are mainly made up of gas and areas where stars are forming, the major arms have the largest densities of both young and old stars. Large telescopes are used by radio astronomers to study the motions of those hydrogen clouds that trace the arms. With a pitch angle of around 9 degrees, the Perseus arm has a spiral extension and measures over 60,000 light-years in length and 1,000 light-years in width. and has the well-known Crab Nebula in addition to double clusters. On the other hand, the Scutum Centaurus arm is around 55,000 light-years in length and 1,000 light-years in width. Our solar system lies between two prominent spiral arms, the Perseus arm and the Scutum Centaurus arm. However, we are not completely free floating in empty space. We are situated on the edge of the Orion Cygnus arm, sometimes referred to as the Orion arm or local arm, which is a small spiral arm. This spiral arm spans about 10,000 light-years in length and 3,500 light-years in diameter. However, a 2016 analysis indicates that its length may exceed 20,000 light-years. The Orion arm is named after the Orion constellation. The solar system is located in the local bubble on the inner edge inside the Orion arm. It is located at 26,000 light-years from the galactic center, halfway down the length of the Orion arm. You might be surprised to hear that the Sun takes 250 million years to complete one rotation around the Milky Way. This is referred to as a cosmic year or galactic year. Thus, during its lifetime, the Sun is estimated to have completed only 18 to 20 orbits since the beginning of mankind. The solar system orbits the Milky Way at a speed of about 220 km per second, or 0.073% the speed of light. The solar system takes around 1,400 years to travel 1 light-year at this speed, or 8 days to travel 1 astronomical unit. Following the ecliptic, the solar system is traveling toward the zodiacal constellation Scorpius. The last time the solar system was in this position in the Milky Way, there were still dinosaurs on Earth. Who knows when it will happen again? Humanity might be extinct, or it might have evolved into something else entirely. Our place in the galaxy is important because it seems that galaxies have habitable zones, just like planetary systems. Because many of the Milky Way's suns orbit the galaxy along paths that take them through the deadly spiral arms, an astounding 95% of them may not be able to support habitable planets. Radiation from the crowded stars is deadly for any star that goes through one of these stellar swarms. In order to maintain its alignment with the galaxy's rotation, our solar system orbits sufficiently far from the galactic center to stay in the calmer region between the spiral arms. Within a large and intricate galaxy, the Earth and its planetary siblings are well situated in a quiet, resource-rich region. As we go closer to the center of our Milky Way galaxy, located roughly 9,500 light-years away from Earth in the Scutum constellation, we will reach UY Scuti. It's considered to be one of the largest known stars, with a radius of 1.18 billion kilometers, which is 1,700 times larger than the Sun's radius. This would give the star a diameter of over 8 astronomical units. That is equivalent to 8 times the distance between Earth and the Sun, or 150 million kilometers, or 93 million miles. Because of this hypergiant star's immense size, its outer surface would reach well beyond Jupiter's orbit, which is around 5 times further from the Sun than Earth. The gas nebula that is ejected from the star stretches 400 times the distance between Earth and the Sun, far beyond Pluto's orbit. Or look at it this way. More than 1 million Earths could fit inside the Sun, but some 5 billion suns could fit inside a sphere the size of UY Scuti. Not surprisingly, UY Scuti is classified as a hypergiant star, which is the classification which comes after supergiant and regular giant. although it may be the largest due to its size, but it is not the heaviest or most massive star. The term mass in massive refers to the amount of matter in the star. The heaviest star is R136A1, which weighs in at about 300 times the mass of the Sun, but only about 40 times the radius of the Sun. On the other hand, UY Scuti has a size significantly larger than the Sun, although having only a mass between 7 and 10 times that of the Sun. Similarly, being so massive doesn't mean that UY Scuti is that hot either. In fact, its surface is almost half as hot as our Sun's. Another thing that makes UY Scuti particularly interesting is the fact that it's a variable star. Over time, variations in luminosity can be seen as a result of the material's continuous fluctuation at and near the surface, due to the unstable battle between the forces of gravity and fusion. These stars are of special interest to astronomers because they can shed light on the inner workings of stars. Although UY Scuti, like many other stars, is thought to be capable of supporting a planetary system, it's possible that the innermost exoplanets have already been swallowed by the host star's expansion. Furthermore, UY Scuti is so faint that it is improbable that we will ever be able to witness those exoplanets directly. As we go to the center of our Milky Way galaxy, around 26,000 light-years away, we see a celestial enigma. Sagittarius A. This supermassive black hole is an incredible cosmic monster that is beyond understanding. Sagittarius A is no ordinary black hole. Its estimated mass is a staggering 4.3 million times that of our Sun. Imagine compressing millions of suns into a single point, a gravitational singularity where space and time warp beyond recognition. This massive monster is located at the heart of the Milky Way, our spiral galaxy. A black hole is a region of space so densely populated with mass that nothing can escape from it, not even light. A black hole is invisible to us, but telescopes can see the materials surrounding it. Black holes surrounding matter, which can consist of gas and dust, warms up and releases detectable radiation. In some cases, telescopes can observe the gravitational influence of a black hole on the motions of nearby individual stars. Observing it directly is a formidable challenge. Sagittarius A is obscured by a dense layer of dust that prevents optical observations. However, astronomers have developed smart strategies to break through this cosmic curtain. The Event Horizon Telescope, a network of radio telescopes spanning a planet, made history in April 2019, when it successfully obtained the second-ever image of a black hole. This discovery comes after the EHT collaboration released the first picture of M87, the black hole, at the center of the farther-off Messier 87 galaxy in 2019. Sagittarius A was visible in the photograph as a dim outline against the brilliant background. This turbulent region, known as the accretion disk, feeds matter to the hungry black hole, causing occasional X-ray flashes. Despite Sagittarius A being less massive and more than 1,000 times smaller than M87, the two black holes look remarkably similar. Its surrounding gas disk, which stretches out over a distance of 5 to 30 light-years, can reach temperatures of up to 18 million degrees Fahrenheit or 10 million degrees Celsius. Not only is the supermassive black hole at the center of our galaxy spinning, but it's doing so at nearly maximum speed, consuming everything in its path. Physicists used NASA's Chandra X-ray Observatory to study the X-rays and radio waves coming from material outflows in order to measure the rotating speed of the supermassive black hole in the Milky Way. A black hole's spin speed is represented by the letter A and ranges from 0 to 1, where 1 is the maximum rotational speed to a specific black hole and represents a significant portion of the speed of light. Physicists discovered that Sagittarius A rotates at a speed of 0.84 to 0.96, which is near the upper limit determined by the width of a black hole. The spin of a black hole differs from that of other celestial bodies. Black holes are truly regions of space-time defined by an outer non-physical boundary termed the event horizon, beyond which no light can escape, unlike planets, stars, and asteroids, which are solid things with physical surfaces. This implies that as black holes spin, they literally distort space-time itself, dragging anything inside the ergosphere with them. This phenomena, known as frame dragging or the lensing-Thirring effect, which implies that knowledge of a black hole's spin is necessary to comprehend how space acts around it. Additionally, the frame dragging around black holes produces strange visual effects. The path of light gets twisted or curved as it approaches a revolving black hole due to spacetime's rotation. This causes a process known as gravitational lensing, in which the rotating black hole's gravitational pull bends the path of light. Frame dragging effects can result in the production of light rings and even the shadow of a black hole. These are examples of how light is affected by black holes' gravitational pull. The theoretical top speed of a black hole is determined by how it feeds on matter and thus how it grows. As matter falls into a black hole, it increases the black hole's spin. But there's a limit to how much angular momentum it can possess. The black hole's mass is another factor. The gravitational attraction of more massive black holes is stronger, making it harder to spin them up. This could explain why the rapidly feeding supermassive black hole at the center of galaxy M87, the first black hole ever captured on camera, is spinning at between 0.89 and 0.91, despite having the mass of 6.5 billion suns. While Sagittarius A, with its mass equivalent to about 4.5 million suns, has a spin speed between 0.84 and 0.96. But soon, something strange happened while researching this black hole. Some scientists believe that Sagittarius A may not be a black hole after all. Instead, it could be an immense concentration of dark matter. Imagine a dark pool of invisible matter forming the basic structure of our galaxy. Sagittarius A has never been directly confirmed, despite the fact that it is widely believed to be a black hole. To put it simply, it is an extremely bright radio emitter located at the Milky Way's galactic core. The astronomy community encountered a challenging problem. G2, a galaxy cloud, had moved a bit too close to Sagittarius A. The G2 gas cloud just kept drifting without undergoing any notable changes, despite the fact the supermassive black hole should have pulled it and destroyed it. Observing the interaction between the Sagittarius A and the G2 gas cloud revealed that G2 was not an ordinary gas cloud as seen by the lack of effect. They explain that at least two components had to be present to allow the cloud to pass through that close to the black hole without being devoured. One is an extended, cold and low-mass gas cloud, and the other is a very compact segment, like a dusty object that dominated the detected emission from G2 as it passed by. Astronomers, however, may be more concerned with the possibility that Sagittarius A is not actually a black hole. First, scientists created a simulation of our galaxy because they were intrigued by the idea that the Milky Way's center might actually be a mass of dark matter. Researchers found that despite the galactic center's replacement, the Milky Way galaxy still exists and operates basically in the same manner throughout the simulations. The behavior of the rotating curve in the Milky Way's outer halo was identical to that of nearby S-stars, or those connected to the radio source Sagittarius A. Taking their inquiries a step further, they proposed that darkinos, a family of particles related to fermions, may comprise the mass at the center of the Milky Way. Apart from its extreme features, such as devouring everything around it, darkinos would have the same properties as a black hole if they clumped together into a huge mass. Sagittarius A is mostly dormant and only occasionally absorbs gas or dust, but nonetheless has an estimated mass millions times that of our Sun. Although there are still a lot of unanswered questions concerning the supermassive black hole, future observations from the Event Horizon Telescope should shed light on these riddles. Stellar mass and intermediate mass black holes form when massive stars cease nuclear fusion and can no longer support themselves against complete gravitational collapse. The mechanism that forms supermassive black holes like Sagittarius A is unclear because there are no stars large enough to directly collapse into a black hole of this size. There are two possible explanations. Either smaller black holes merge in order to form larger black holes, or smaller black holes grow enormously large by consuming gas and dust from their surrounding. Sagittarius A remains an astronomical marvel, a cosmic mystery at the heart of the Milky Way. As our understanding deepens, we continue to unravel our galaxy's secrets. In 1917, American astronomer Harlow Shapley provided the first reliable measurement of the galaxy's size. He determined the size by first determining the globular cluster's spatial distribution. As had been previously believed, Shapley discovered that the galaxy is enormous, with the Sun closer to its periphery than its center, rather than a relatively compact system. Assuming that the globular clusters surround the galaxy, he calculated that the galaxy has a diameter of roughly 100,000 light-years, or 600,000 trillion miles. The Sun is located approximately 30,000 light-years from the galaxy's center. His values have held up remarkably well over the years. The Milky Way's stellar disk is roughly the size predicted by Shapley's model. Dark matter or invisible matter may fill an even larger volume than expected, while neutral hydrogen is somewhat more widely distributed. According to recent calculations, a dark matter area that includes a few visible stars might have a diameter of about 2 million light-years. In addition to having multiple satellite galaxies, the Milky Way is a member of the local group of galaxies, which is a subcluster of the Virgo supercluster, which is itself a component of the Laniakea supercluster. There are at least 100 to 400 billion stars in our galaxy, and at least that number of planets. The Milky Way and everything else in space are in motion. The radiation from the Big Bang, known as the cosmic microwave background, is used as a reference point for calculating the speed of objects in space. The Milky Way galaxy is thought to be traveling at a speed of roughly 600 kilometers per second, or 372 miles per second, inside the local group of galaxies. Since the oldest stars in the Milky Way are almost as old as the universe, they most likely formed shortly after the Big Bang's dark ages. The galactic nucleus is the site of a wide range of activity apparently powered by the black hole. The region emits X-rays and infrared light, and it is possible to see fast-moving gas clouds there. Data clearly show that matter, including some gas from the Z direction, that is perpendicular to the galactic plane, is being drawn into the black hole from outside the nuclear zone. As the gas nears the black hole, the central object's strong gravitational force squeezes the gas into a rapidly rotating disk, which extends outward about 5 to 30 light-years from the black hole. Surrounding the nucleus is an extended bulge of stars that is nearly spherical in shape, and that consists primarily of population 2 stars, though they are comparatively rich in heavy elements. A star's metallicity, or the amount of elements heavier than helium in its composition, divides stars into 3 primary population groups. Population 3 are the oldest, and population 1 stars are youngest, like our Sun. The disk portion of the galaxy contains the population 1 stars. Their ages range from 0 to 10 billion years. The spiral arms include the younger ones. The orbits of population 1 stars are well organized, with roughly circular paths in the galactic disk's midplane. Young star clusters made of population 1 stars are called open clusters because the stars are loosely bound together, in contrast to the old concentrated globular clusters. Compared to population 2 stars, population 1 stars have a higher abundance of elements heavier than helium. Astronomers frequently refer to elements heavier than helium as metals. The oldest population 1 stars have somewhat eccentric orbits that can carry them up to 3,000 light-years from the disk plane, and they have a metal abundance 0.1 times that of the Sun. The population 2 stars inhabit the spheroidal component, the stellar halo and bulge. They have masses of less than or equal to 0.8 solar masses because they are old. Their ages range from 10 to 13 billion years. Their orbits are much more randomly oriented than the population 1 orbits and are highly elliptical. As a unit, the spheroidal component has little overall rotation. Population 2 stars make up globular clusters. Globular clusters were used to find the center of the galaxy because they swarm around the center like bees around a hive. On the other hand, population 3 stars are those that have not been directly observed. They are believed to have virtually no heavy elements at all. These stars are thought to be the first ones that formed in the primordial universe shortly after the Big Bang. They were extremely massive and hot, and they burned their fuel very rapidly, turning hydrogen and helium into heavier elements. When they die, they explode as supernova, scattering some of these elements into the surrounding space. These stars probably created the first heavy elements that became part of later stars, and to have played a key role in the formation of the first galaxies. Numerous globular clusters of related stars are mixed in with the stars, and both the stars and the clusters orbit the nucleus almost radially. Our galaxy is surrounded by a huge hot gas halo that is several hundreds of thousands of light-years in diameter. A halo is a spherical cloud of stars surrounding a galaxy. The mass of the halo is thought to be roughly equal to the total mass of all the Milky Way's stars. Astronomers have proposed that the Milky Way's halo is composed of 2 populations of stars. The Paranal Observatory's findings indicate that the stars in the inner halo are 11.5 billion years old. The outer halo is thought to be made up of the stellar components of smaller galactic systems. The stars in the halo are older and have lower metal content in them than the majority of the stars in the Milky Way's disk. The halo also contains gas and dark matter. The halo is evidence of the two galaxies that collided billions of years ago and reinforces the idea that the Milky Way has a dynamic origin story. In the Milky Way's stellar halo, astronomers have also found more than 200 far-off variable stars referred to as Lyra stars. These stars serve as important standard candles that are used to measure astronomical distances and are often found in globular clusters. The farthest star from Earth is about 1 million light-years away, which is nearly half the distance to Andromeda. About 90% of the matter in our galaxy is dark matter, or matter that is invisible to the human eye. Stars make up the remaining 10 to 15% of the visible stuff in the Milky Way, which is composed primarily of gas and dust. Simulations of the Milky Way's rotation have shown that this massive amount of dark matter produces an invisible halo. If the dark matter did not exist, then the stars within the Milky Way would orbit much slower than has been observed. The Milky Way's dusty ring can be observed in the night sky on a clear night. As we are located approximately 26,000 light-years away from the center of the Milky Way, we are unable to capture images of the disk. Any depiction of our galaxy that you have ever seen is either an artist's portrayal of it or a separate spiral galaxy. We don't have a picture of the Milky Way as a whole, since we can only capture images of it from within the galaxy. So why do we believe that it is a barred spiral galaxy? There are several clues. The first clue to the shape of the Milky Way comes from the bright band of stars that stretches across the sky. In locations with dark night skies, this band of stars can be viewed with the naked eye. That band comes from seeing the disk of stars that forms the Milky Way from inside the disk, and tells us that our galaxy is basically flat. Many telescopes, both on Earth and in space, have captured photographs of the Milky Way disk by capturing a sequence of images in different directions, which is similar to creating a panoramic photo with your phone or camera. The concentration of stars in a band adds to the evidence that the Milky Way is a spiral galaxy. If we lived in an elliptical galaxy, we would see the stars of our galaxy spread out all around the sky, not in a single band. The Milky Way galaxy was believed to be only a few thousand light-years large until around a century ago, and most people believed it to be the whole universe. Although other galaxies had been found, it was believed that they were only tiny objects inside our galaxy. French astronomer Charles Messier discovered the first galaxies in the 17th century, although he had no idea what they were at that time. As a skilled comet observer, Messier saw several additional fuzzy objects in the sky that he was certain were not comets. Fearing that other comet hunters would be misidentified as well, he put together a list to help them out. On Messier's list, 110 star clusters and spiral nebula were detected. The objects are denoted by M for Messier, followed by a number, for example, M51. However, it took astronomers nearly 300 years to figure out the fuzzy spiral nebulae. Some claimed that these nebulae were island universes, which are objects that are similar to the Milky Way galaxy, but exist outside of it. Others disagreed and thought that these spiral objects were actually Milky Way gas clouds. The dispute continued until the 1920s, when American astronomer Edwin Hubble measured the precise distance to a spiral nebula. Hubble discovered that one of the objects he was seeing was actually a Cepheid variable star in 1923, while studying the Andromeda Nebula, which is now known as the Andromeda Galaxy. First identified in the early 1900s by American astronomer Henrietta Leavitt, Cepheids are stars whose brightness changes periodically over time. Leavitt discovered a connection between a Cepheid's luminosity or brightness and its period that is now known as the period luminosity, the PL relationship. The PL relationship can be used to calculate the actual brightness of a Cepheid by calculating its period, which is obtained by measuring changes in brightness over a period of days or weeks. Hubble established that the Cepheid he was studying in M31 was located outside of our own galaxy by calculating its distance using the PL ratio. This put an end to the controversy surrounding the spiral nebulae and proved that they were in fact far-off galaxies similar to the Milky Way. Hubble continued his study of galaxy distances using Cepheids as his measuring tool before publishing his results in 1929. In his work, Hubble created a graph showing the distances from Cepheid variables and the velocities of galaxies, which is obtained from estimating the redshift of these galaxies' spectra. The majority of galaxies are moving away from us, or receding according to this graph, and their rate of motion, the recessional velocity, is inversely correlated with their distance from us. Distant galaxies recede more quickly than nearer ones. This was later known as Hubble's law. Hubble's initial estimates for the recessional velocity of galaxies was very high, because at the time no one knew that there were actually several different types of Cepheid variables, with slightly different period luminosity relationships. But as astronomy has advanced recently, the value of the graph's slope, known as Hubble's constant, has been reduced, and the results are now converging toward an accepted value of about 65 kilometers per second, or that galaxies recede by an additional 65 kilometers per second for every megaparsec they are away from us. There are trillions of galaxies in the universe, and up to a few 100 billion stars can be found in each galaxy. The same way that one studies atoms to understand the qualities of a material, one must study the building blocks of the universe to comprehend it. Understanding the formation and evolution of galaxies is essential for our understanding of the universe. Although the study of galaxy formation dates back around 50 years to the foundational work of Egan, Lyndon Bell, and Sandage, we still do not have a comprehensive understanding of how galaxies form and evolve. Many details still need to be explored. In addition to providing us with valuable answers to the questions like where do we come from and where are we going? Observation of galaxies other than our own also enables us to draw several conclusions about the evolution of the universe. But the only galaxy we have access to a vast amount of data on its stars is our own. The other galaxies are just too far away for us to observe star by star. Before we continue, one might wonder if knowledge of the Milky Way's development provides any insight into knowledge of other galaxies. The answer is yes. Approximately 50% of stars in the modern universe reside in Milky Way-like galaxies. To put it another way, the Milky Way is a fair representation of a typical galaxy in the universe. Our knowledge of the Milky Way's development will provide a strong foundation for our understanding of other galaxies. Soon after the Big Bang, which occurred 13.61 billion years ago, the Milky Way began as one or more small overdensities in the universe's mass distribution. Some of these overdensities were the seeds of globular clusters in which the oldest remaining stars in what is now the Milky Way formed. It's possible that about half of the material in the Milky Way originated in other far-off galaxies. These star groups and individual stars now make up the Milky Way's stellar halo. The Milky Way's mass reached a point where it began to rotate relatively quickly, only billions of years after the first stars were born. Because of the conservation of angular momentum, this caused the gaseous interstellar medium to compress into a disk from a roughly spheroidal shape. Therefore, later generations of stars formed in this spiral disk. Throughout its history, the Milky Way has consumed many galaxies to get to its current size and form. In the last 12 billion years, the Milky Way has swallowed up more than a dozen galaxies. According to cosmological simulations, it merged with a particularly massive galaxy known as the Kraken, approximately 11 billion years ago. Our galaxy is currently consuming the Canis Major Dwarf Galaxy by adding the smaller galaxy's stars to its own spiral. At present, the Milky Way is traveling at a speed of 250,000 miles per hour in the direction of the Andromeda Galaxy. It is expected that the two galaxies will collide in roughly 4.5 billion years. The Milky Way and Andromeda are the two largest galaxies in the local group. They will merge because before dark energy took over, they became gravitationally bound to one another. The merger is expected to change the night sky over Earth. The Milky Way is orbiting a point in space that is roughly halfway between it and the Andromeda Galaxy. Although it's difficult to believe, experts think that our solar system probably will survive such a terrible event. Since galaxies are primarily made of empty space, this collision will not have a significant impact on our solar system. Despite having 100 billion stars each, our galaxy and the Andromeda Galaxy are very far apart. Currently, Andromeda is located 2.5 million light-years away from Earth. Similar to how a ball in the air accelerates faster as it falls toward Earth, Andromeda will be drawn closer and faster by the Milky Way's increasing gravitational pull as it gets closer. In just 4 billion years, the Milky Way and Andromeda will have tugged and ripped at one another's throats. All that's left will be the spectral framework of two separate galaxies in the past. The carnage will go on for as long as time does not stop until the central supermassive black holes in both galaxies are near enough to one another to collide and join. By that point, the Milky Way and Andromeda galaxies, the two separate spiral galaxies, will be no more. Our solar system will have a new home in an entirely different class of galaxy called an elliptical galaxy. What about life on Earth, then? Will life on Earth continue after the merger? Well, in roughly 7.5 billion years, the Sun will grow larger and swallow the Earth, turning it into a red giant. This will happen ultimately in a timeline of about 4 billion years. As solar radiation reaching the Earth increases, Earth's surface temperature will increase. We might experience a runaway greenhouse effect, much like what's happening right now on Venus. Thus, there's a good chance that life on Earth won't exist after the merger. However, perhaps by then, some people on Earth will have developed space travel abilities. It's possible that we will have abandoned Earth and our solar system. The view of Andromeda colliding with the Milky Way might still be available to us, although from a slightly different angle. As we gaze up, let's realize how short our life is. We are stardust, seeing a cosmic tale. For whatever reason, we are here now, sitting and wondering about the universe. We, the very children of the universe, born from ordinary chemicals over billions of years, now gaze wondrously into the endless black abyss to think about it.
Beyond the Milky Way. With the size and shape of the galaxy measured, the question of our place in creation now shifted from the position of the Sun within the galaxy to the nature of the universe itself. If the progress from Copernicus through Newton to Leavitt and Shapley appears relatively fast, certainly when viewed in the context of the glacial progress through the 2,000-year dominance of Aristotelian thinking, then the decade that followed Shapley's determination of the size of the Milky Way might be described as an intellectual avalanche. The revolution was fueled from two sides. A new generation of telescopes and the increasingly sophisticated observational techniques developed by astronomers like Leavitt, Hertzsprung, and Shapley provided the data, and in parallel, theoretical physics experienced a revolution. Claims of revolutions or paradigm shifts have to be made with great care in science. Indeed, the terminology is quite unfashionable in certain academic circles. But from a physicist's perspective, there is no doubt that physics experienced a revolution in 1915, because in November of that year, Albert Einstein presented a new theory of gravity to the Prussian Academy of Science. The theory is known as general relativity, and it replaces Newton's law of universal gravitation. Many physicists regard general relativity as the most beautiful piece of physics yet devised by the human mind, and we will explore why this is so a little later. For now, let us note that the Big Bang, the expanding universe, black holes, gravitational waves, and the whole evocative landscape of 21st century cosmological language began, absolutely, with the publication of general relativity. The parallels with the Newtonian revolution are clear. Without Newton's laws, there is no deep understanding of the solar system and the motions of the planets. Without general relativity, there is no deep understanding of the large-scale structure and behavior of the universe. But we are getting ahead of ourselves. As the second decade of the 20th century dawned, the size and shape of the Milky Way galaxy was established, albeit with rather large errors, but the true extent of the universe beyond our galaxy was still hotly debated. Could we at least cling to a sort of token pre-Copernican fig leaf and place our galaxy at the center of the universe? The desire to be special runs deep. The last intellectual rearguard action against our demotion can, rather theatrically, be said to have been played out on a single evening on the 26th of April 1920 in the Baird Auditorium at the Smithsonian Museum of Natural History, Washington, D.C. This is, of course, an oversimplification, but allow me a minute to enjoy the sound of the outraged, shaking jowls of 1,000 historians of science before I qualify and partially justify this hyperbolic claim. The Mariner 10 mission had enabled scientists to see about half of the planet, so the first real glimpses into the terrain of Mercury came from the flybys of Messenger. As planetary scientist Nancy Chabot explains, before Messenger, we had only seen 45% of the planet, and we saw some stuff during the flybys before we went into orbit. But after orbiting the planet, we've now mapped 100% of the planet and seen nearly everywhere. There are some permanently shadowed regions which are still mysterious, but after mapping the full planet, we have a good idea of what the surface looks like, and craters are absolutely a dominant landform. This planet has been sitting there for billions of years and been hit over and over, and it hasn't had a lot of processes to destroy those craters. Amongst the thousands upon thousands of craters on Mercury, the largest by far is Caloris Planitia, a lowland basin 1,525 kilometers in diameter that is thought to have formed in the early years of the solar system, around 3.9 billion years ago. It was first spotted as Mariner 10 sped past in 1974, but due to the trajectory and timing of the craft, only half of it was lit, so the full character of this crater remained a mystery for another 30 years, until Messenger could photograph it in all of its glory. Taking one of its very first photos, Messenger revealed Caloris to be bigger than had been previously estimated. encircled by a range of mountains rising 2 kilometers from the Mercurian surface, whose peaks create a 1,000-kilometer boundary around the lava plains within. On the other side of the mountains, the vast amount of material that was lifted from the planet's surface at the moment of impact formed a series of concentric rings around the basin, stretching over 1,000 kilometers from its edge. The collision that created Caloris hit Mercury with such force that it also had more global consequences. Messenger photographed in great detail an area named, in the not particularly scientific vernacular, the weird terrain, a region at the planet's diametrically opposite point, the antipode to Caloris. This area of strange geological formations, distinct from the rest of the surrounding terrain, was likely created by the seismic shock wave of the Caloris impact, reverberating through the whole of the planet. Right up until the end of its mission in 2015, Messenger continued to uncover many of Mercury's secrets, including a few very particular surprises. Using a combination of photography, spectroscopy, and laser topography, Messenger revealed tantalizing evidence that even this close to the Sun, water ice can exist on the surface of a planet. Even though the Sun blasts much of Mercury's surface, the tilt of its rotational axis is almost zero, so there are craters and features around the planet's poles that never see direct sunlight. Combined with the lack of atmosphere, these regions are forever exposed to the freezing temperatures of space. And it's in this environment that Messenger was able to record the clear signature of water ice. Here, in the eternal night of a polar crater, it's cold enough for ice to survive for millions of years, just meters away from the savage ferocity of the sun's light. However, Messenger's most startling discovery was still to come. The mission objectives had been developed to explore the deep history of Mercury and provide data to test against our theories of the formation and early life of the planet. Messenger was equipped with a collection of spectrometers designed to analyze the composition of Mercury at different depths. The Messenger team had worked on a detailed set of predictions outlining the chemistry of the planet. But as the spacecraft began to sniff at the Mercurian surface, it soon became clear that our assumptions had not been quite right. As the gamma-ray and X-ray spectrometers analyzed the elements on Mercury's surface, they began to measure the unexpected characteristic signature of a number of elements such as phosphorus, potassium, and sulfur at much higher levels than they were expecting. Up to this point, the working hypothesis had been that during the formation of Mercury and all the rocky planets, as the rock condensed and combined to form the planet, the heavier elements like iron would sink towards the center, forming the bulk of the core, while the lighter elements, such as phosphorus and sulfur, would remain near the surface. These more volatile elements would then be expected to be stripped away from the surface, particularly on a planet like Mercury, which is so close to the Sun. And yet the Messenger data confirmed high levels of potassium, and sulfur was detected at 10 times the abundance of the element on Earth or the Moon. Both are volatile elements, easily vaporized, and when this close to the Sun, they simply should not have survived the planet's birth. On top of that, the Messenger data confirmed what we had long suspected about the structure of Mercury, that it is the densest of all the planets, with a massive iron core making up 75% of the planet's radius, compared to just over 50% here on Earth. The core creates a strange lopsided magnetic field, indicating that the internal dynamics of the planet are different to anything we have seen before. All of this adds up to making Mercury something of a mystery, as nothing quite accords. The eccentric orbit, the abundance of volatile elements on the surface, and the oversized iron core all point to the planet having a history far more complex than was first imagined. And the only explanation to make sense of the Messenger data is that Mercury was not born in its current sun-scorched position. It has long been supposedly known that the orbits of the planets are eternal, stable loops that sustain the structure of the solar system in an endless rhythm. But everything we are learning now suggests that this is far from the whole story. Mercury, like all four of the rocky siblings, was formed of molten rock. A few million years later, as the young planet began to cool, its crust solidified, and its journey around the sun transformed from being part of a swirling cloud into a clearly defined passage, an orbit. The path the infant Mercury travelled, however, was most probably far removed from the course it now holds. The young Mercury was born not as the closest planet to the Sun, but at a much greater distance, far beyond the orbit of Venus, beyond Earth, perhaps even beyond Mars. This was a planet that came into being in the mildest region of the solar system. It was far enough away from the Sun to allow volatile elements like sulfur, potassium, and phosphorus to be folded into its first rocks without being vaporized away by the heat of the Sun, but maybe near enough for its surface to be warmed, perhaps even just the right amount for liquid water to settle on its surface. This may well have been a planet big enough to hold an atmosphere, a watery world upon which all the ingredients of life could well have existed. Mercury, it seems, really did have its own moment in the Sun, but these hopeful beginnings were not to last. Today, it's hard to imagine the planets in any orbit other than our night sky. They feel eternal, permanent, and so it's natural to think of the solar system as a piece of celestial clockwork, a mechanism running with perpetual and unchanging precision, marking out the passage of time. In time frames that we can comprehend, days, weeks, months, and years, the motion and trajectory of the planets is just that, clockwork. We use these markers to plot out the 24 hours of a day, 365 days of a year, and the lunar cycle is, of course, intimately linked to our months. Beyond that, Newton's laws of universal gravitation, first described in 1687, allow us to this day to plot out the trajectories of all the heavenly bodies far into the future and back into the distant past. This predictability of motion is what allows us to plot great astronomical events, such as eclipses and transits, far into the future. It's why, for example, we can predict that on the 14th of September 2099, the Sun, Moon, and Earth will be in precise alignment to create the final total solar eclipse of the 21st century across North America. But 100 years ahead or behind us is nothing more than a proverbial blink in terms of the life of the solar system, and over longer durations the clockwork becomes a lot less reliable. If there was only one planet orbiting one star, for example if Mercury was the orphan child of the solar system, we would be able to calculate precisely the gravitational force between Mercury and the Sun, and to plot Mercury's orbit around the Sun with essentially infinite precision. But add one more planet into our rather vacant imaginary solar system, let's say we make it Jupiter, so there is now a gravitational force between all three objects, the Sun, Mercury, and Jupiter, and it's no longer possible to calculate exactly where they're all going to be in the future, or where they were at some point in the past. When there are more than two objects in play at any one time, you have what physicists call a chaotic system. It means the planets can push and pull one another, moving entire orbits in ways we simply cannot predict. So the further we look back in time, the less certain we are of the position of any of the planets. Our mathematics fails, so instead we have to rely on circumstantial evidence to piece together a picture of the past. In the case of Mercury, it's the evidence from MESSENGER detailing the levels of volatile elements like potassium and sulfur that enable us to begin to understand the early life of the planet and infer that Mercury must have begun life further out in the solar system than it finds itself today. So what happened next? How did a planet that began its life in the sweet spot of the solar system end up in the scorched interior? The answer lies in the other clue MESSENGER confirmed for us, Mercury's massive iron core. Relative to its size, Mercury has the most massive core of any of the rocky planets. 75% of its diameter and almost half of its mass is molten iron, compared to around just a fifth of the mass of the Earth. We've suspected the oddity of Mercury's composition for well over 150 years, and that's because of some brilliant deduction by a German astronomer called Johann Franz Encke, who determined the mass of Mercury by measuring the gravitational effect it had on a passing comet, a comet that we now call, unsurprisingly, Comet Encke. With an approximation of the planet's mass, we are able to calculate the density of the planet, and with that calculation, approximate its composition. So we've known for some time that Mercury is odd, but only with the arrival of Messenger did we begin to reveal just how odd the smallest planet actually is. By accurately measuring Mercury's magnetic field, we've been able to confirm that far from being a geologically dead planet, Mercury has a dynamic magnetic field driven by an internal force, indicating that the core is at least partially liquid. This goes against the conventional thinking of planetary dynamics, because we would expect a planet as small as Mercury to have lost its internal heat long ago. Just as Mars lost its heat because of its size, we would have expected the core of Mercury to have cooled and solidified. But Messenger's data proved otherwise. By combining precise measurements of Mercury's gravity field with the extraordinary mapping of its surface, Messenger found that Mercury's structure is unique in the solar system. It appears to have a solid silicate crust and mantle above a solid layer of iron sulfide, which surrounds a deeper liquid core layer, possibly with a solid inner core at the center of the planet. This challenges all the theories about its formation. 4.5 billion years ago, we know that the inner solar system was in turmoil. In the middle of it all, the newly born Mercury found itself orbiting far out from today's intimate proximity with the Sun, surrounded by rocky debris and scores of planetary embryos all jockeying for position. The young solar system was still a place where planets could live or die. But it wasn't just the rocky planets that found themselves disturbed. Jupiter, the largest and oldest of all the planets, was on the move. And when a planet of that size shifts its position, there are almost always casualties. We'll come back to the story of Jupiter's grand tack and the havoc it spread throughout the solar system in Chapter 3. But for now, all we need to know is that the evidence suggests that the juvenile Mercury was kicked by the gravitational force of Jupiter on an inward trajectory, finding itself flung in towards the Sun and into the path of danger. In the crowded orbits of the early solar system, such a change of course was fraught with danger, and all of the evidence indicated that this was the most violent and defining of turns in Mercury's history. As the planet swerved inwards, it collided with another embryonic world and shattered. Today we see the evidence of this ferocious collision in the strange structure of this tiny planet. A giant core has been left behind, the exposed interior of a planet that had much of its outer layer, its crust mantle, stripped away and lost to space in the aftermath of the collision. This collision not only transformed the physical characteristics of the planet, but also knocked Mercury further inwards on a lopsided trajectory that we see reflected in the most elliptical orbit of all the planets. Although we cannot be certain of these events, it's a brilliant piece of scientific deduction to use the evidence we have to create a plausible scenario of events that happened unimaginably long ago. Events that drove the first rock from the Sun from a position full of potential to a place much too close to the Sun to support any form of life. An opportunity lost. After 4 years of observation and its brilliant discovery of Mercury's ancient past, Messenger finally ran out of fuel on the 30th of April 2015 and added yet another crater to this tortured world that once held such promise. Shrouded in an unbroken blanket of cloud, the next rock from the Sun tells a very different story. Over 50 million kilometers beyond Mercury lies a world that at first sight has the potential to be far more Earth-like than her scorched inner companion. Venus is perhaps the most mysterious of all the planets. Lying on the inner edge of the so-called habitable zone, This is a planet that holds its secrets close. For centuries, it has teased us with its brightness in the early morning and early evening sky. It's so bright because it's a large planet about the same size as the Earth. It's not too far away from us either, and the clouds that shroud it are highly reflective, reflecting 3/4 of the light that hits them. That's the frustrating but tantalizing thing about Venus, because even when you look at it through a big telescope, it is featureless. You never see the surface, which means that until the 1950s, scientists could only speculate about what lay beneath. In the late 19th and early 20th centuries, many thought that beneath her clouds Venus was hiding a mirror world to Earth. If not home to complex sentient life, then certainly hosting basic life forms. Faced with that impenetrable cloak, our collective imaginations fueled the idea of a living, breathing world beneath the clouds, a shroud that meant for the first half of the 20th century, we lived convinced that we were far from alone in the solar system. Nobel Prize-winning chemist Svante Arrhenius was one of the most renowned scientists to fuel the mythology of what lurked behind Venus's cover. Like many of the scientists of his era, Arrhenius let his curiosity wander into many different realms, including astronomy, and he hypothesized at length about the Venusian environment. Assuming the clouds of Venus were composed of water, he wrote in his book The Destinies of the Stars that a very great part of the surface of Venus is no doubt covered with swamps, creating an environment not unlike the tropical rainforests found here on Earth. Expanding on this picture, he suggested that the complete cloud cover of the planet created a uniformity totally unlike the extremes of weather that define different parts of the Earth. In Arrhenius's imagination, this stable environment, with a consistently uniform climate all over the planet, meant that any life on Venus lived without the evolutionary pressures of changing environments that drive natural selection here on Earth, leaving Venus in an evolutionary limbo akin to the Carboniferous period. Describing a world full of prehistoric swamps and dark forests, Arrhenius created the perfect canvas for science fiction writers of the time to conjure up a menagerie of curious life forms lurking beneath the clouds. Today, Arrhenius is far less known for his fertile imaginings on the wildlife of Venus than he is for his work on the climate of Earth. In 1896, he was the first scientist to use basic principles of chemistry to demonstrate the impact that the atmosphere can have, in particular levels of carbon dioxide, on the surface temperature, a process that was called the Arrhenius effect, but is now known as the greenhouse effect. An effect that would not only have profound consequences for our understanding of our impact on our own planet, but would also be vital in explaining the true nature of Venus beneath the clouds. By the 1920s, as ground-based technology improved, we stopped painting the surface of Venus with our imaginations and started filling in the gaps with facts. The first spectroscopic analysis of the planet's atmosphere suggested that it wasn't water or oxygen that filled the clouds of Venus, so some thought this hinted at an arid desert land beneath. Others speculated that formaldehyde filled the air, leading to the belief that Venus was not only a dead planet but a pickled one too. But come the 1950s, the true nature of Venus began to be revealed, as more accurate Earth-based observations suggested the presence of overwhelming levels of one defining gas in the Venusian atmosphere. This was not a planet shrouded in clouds of water and oxygen, nor pickled in formaldehyde. This was a planet engulfed in a blanket of carbon dioxide, and as Arrhenius had demonstrated on Earth, this almost certainly meant that whatever lay beneath the clouds, the heat would be beyond the limits of even the most resilient life forms on Earth. As the first spacecraft were being built to explore our sister world, it was becoming increasingly clear that visiting Venus would be far from easy, and she would be far from welcoming. In the early 1960s, the Soviet Union began a series of missions under the program name Venera, which attempted to explore the atmosphere and surface of Venus directly for the first time. The initial launches of the Venera program failed before they had even left Earth's orbit, but within a couple of years the program began to slowly see some success. Venera 1 was successfully launched on the 12th of February 1961. Designed as a flyby mission, it is thought to have passed within 100,000 kilometers of Venus, but a total telemetry failure on the craft meant that no data was returned to Earth. As far as we know, Venera 1 is still in orbit around the Sun to this day. Venera 3 attempted to go a step further, and was designed to enter the Venusian atmosphere to take the first direct measurements. However, on crossing the atmospheric boundary, the probe's systems failed, and no data was returned as it plummeted towards the ground. All that was left for Venera 3 was the historic position as the first human-built object to crash into another planet's surface. Despite multiple failures, the Soviets didn't give up, and in October 1967, Venera 4 entered the atmosphere of Venus and sent back data supporting the Earth-based observations, revealing for the first time that the blanket of clouds surrounding Venus was made up of primarily carbon dioxide, 90 to 95%, 3% nitrogen, and just trace amounts of oxygen and water vapor. Venera 4 confirmed beyond all doubt that this was no second Earth. As it descended through the thick clouds, the temperature rose to 262 degrees Celsius. The atmospheric pressure increased to 22 standard atmospheres, 2,200 kPa, and this was still 26 kilometers above the surface. As Venera 4 parachuted its way down to the surface, it provided data to Earth while confirming its own imminent death. This was a spacecraft that was not designed to survive the intense pressures and temperatures it was measuring, let alone the lack of the water landing it was designed for. The craft failed during the descent and was lost long before it reached the surface. Gradually, through the following missions, the Soviet scientists began to overcome each and every challenge Venus put in front of them. Venera 7 was built to survive the most violent of landings, and even though its parachute failed, it made it to the surface intact in 1970 and was able to use its damaged antennae to transmit limited temperature data for 23 minutes before it expired. Venera 9 not only made it to the surface and operated for 53 minutes in October 1975, but was also the first craft to successfully deploy its camera on the ground and transmit an image back to Earth. In the first ever picture taken from the surface of another planet, the black and white fractured image revealed a rocky, desolate landscape, with measurements confirming it to be a blistering 485 degrees Celsius, with an atmospheric pressure of 90 atm crashing down. By the time Venera 13 launched on the 30th of October 1981, the ambition of the missions and the confidence in delivering data from the surface had been radically transformed. Venera 13 functioned for 127 minutes, in recorded temperatures of 457 degrees Celsius and a pressure of 89 Earth atmospheres. The probe's cameras deployed, taking the first color image from the surface of Venus. Spring-loaded arms measured the compressibility of the soil, while a mechanical drill arm took a sample of the Venusian surface that was analyzed by an onboard spectrometer. If that wasn't enough, onboard microphones were deployed to record the vicious winds that were assumed to be whipping the surface of Venus, the first ever recording of the sound of another planet. As the Venera missions came to a close in 1983, not even the smallest doubt remained of Venus's hostility. Far from the benign water world we had once imagined, the reality was that this was not a sister we recognized. In our search of the heavens for a place like home, we'd found a toxic, fiery hellscape. Venus is an enigmatic world, almost Earth-like in size, position, and potential, and yet as far from paradise as it's possible to imagine. If Mercury's story is one of catastrophic orbital change, and Earth's of balance and stability, the story of Venus is a tragedy, a tale of subtle yet relentless decline. So why did it all go wrong for Venus? Why did a world born with such similarities to the Earth take such a different path? To answer that, we need to look beyond the tortured planet we see today and go back to a time when Venus was a young, thriving planet. 4 billion years ago, Venus was a familiar world, a world created from the same dust as the Earth, born just about the same size, and settled into an orbit that seemed just far enough away from the glare of the sun to allow a precious process to begin to take hold. In almost every conceivable way, Venus's early life mirrored that of our own world. As its newly formed crust settled and cooled from the violent heat of its birth, an atmosphere began to grow around the young planet, fed by gases bubbling up from the molten rock below its surface, as well as captured from the clouds of gas and dust it swept through on its orbit around the sun. Clinging to the young Venus, this thin layer of gas would have certainly contained nitrogen, oxygen, and carbon dioxide. But most intriguing of all, we are certain it would have also contained large amounts of water vapor. High in the Venusian atmosphere, this water vapor eventually cooled enough to change state from vapor to liquid. And with that transformation, a process began that perhaps for the first time on any of the planets would have seen the conditions become just right for droplets of liquid water to take shape and begin falling from the Venusian sky. These were the first rains of the solar system, showering down onto the dry plains of Venus. Gradually these rains would have not just fallen but flooded the surface. Rivers would have flowed, and shallow oceans taken hold of large swathes of the planet's surface. Venus, perhaps before even the Earth, became a water world, a planet with skies full of clouds and a surface full of oceans, feeding the cycle of water around this young planet. How can we be certain this blue version of Venus existed? Unlike Mars, where we can see the evidence of its watery past etched onto its surface, we have no such direct evidence of the presence of liquid water on the surface of Venus. The only physical evidence we have that suggests the planet's watery past comes from measurements taken by NASA's Pioneer Venus spacecraft back in 1978. One of its most surprising discoveries revealed an unexpected amount of deuterium, heavy water, in the atmosphere compared with hydrogen. This DH ratio is far smaller on Venus than it is on Earth, and that's interesting because when the two planets formed, the ratio would have almost certainly been the same. Because hydrogen is far more easily lost from an atmosphere than deuterium, this smaller ratio suggests that Venus has lost a lot more water than the Earth over its lifetime, the signature of a long-lost primordial ocean. As cosmochemist Larry Nittler explains, scientists believe that Venus once had a lot of water in its oceans, but lost it over time, and perhaps in oceans as recently as 1 billion years ago. The reason we can tell this is from the isotopic composition of hydrogen measured in its atmosphere by spacecraft. Now, hydrogen has 2 flavors of isotopes. Whereas most hydrogen atoms are just a single proton in the nucleus, some, a small fraction, are what we call deuterium, that have a proton and a neutron, so they weigh twice as much as the regular hydrogen. What happens when you have evaporation of water from a planet, or the atmosphere, is that the water molecules that contain hydrogen are much lighter than the water molecules that contain deuterium, so they evaporate more easily and can be lost more easily. So over time, as you evaporate water, deuterium-bearing molecules stay behind relatively to the regular ones, and you build up a deuterium to hydrogen ratio. And by back-calculating from the measured ratio today, we can figure out how much water has been lost over the billions of years of evolution, and on Venus, it's quite a lot. None of this is solid proof, but it does begin to point us in one direction, and with no further exploration of the surface, we've had to rely on an accumulation of indirect evidence to begin to paint a more detailed picture of Venus's watery past. As with almost all of our understanding of the planets, the evidence that built this picture has been accumulated through decades of exploration. Starting with the Venera mission's first touchdown on the planet, to the Pioneer Venus orbiter, and to the more recent Magellan mission, which not only relayed extraordinary radar soundings of the surface of Venus, but provided the first full topographical map of the planet collated over a period of 4 years in orbit. Combining all of the data that has been accumulated over decades of exploration has allowed us to peer deep into the planet's past, using the same tools that enable us to model the future of climate change here on Earth, to create climate models of Venus in the past, present, and future. The results of this analysis, conducted most recently by a team from NASA's Goddard Institute for Space Studies, GISS, all point to the same conclusion. In the distant past, Venus was a planet covered in shallow, primordial oceans. Some estimates suggest that this water world was far from fleeting, a blue planet just like our own that could have been sustained for around 2 billion years, and perhaps only disappeared some 700 million years ago. It's a tantalizing thought that such a similar world to our own existed for so long with liquid water on its surface. We know life took hold quickly on our own blue planet, within 500 million years of the Earth being formed. So there seems good reason to suspect that if Venus really was as wet as the models predict, it too could have sprung into life. Exactly what went on in the long-lost rivers and oceans of Venus is yet to be discovered. Hidden behind the clouds, we have not yet been back to search for any signs that life ever took hold here. Our exploratory attentions have turned to Mars, as a planet that not only has a fertile past, but is also a possible target for human colonization in the future. We know for certain that no life, at least no life we understand, could exist on Venus today, and perhaps even the evidence of any biology on that long-lost water world has long ago vanished under the oppressive heat, rampant volcanism, and extreme pressures of the planet today. The history of science is littered with crunching moments of conflict, debates, and disagreements that divided opinion in the most passionate of battles. The wonderful thing about science, however, is that the debates can be settled when facts become available. Science and conservative common sense famously clashed in 1860 when Thomas Huxley and Samuel Wilberforce fulminated over the new theory of evolution published by Darwin 7 months earlier. I imagine Wilberforce's indignant, reddening cheeks shaking with righteous outrage as he denied the repugnant possibility that his grandfather was a monkey. None of his relatives was a chimpanzee, by the way. We simply share a common ancestor with them around 6 or 7 million years ago. But the unctuous, oleaginous, and saponaceous bishop, as Disraeli once called him, was having none of it. This might be a little unfair to the great Victorian orator and Bishop of the Church of England, but in the case of evolution, he was firmly on the wrong side of reality. Few great leaps in knowledge occur without dividing opinion, and this is entirely appropriate. Extraordinary claims require extraordinary evidence, and the great scientific discoveries we are celebrating here are utterly extraordinary. The trick, as an educated citizen of the 21st century, is to realize that nature is far stranger and more wonderful than human imagination, and the only appropriate response to new discoveries is to enjoy one's inevitable discomfort, take delight in being shown to be wrong, and learn something as a result. The world of astronomy had its moment of intellectual sumo in what has become known as the Great Debate. The year was 1920, and 2 eminent astronomers found themselves stuck on a train together, traveling the 4,000 kilometers from California to Washington to discuss the greatest cosmological question of the day. The younger of the 2 men, Harlow Shapley, we have already met. He had just published his data suggesting that the Milky Way galaxy was much larger than previously suspected. This, however, was where he believed the universe stopped. Shapley was convinced our galaxy was the beginning and end of the cosmos. His travelling companion thought otherwise. Heber Curtis had been studying a misty patch of light known as the Andromeda Nebula. He was convinced that this was not part of our galaxy, but a separate island universe of billions of other stars. It's not known what they discussed on the train, but the debate itself took place at the Smithsonian Museum of Natural History throughout the day and night of the 26th of April. At stake was the scale of the universe itself, and both men knew that the question would ultimately be settled by evidence rather than debating skills. The human race had already been shunted from the centre of the universe by Copernicus, and now faced the possibility that the Milky Way galaxy itself was part of a multitude, stretching across millions of light-years of space. The question wasn't settled that evening, but the experienced Curtis, perceived as the underdog because of the magnitude of what he was suggesting, landed significant blows. Curtis observed that the Andromeda Nebula contains a number of novae, exploding stars that shine temporarily but brightly in the night sky. But he also noted that the novae in Andromeda appeared on average to be 10 times fainter than any others. Curtis asserted that Andromeda's novae appear dimmer simply because they are perhaps 500,000 light-years further away than those in the Milky Way. Andromeda is therefore another galaxy, claimed Curtis, which strongly implied that the other so-called nebulae were other galaxies too. This was the very definition of an extraordinary claim, and the extraordinary evidence came only 4 years later. In 1923, a photo of Andromeda, taken by a 33-year-old astronomer called Edwin Hubble, further fueled the great debate. It's only a photograph, but just like Anders' Earthrise, it belongs to a rarefied group of images that have transformed our perspective. Aside from their scientific merit, such images assume great cultural significance because of the ideas they generate and the philosophical and ideological challenges they pose. They also carry with them, in the shadows, personal stories. Someone would have taken a photograph of Andromeda someday and discovered what Hubble did. But Hubble took this one, and his story therefore becomes inextricably intertwined with it. Some don't like their history presented in this way, but science is richer when its stories include people as well as ideas. Curiosity is, after all, a human virtue. Hubble may never have taken the photograph had he followed through on a promise to his father to practice law. Reading jurisprudence at Queen's College, Oxford, as one of the first Rhodes Scholars, Hubble aimed to fulfill his father's wishes, but John Hubble died before Edwin finished his degree. The death of his father encouraged Edwin to ditch law and revisit his childhood passion for astronomy. He left Oxford for the University of Chicago, joined the Yerkes Observatory, and received his PhD in 1917 with a thesis entitled Photographic Investigations of Faint Nebulae. After brief service in the US Army at the end of World War I, Hubble obtained a position at the Mount Wilson Observatory. He found himself at the controls of the largest, most powerful telescope on the planet, and with the knowledge and good sense to point it at the most intriguing and controversial object in the night sky, Andromeda. Just like Curtis before him, Hubble could make out distinct features within the misty patch, but the newly commissioned 100-inch Hooker telescope allowed him to see much more detail. On the 5th of October 1923, he took a 45-minute exposure, found 3 unidentified specks that he assumed were new novae, and marked them all with an N. To confirm his findings, Hubble needed to compare this plate with previous images of Andromeda taken at Mount Wilson. The following day, he made the journey down to the basement archive where the observatory's collection of images was catalogued and stored. To Hubble's delight, 2 of the specks were indeed newly discovered novae, what we now know to be the bright nuclear flares of white dwarf stars as they accrete gas and dust from a nearby companion. But it was the 3rd speck that he found most interesting when he compared it to previous images. As Hubble scanned back through the Mount Wilson catalogue, he discovered that the star had been captured before. In some plates it appeared brighter, whereas in others it appeared dim or not present at all. Hubble immediately grasped the importance of his discovery. The 3rd speck was a Cepheid variable, the type of star Henrietta Leavitt had studied 2 decades earlier. In one of the most famous corrections in scientific history, Hubble crossed out the letter N and replaced it in red ink with the letters VAR, followed by a very understated exclamation mark. Hubble had discovered a cosmic yardstick in Andromeda, and it was a trivial matter to calculate the distance. The new star varied with a period of 31.415 days, which, following Leavitt, implied its intrinsic brightness was 7,000 times that of our Sun. And yet it appeared so dim in the night sky that it was invisible to all but the most powerful of telescopes. Hubble's initial calculations revealed that the star was over 900,000 light-years away from Earth. A staggering distance when the size of our own galaxy was estimated to be no more than 100,000 light-years across. Hubble, with the help of Leavitt's ruler, laid the great debate to rest. Andromeda, the distant patch of light in the night sky, is a galaxy, an island, according to current estimates, of 1 trillion suns. Current measurements put the giant spiral at a distance of 2.5 million light-years from the Milky Way, one of around 54 galaxies gravitationally bound together to form our galactic neighborhood known as the local group.
In the daytime, our universe stretches only as far as the horizon. The sun hides in plain sight because it's too bright for us to see it directly. Only rarely do we glimpse a watercolor moon. Unless we think hard, our intellects are confined to the surface of the Earth. After sunset, beyond cities, the universe appears, a destination for the imagination, albeit separated by a seemingly unbridgeable gulf. This may be true for the stars, but it is not so for the planets. There are times when Mars, Venus, Jupiter, and Saturn dominate the sky, bright lights that shift position nightly against the fixed stars, commanding our attention even if we aren't certain what we're looking at. The distances are still vast by terrestrial standards, but despite appearances, the gulf is certainly not unbridgeable, because we have visited all of these planets and taken our first steps into the outer reaches of the solar system beyond. And yet the wandering lights in the dark still feel detached from human affairs, and the time and effort we've spent in visiting them might seem to be an indulgence. This assumption, however, is profoundly wrong. The solar system is a system. The Sun and the 8 major planets and countless billions of minor planets, moons, asteroids, comets, and unclassified lumps of ice and rock were formed back in the mists of time, and they continue to evolve as one. We rarely notice the dynamic, interconnected nature of our system, although asteroid strikes on our planet are not such a rare occurrence. The Chelyabinsk impact in February 2013 injured 1,500 people when a 12,000-ton asteroid broke up as it entered the Earth's atmosphere at 60 times the speed of sound. And the Tunguska airburst in Siberia in 1908 flattened 800 square miles of forest in an explosion comparable to that of the most powerful hydrogen bomb ever tested. The surface of the Moon bears testament to a record of violence and destruction from the skies that the Earth has also endured, but the relentless erasure of craters by weathering, and our good fortune that no major impacts have occurred in recorded human history, are the reason for our misplaced sense of isolation from the heavens. The interdependent nature of the solar system has become more evident as we've begun to understand its history. It's tempting to imagine that the physical layout of the planets is a fossilized remnant of primordial patterns in the collapsing dust cloud around the newly ignited Sun 4.6 billion years ago. But our exploration of the planets, coupled with increasingly powerful computer simulations of the evolution of the solar system, has revealed that this is not the case. Planetary orbits are prone to instability, particularly so in the early, more chaotic years when our solar system was young. The details of precisely how the planetary orbits have shifted are still uncertain, but we now suspect that Mercury, the innermost planet, began life much further out and was deflected inwards to its present-day seared orbit. Jupiter and Saturn may have drifted inwards shortly after their formation, before reversing their course and retreating, but not before affecting the distribution of material out of which Mars and Earth would later form. Around the time that life began on Earth, Neptune and Uranus may have been flung outwards, disrupting the orbits of billions of smaller objects far from the Sun. The record of this time of unprecedented violence, known as the Late Heavy Bombardment, is written across the scarred surface of the Moon, itself most likely formed in a glancing interplanetary collision between Earth and a Mars-sized planet 4.5 billion years ago. The planets are like snowflakes. The detail of their structure, their composition, size, spin, and climate are a frozen record of their past. An understanding of the planets beyond Earth is therefore a prerequisite for understanding our home world, and that, in turn, is a prerequisite for understanding ourselves. Earth is unique in the solar system because it's a planet with a complex ecosystem. The genesis and subsequent 4 billion year evolution of life on Earth required planetary characteristics which are necessarily linked to the evolution of the system as a whole. There had to be liquid water on the surface, and much of this water was delivered after the Earth's formation by icy, water-rich asteroids and comets, possibly deflected inwards from the outer solar system by Jupiter. These rivers, seas and lakes of extraterrestrial origin had to persist for the best part of 4 billion years, which required a stable atmosphere to maintain surface temperatures and pressures within a limited range. 4 billion years is a long time, around a third of the age of the universe. The Sun has brightened by 25% since the Earth formed, which makes the stability of our environment all the more difficult to understand. In a chaotic system of planets around an evolving star, a planet with life-supporting properties and the remarkable stability enjoyed by Earth over billions of years may be extremely unusual. The study of our sister worlds, Mars and Venus, has proved instructive in understanding just how fortunate we may have been and how delicate our position today might be. 4 billion years ago, as life began on Earth, Mars was also Earth-like. It had oceans and rivers, an active geology and complex surface chemistry, the ingredients of life. One of the primary goals of the fleet of spacecraft currently in orbit around and exploring the surface of Mars is to search for evidence of past or even present life, and to understand why the red planet was transformed from a potential Eden at the dawn of the solar system to the frigid desert world we observe today. The story is complex, but one of the most important differences between the two worlds is size. Mars is just 1/10 the mass of Earth, too small to hang on to its internal heat, its protective magnetic field, and its atmosphere for much more than 1 billion years after its formation. Yet Mars formed in a similar region of the solar system to Earth and Venus, so why is it so small? The answer may lie in the fast-changing orbits of Jupiter and Saturn early in the solar system's history. These surprising findings will be explored later in this book. The history of Venus is perhaps even more puzzling, in part because of the immense difficulty of exploring the planet. Venus is often described as a vision of hell. Surface temperatures are high enough to melt lead, and the atmospheric pressure is 90 times that on Earth. Sulfuric acid raindrops fall from its clouds. And yet, long ago, Venus too may have been Earth-like. Perhaps there were once Venusians, before a runaway greenhouse effect took hold, and began destroying Venus's temperate climate about 2.5 billion years ago, although this date is highly uncertain. Taken together, the stories of the 3 large terrestrial planets are salutary. If an alien astronomer observed our solar system from afar, they would classify Mars, Earth and Venus as potentially living worlds, orbiting as they do inside the so-called habitable zone around the Sun, the region within which, if atmospheric conditions are right, liquid water can exist on the surface of the planets. All 3 worlds may once have been habitable, and all 3 worlds may once have harbored life, but now only Earth supports a complex ecosystem, let alone a civilization. Understanding why Mars and Venus diverged so significantly from Earth over the last 4 billion years will provide great insight into the fragility of worlds, and perhaps suggest whether our own good fortune is near impossible to comprehend or merely outrageous. Planets change. Ours could change at any moment. A stray comet from the frozen Kuiper belt beyond the orbit of Neptune could put an end to our story. We could also put an end to ourselves. The study of Venus might help us avoid one of the ways by which we could destroy us, because it shows us what greenhouse gases to avoid. I think one of the reasons why anthropogenic climate change is so difficult to observe and is that the atmosphere temperature should be our primary concern. That may be so, but I argue that a deeper understanding of the evolution of the planets is essential for our continued prosperity and existence on this one. The threat of catastrophic climate change is an obvious example, but there are many other reasons why knowledge is important. There is feedback in human affairs. Our collective state of mind affects the decisions we make. To confine our imaginations to the surface of the earth is to ignore both our immense good fortune and the fragility of our position. A wider knowledge of both will, I believe, help secure a safer and more prosperous future.
Earth sits a mere 150 million kilometers from the Sun. Not too hot, not too cold, with surface temperatures ranging from -88 to +58 degrees Celsius. This Goldilocks location has created a stability of climate that, despite the best efforts of ice ages and impacts, has allowed life to maintain an unbroken chain for nearly 4 billion years. And yet we know for certain that it cannot last. Our Sun, like every star in the universe, is far from static. Stars have life cycles of their own, and eventually the hydrogen fuel that powers the nuclear reactions within a star will begin to run out, and the star will enter the final phases of its lifetime. It will expand, cool, and change color to become a red giant. Small stars, like our Sun, will undergo a relatively peaceful and beautiful death, which will see it pass through a planetary nebula phase to become a white dwarf, which will cool down over time to leave a brown dwarf. Life on Earth has prospered through our Sun's middle years, but these optimum conditions are waning. At first the changes will be invisible, but 1 billion years from now they will be obvious to any life forms left on the planet. An immense sun filling the sky will warm and transform itself and the Earth that it shines upon. The sun is both the giver and the taker of life on our planet. It is one of the great paradoxes of the universe that as the life of a star like ours begins to wane, its size and luminosity will increase. A rise in luminosity of just 10% will see the average surface temperature on Earth rise to 47 degrees Celsius instead of the 15 degrees Celsius that it is today. The effect of this rise in temperature manifests in a lifting of vast amounts of water vapor from the oceans into the atmosphere, creating a greenhouse effect that could quickly and rapidly run out of control, evaporating the oceans and sending the surface temperature skyrocketing. Astrobiologist David Grinspoon explains. The greenhouse effect is the name we give to the physical process by which planets heat up through the interaction of their atmospheres and solar radiation. Basically, solar radiation comes in what we call the visible wavelengths. Primarily, they're wavelengths that we can see, and most atmospheric gases are very transparent to visible radiation. So light from the sun comes through pretty much unimpeded by an atmosphere and reaches the surface of a planet. Then the surface of the planet re-radiates that radiation in infrared, because planets are much cooler than the sun. And that means they radiate at much longer wavelengths, what we call infrared or heat radiation. That infrared radiation doesn't make it through an atmosphere so easily. Some of the atmospheric gases, the ones we call greenhouse gases, block infrared radiation, and so therefore the more of those greenhouse gases that are in a planet's atmosphere, the harder it is for that surface radiation to make it back out into space, and the more that planet will heat up. Estimates of the time scale that will see our oceans disappear vary massively, and are heavily influenced by a multitude of factors. But few are in doubt that by the time our planet reaches its 8 billionth birthday, in 3.5 billion years' time, the end will be in sight. With temperatures heading above 1,000 degrees, life will have long disappeared from a surface that is beginning to melt under the burning sun. Moving even further into the future, the outlook becomes bleaker. As the sun enters old age, it will grow into a red giant, engulfing the Earth within its expanding atmosphere. Moonless, lifeless, and perhaps reduced to its inner core,
our planet and the civilizations it once harbored will be nothing but a distant memory, etched in the atoms that made us all, as they are dispersed amongst the cosmos. For planet Earth, the clock is ticking, and time is slowly running out. But ours is far from the only world to enjoy its moment in the sun. Across the history of our solar system, stretching deep into its ancient past and reaching far into its future, we see stories of worlds in a constant battle with our ever-changing star. Close in, ancient worlds such as Mercury, which long ago lost their fight with the sun, are taunted by views of Earth and what might have been. Further out and even hotter, Venus circles, shrouded in a choking cloak of cloud, and even further beyond the Earth, Mars sits cold and barren. Beyond these planets, frozen worlds await, huddled in perpetual hibernation, anticipating the moment when the warmth of the sun reaches out far enough, with sufficient heat, to trigger a first spring. On that day, mountains of ice will melt, rivers of water will flow, and where there was once only bleakness, in the distant future on planets once frozen and lifeless, we might find a place that looks very much like home. The story of our solar system is not as we once thought it, eternal and unchanging. Instead, it is a place of endless transformation. It is a narrative that repeats itself with a predictable rhythm. As one world passes, another comes into the light. Only one planet has maintained stability for almost the entire life of the solar system. The Earth has remained habitable for at least 4 billion years, while change has played out all around it. What makes the Earth so lucky compared to all of its terrestrial siblings? To answer that question, we need to look not just at our planet, but at the whole of the solar system, going right back to the very beginning. For the first few million years after its birth, there were no terrestrial worlds to see the sun rise, and there were no days, no nights, no circular tracks around it. Instead, surrounding our infant star was a vast cloud of dust and gas. A tiny fraction of the material left over from the sun's formation, this swirling cloud would one day coalesce to form the various planets of the solar system, and many other smaller bodies. But at this time, 4.7 billion years ago, there was nothing but tiny specks of dust reflecting back the light of our slowly growing star. Only time, vast amounts of empty time, would allow enough of this gas and dust to catch and cluster, randomly forming the smallest of seeds. Most of these seeds would hardly get the chance to grow at all, smashed apart and returned to the immense swirl of dust from whence they arose. Just a few would grow big enough and survive long enough to capture and condense more of the cloud, slowly increasing their mass and density. We still do not fully understand the process by which grains of dust no thicker than a human hair can amass to become rocky objects the size of a car, and as yet no model exists to explain this part of the evolution of a planet. But what we do know is that once that disk of gas and dust becomes populated with clumps of rock that make it past the meter-sized barrier, a powerful force comes into play to propel the process forward. These newly formed planetesimals are big enough to allow the great sculpting force of gravity to draw the clumps together, growing to sizes of over a kilometer in length. Swirling around the sun, thousands upon thousands of these objects live and die, colliding and coalescing under the increasing gravitational forces of attraction, until eventually just a few emerge as planetary embryos, moon-sized bodies known as protoplanets. In the last violent stages of the process of planetary birth, these protoplanets swirl around in crowded orbits, and many are destroyed, returned to the dust of their origins. But occasionally, when a collision brings two or more of these giant objects together, the size of this mass of rock becomes big enough for gravity to pull it in from all sides, creating a sphere of newly formed rock, a new world. In that moment, a planet is born. Each of the terrestrial planets in our solar system was born this way. They are the survivors of a process that destroys far more worlds than it ever creates, and which left just 4 rocky planets remaining, starting closest to the Sun with Mercury, then Venus, Earth, and finally, farthest out, the cold and dead world of Mars. Today, these 4 worlds all look vastly different, and yet all were created the same way, made up of the same ingredients and orbiting the same star. So why have they ended up so distinct from each other, and with such starkly different environments? And what makes this place, the Earth, so unique, the only one of the rocks that has blossomed with life? To understand, we have to look deep into the past of our solar system, to explore the unique history of each of the planets by means of amazing feats of human engineering across billions of miles, and into environments of unknown and unimaginable extremes. Getting to the smallest planet in the solar system is anything but easy. Skirting past the Sun at a distance of just 46 million kilometers at the closest point in its orbit, Mercury is a planet that is not only held deep in the gravitational grip of our massive star, but is also moving at an average orbital speed of 48 kilometers per second, by far the fastest orbiting planet in the solar system, and far outpacing the Earth's more leisurely 30 kilometers per second. It needs to whip around this quickly, otherwise it would have fallen into the Sun's embrace long ago. But the combination of its speed and position make it a planet that's immensely difficult to get close to, and even harder to get into orbit around. In order to do so, you have to travel fast enough to catch up with Mercury, but not so fast that you cannot somehow slow down to prevent a headlong descent into the Sun. And that challenge has meant that until relatively recently, it was the least explored of all the terrestrial planets. For many decades, our first and only close-up glimpse of the innermost rock orbiting the Sun came from the Mariner 10 spacecraft, when on 3 separate occasions in 1974 and 1975, it briefly flew past Mercury. This was the first spacecraft to use another planet to slingshot itself into a different flight path, using a flyby of Venus to bend its trajectory, to allow it to enter an orbit that would bring it near enough to Mercury to photograph it close up. Clad in protection to ensure it could survive the intense solar radiation and immense extremes of temperature, Mariner 10 was able to send back the first detailed images of Mercury as it flew past at just over 200 miles above its surface. It passed by the same sunlit side of Mercury each time, so it was only able to map 40 to 45% of Mercury's surface. The spacecraft took over 2,800 photos, which gave us never-before-seen views of the planet's cratered, moon-like surface, a surface that we had never previously been able to fully resolve through Earth-based observation. Despite the beauty of the pictures taken, it wasn't the images from Mariner 10 that really surprised us. It was the data the probe collected relating to Mercury's geology, which pointed to a much more surprising history of the planet than had previously been imagined. Mercury, it seemed, was far from being just a scorched husk. Mariner was able to sense the remains of an atmosphere, consisting primarily of helium, as well as a magnetic field and a large iron-rich core, opening a mystery that would remain unexplored for another 30 years. As it flew past Mercury for the last time on the 16th of March 1975, the transmitters were switched off and its contact with Earth silenced. Mission completed, Mariner 10 began a lonely orbit of the Sun that, as far as we know, continues to this day. At first sight, many things about Mercury simply don't make sense. During its 88-day orbit around the Sun, it travels in a lopsided elliptical orbit, which means it can be as far away from the Sun as 70 million kilometers, but occasionally as close as 46 million kilometers. This is by far the most irregular of orbits of all the planets, but it is not the end of Mercury's oddity. Temperatures at midday can rise to 430 degrees Celsius on the surface, but at night, because it's a small planet and it has no atmosphere, temperatures fall to minus 170 degrees, giving it the greatest temperature swing of any known body in the solar system. Its rotation is also unusual, gravitationally locked to the Sun in what is known as a 3-to-2 spin-orbital resonance. This means the planet spins precisely 3 times on its axis for every 2 orbits, which in turn means that its day is twice as long as its year. In effect, you could be travelling over its surface at walking pace and keep the Sun at the same point in the sky as you strolled through eternal twilight. As planetary scientist Nancy Chabot explains, a day on Mercury is not like a day on Earth. It has a very unusual orbit. It has to go around the Sun twice to have one complete solar day on the planet, where the Sun goes from directly overhead to directly overhead, and this actually takes 176 Earth days. Because of the planet's orbit, there are places on the Mercurian surface where a hypothetical observer would be able to see the 2.5 times larger in the sky Sun appear to rise and set twice during one Mercurian day. It rises, then arcs across the sky, stops, moves back towards the rising horizon, stops again, and finally restarts its journey towards the setting horizon. Most of Mercury's anomalies can be explained by the orbital mechanics of its journey around the Sun, except, that is, for the odd elliptical orbit that takes it on such an oval-shaped, elongated course. This irregularity has puzzled astronomers for centuries, and hints at an ancient planet that was very different from the Mercury we see today. To truly begin to understand Mercury's history, we had to wait nearly 40 years before we could return to her. On the 18th of March 2011, NASA's Messenger spacecraft became the first to enter Mercury's orbit. And over the next 4 years, it succeeded in not only photographing 100% of the planet's surface, but also collecting extensive data on its geology. But before any of this could happen, Messenger had to take perhaps the most circuitous route in the history of our exploration of the solar system. Just passing close to Mercury to take a few snaps, as Mariner 10 did, is hard enough. But actually entering into its orbit was thought to be either too difficult to achieve or too costly to execute, as cosmochemist on the Messenger mission Larry Nittler explained. There are 2 major challenges to getting a spacecraft into orbit around Mercury: gravity and money. When you go from Earth to Mercury, you're falling into the gravitational well of the Sun, which makes you accelerate faster and faster as you get closer. And if you were to go straight from Earth to Mercury, this means that you would basically just zip right by the planet, or you would need to bring an incredible amount of fuel to put the brakes on, more than you could actually afford. A number of missions never made it further than pencil and paper, while others floundered and failed at the proposal stage. It was only when Chen Wan-yen, a NASA engineer from the Jet Propulsion Laboratory, JPL, provided a trajectory that could not only get a craft into orbit, but could do it at an estimated bargain bucket cost of $280 million, that the Messenger mission could really begin to take flight. Taking off from Cape Canaveral on the 3rd of August 2004, Messenger began a 6-year, 7-month, 16-day journey to Mercury that would take it on a 7.9 billion kilometre trajectory before it entered into orbit around the smallest of all the planets. To arrive at Mercury with the right speed and on the right course would require a complex route that would entail a number of gravity-assist maneuvers around the Earth, Venus, and Mercury itself to reduce the speed of the craft relative to Mercury. So, combined with the brief firing of its large rocket engine to finally insert it into orbit, this mission profile allowed Messenger to complete its voyage without the need to carry the vast reserves of fuel required to slow its passage through the firing of rockets. This design made the craft lighter and cheaper, but ultimately much slower. Almost 7 years was a long time to wait for the team patiently charting its progress across the stars. Larry Nittler described Messenger's course as sneaking up on Mercury by taking a 7-year journey, flying around the Sun many times, doing multiple flybys around Mercury and Venus, and each time transferring some of the craft's speed and energy to the planet, so it could slow down, so that when we finally got to Mercury after 7 years, we were able to fire our engine just a little bit to slow down even more and get captured by the weak gravitational field of the planet. Appropriately, when Messenger finally entered into Mercury's orbit at 0045 UTC on the 18th of March 2011, the path it settled into was highly elliptical. This orbit took it on a 12-hourly cycle from 200 kilometers above the planet's surface to 10,000 kilometers away from it. It may seem like an odd orbit for a craft with the singular aim of getting as close to Mercury as possible, but this was an essential part of the design of the mission, vital to protect Messenger from the fierce heat radiated by the scorching hot surface of Mercury. The sunlight reflected from the surface is so powerful, it would have literally melted the solder holding the spacecraft together if it wasn't given time to cool down between its closest approaches to the planet. Protected by an enormous ceramic solar shield and its eccentric orbit, Messenger could begin its work. For 2 years, the spacecraft mapped pretty much every bit of the surface of Mercury, and the images beamed back to Earth revealed a planet that's been in the firing line for billions of years. Too small to hold on to an atmosphere that might protect it from meteorites, and lacking any processes to recycle old terrain, Mercury's ancient surface is the most cratered place in the solar system.
1968 was a difficult year on planet Earth. The Vietnam War, the bloodiest of Cold War proxy tussles, was at its height, ultimately claiming over 3 million lives. Martin Luther King Jr. was assassinated in Memphis, prompting presidential hopeful Bobby Kennedy to ask the people of the United States to tame the savageness of man and make gentle the life of this world. Kennedy himself was assassinated before the year was out. Elsewhere, Russian tanks rolled into Prague, and France teetered on the edge of revolution. As I approached my first Christmas, my parents could have been forgiven for wondering what kind of world their son would inhabit in 1969. And then, as Christmas Eve drifted into Christmas morning, an unexpected snowfall decorated Oakbank Avenue, and Borman, Lovell and Anders, 400,000 kilometers away, saved 1968. Apollo 8 was, in the eyes of many, the moon mission that had the most profound historical impact. It was a terrific, noble risk, a magnificent roll of the dice, a distillation of all that is great about exploration, a tribute to the sheer balls of the astronauts and engineers who decided that, come what may, they would honor President Kennedy's pledge to send a giant rocket more than 300 feet tall, the length of this football field, made of new metal alloys, some of which have not been invented, capable of standing heat and stresses several times more than have ever been experienced, fitted together with a precision better than the finest watch, carrying all the equipment needed for propulsion, guidance, control, communications, food, and survival on an untried mission to an unknown celestial body, and then return it safely to Earth, re-entering the atmosphere at speeds of over 40,000 kilometers per hour, causing heat about half that of the temperature of the sun, almost as hot as it is here today, and do all this, and do it right, and do it first, before this decade is out. If I heard that from a leader today, I'd be first on the rocket. Instead, I have to listen to vacuous diatribes about fairness, hard-working families, and how we're all in it together. Sod that, I want to go to Mars. To set Apollo 8 in context, Apollo 7, the first manned test flight of the Apollo program, was flown by Schirra, Isola and Cunningham in October 1968. Apollo 8 was supposed to be a December test flight for the lunar lander, conducted in the familiar surroundings of Earth orbit, but delivery delays meant that it was not ready for flight, and the aim of meeting Kennedy's deadline looked to be dead. But this wasn't the 21st century, it was the 1960s, and NASA was run by engineers. The program manager was George Low, an Army veteran and an aeronautical engineer who knew the spacecraft inside out and had the strength of character to make decisions. Why not send Apollo 8 directly to the Moon without the lunar lander, proposed Low, allowing Apollo 9 to test fly the LEM, Lunar Excursion Module, in Earth orbit in early 1969 when it became available, and pave the way for a landing before the decade was out. Virtually every engineer at NASA is said to have agreed, and so it was that only the second manned flight of the Apollo spacecraft lifted off from Kennedy on the 21st of December, 10 short weeks after Apollo 7, bound for the Moon. The crew later said that they estimated their chance of succeeding to be 50-50. Precisely 69 hours, 8 minutes and 16 seconds after launch, the command module's engine fired to slow the spacecraft down and allow it to be captured by the Moon's gravity, putting the 3 astronauts into lunar orbit. Newton's almost 300-year-old equations were used to calculate the trajectory. This was a spectacular, practically unbelievable engineering triumph. Less than a decade after Yuri Gagarin became the first human to orbit the Earth, 3 astronauts traveled all the way to the Moon. But the mission's powerful and enduring cultural legacy rests largely on 2 very human actions by the crew. One was the famous and moving Christmas broadcast, the most watched television event in history at that time, when distant explorers read the first lines from the book of Genesis. "We are now approaching lunar sunrise, and for all the people back on Earth, the crew of Apollo 8 has a message that we would like to send to you," began Anders. "In the beginning, God created the heaven and the earth was without form and void, and darkness was upon the face of the deep." Borman concluded with a sentence clearly spoken by a lonely man 400,000 kilometers from home. "And from the crew of Apollo 8, we close with good night, good luck, a Merry Christmas, and God bless all of you on the good Earth." The mission's most potent legacy, however, is NASA image AS8142383, snapped by Bill Anders on a Hasselblad 500 EL at f11 and a shutter speed of 1/250th of a second on Kodak Ektachrome film. It was, in other words, a very bright photograph. The image is better known as Earthrise. When viewed with the lunar surface at the bottom, Earth is tilted on its side with the South Pole to the left and the equator running top to bottom. Little landmass can be seen through the swirling clouds, but the bright sands of the Namib and Saharan deserts stand out salmon pink against the blackness beyond. Just 368 years and 10 months after a man was burned at the stake for dreaming of worlds without end, here is Earth, a fragile crescent suspended over an alien landscape, the negative of a waxing moon in the friendly skies of Earth. This is an unfamiliar planetary Earth, no longer central, just another world. When Kennedy spoke of Apollo as a journey to an unknown celestial body, he meant the Moon. But we discovered Earth, and in the words of T.S. Eliot, came to know the place for the first time.
Today, Venus has the slowest rotation of any planet in the solar system, taking 243 Earth days to complete one rotation on its axis. This period is known as the sidereal day, which is different to a solar day, the time it takes for the Sun to return to the same point in the sky. On Earth, the sidereal day at 23 hours 56 minutes and 4.1 seconds is very close to the solar day, which lasts pretty much exactly 24 hours. But on Venus, the difference between these two periods is much greater. Even though the planet takes 243 days to rotate on its axis when combined with its orbit, a solar day on Venus lasts for 116.75 Earth days. It means every day on Venus lasts almost 4 months on Earth. And not only that, but Venus also rotates from east to west, one of only 2 planets to do so, along with Uranus. So across this toxic world, a sunrise would last literally for days as it inches across the sky. This slow progression of the sun in the Venusian sky, due to the planet's creeping rotation, has raised many questions about how in the past the planet would have been heated, and how the climate would have been affected by such a different rotation compared with the Earth's. Today, the climate of Venus is what is known as isothermal. There is a constant temperature between the day and night sides, and between the equator and the poles. This is because the thick atmosphere literally acts like a blanket, dissipating the heat of the sun so that the only real variation in temperature on the Venusian surface occurs due to differences in altitude. In its past, however, this may have been very different. With a more Earth-like atmosphere, so the sun would have been beating down on the planet's surface for days on end. To make things even more complex, we know the spin of a planet is intimately linked to its climate, and we've got strong evidence to suggest that how fast a planet spins is directly related to its chance of habitability. Until very recently, it was assumed that the slow rotation of Venus must have been caused by the presence of a thick atmosphere early on in its history that in effect acted as a brake on the planet's spin. However, recent studies now suggest that the planet could have had a thin atmosphere like that of modern Earth, and still have ended up with its slow rotation. Gradually, as we start to build a picture of ancient Venus, we begin to see beyond the cloud cover of today, through to an ancient planet with an Earth-like atmosphere, and a day lasting over 200 Earth days, as the sun beat down on the ocean-covered surface. To make sense of the climate of this Earth-like Venus, the team at the Goddard Institute needed to make another tweak, or postulation to be more precise, to the model. With the sun hitting the one side of the surface for so much longer than on the Earth, the evaporation rate of the oceans would be far greater and potentially incompatible with the water world we suspect existed. But by simply adjusting the amount of dry land on the surface of Venus, especially in the tropics, the effect is dramatic. With a higher percentage of land, the models suggest that even the slow rotation would not dry out the planet, and it could have held on to enough water to be ripe for supporting the emergence of life. By combining all of this data, the GIST team have painted our most up-to-date picture of early Venus, and it's a beguiling image. Within the infant solar system, it is a planet the size of Earth with similar atmosphere to the one we see today. On Venus, days lasted for months as the sun arced slowly across the sky from west to east, rising and setting over a vast, shallow ocean. Finally, the data from radar measurements taken by NASA's Magellan mission in the 1990s was used to paint the last brushstrokes of this long-lost world. Filling in the lowlands with water, the topography of this ancient world emerges, with the highlands exposed as the Venusian continents. It all points to the possibility that Venus could have been the first habitable world in our solar system. So what changed? To find out, we need to look not just at the planet in isolation, but also at the star around which it orbits. No planet lives out its life in isolation. Venus, like all the planets, is not just part of a configuration of planets and moons, asteroids and comets, but is also part of a solar system, a system that is driven more than anything else by the star at its center. Today, the sun burns bright in our skies, bathing our planet in just enough starlight to keep the oceans from freezing, but not too much to boil them away. Earth lies in the sweet spot we call the Goldilocks zone, but as we have already seen in this chapter, nothing in the solar system is forever, and what we see today is not what we will see tomorrow, nor what we would have seen yesterday. As our sun gets older, it's gradually burning hotter and hotter. This is because as it ages, the process of nuclear fusion, the fusion of hydrogen into mainly helium, gradually leads to an increase in the amount of helium in its core. This rise in helium causes the sun's core to contract, which in turn allows the whole star to shrink in on itself, creating an increased pressure that results in a rise in the rate of fusion, and so the energy output of the sun goes up. If tomorrow the sun is burning hotter than today, it of course makes sense that in the early days of the solar system our sun burned far less brightly. It's a life cycle that is common to all main sequence stars, the category of star that includes our sun. And as the most common type of star in the universe, we've been able to study this life cycle in intimate detail, allowing us to make immensely detailed predictions about the characteristics of our sun in the past and in the future. Winding back the clock, the current consensus among astronomers is that 4 billion years ago the faint young sun was at least 30% dimmer than it is today. This cooler sun would have undoubtedly had a big impact on all of the terrestrial planets. Earth would have been much colder, and as it was receiving far less solar energy, it remains something of a mystery as to why our planet wasn't frozen solid. Instead, at this time on Earth, first life was just beginning, in the liquid water that we are pretty certain covered its surface. At the same time, 3.5 to 4 billion years ago, the young sun would have bathed Venus in a warmer glow. This ocean world found itself in its very own sweet spot, a world held in a delicate balance. With the sun weakened and restrained, the Earth-like atmosphere of Venus could act as a gentle blanket, keeping the surface temperate and covered in an abundance of liquid water. But even with this additional solar energy, we think Venus would still have been much cooler than the Earth is today. In fact, we believe temperatures at that time would have been like a pleasant spring day here on Earth. It wasn't to last. Slowly the young sun grew brighter, its increased energy output causing temperatures to gradually rise, which in turn began to lift more and more water vapor into the air, thickening the atmosphere and sealing the planet's fate. Although the oceans of Venus may have persisted for billions of years, as the surface warmed and the atmosphere thickened, the destiny of this planet was already set, driven by an unstoppable process we have recently become very familiar with here on Earth. The greenhouse effect is a process that has the power both to protect and to destroy a planet. But despite this power, it actually boils down to some pretty simple physics. It's all about how sunlight, solar radiation, interacts with the constituent parts of an atmosphere. In the case of the Earth, as solar radiation hits our atmosphere, some of it is reflected straight back out into space, some is absorbed by the atmosphere and clouds, but most of the sunlight, about 48%, passes straight through the atmosphere and is absorbed by the Earth's surface, where it is heated up. The reason so much solar radiation makes it to the surface is because the gases in our atmosphere, like water vapor and carbon dioxide, are transparent to light in the visible spectrum. When you think about it, that's pretty obvious, because there's a source of visible light in the sky, the sun, and we can all see it. But it's a different story when that sunlight heats the surface of the Earth and re-radiates back out, not as visible light, but as the longer wave infrared light, thermal radiation. We can't see this light, but as it radiates back out from the Earth's surface, carbon dioxide and water vapor absorb the infrared, trapping that energy, and so the planet maintains a higher temperature that is intimately linked to the constituent parts of the atmosphere. The higher its level of gases like water vapor, carbon dioxide, methane, and ozone, the greater the greenhouse effect and the bigger the uplift in temperature. Despite the very real threat that this now poses to the future of our planet, the greenhouse effect on its own is not necessarily a bad thing. The Earth would be at an average temperature of around -18 degrees Celsius without it. But as we are currently witnessing here on Earth, shift the balance of those gases, and things can change very quickly. At some point in Venus's past, the levels of water vapor lifted into the atmosphere by the warming sun pushed the greenhouse effect to become precariously more intense. With less and less of the sun's energy escaping, the ambient temperatures began to rise exponentially, until the day came when the last raindrops fell onto the surface of the planet, the heat evaporating the rains long before they could reach the ground. Venus had reached a tipping point. With the increasing temperatures feeding more and more water vapor into the atmosphere, a runaway greenhouse effect took hold, driving away the oceans. This led to the surface of the planet getting so hot that carbon trapped in rocks was released into the atmosphere, mixing with oxygen to form increasing amounts of another greenhouse gas, carbon dioxide. With no water left on the surface and no other means to remove it, carbon dioxide built up in the atmosphere, setting the planet on a course that would result in the scorched body that we see today. And so Venus's moment in the sun came to an end. Earthlings take note. When it comes to the greenhouse effect, there is a precariously thin line between keeping a planet warm and frying it. Of the 4 rocky worlds, only one has managed to navigate through the instability and constant change of our solar system over the last 4 billion years and maintain the characteristics needed to support life. Mercury lost its fight early as it was flung inwards towards the sun. Venus flourished at first before slowly coming to the boil, and Mars, the runt of the litter, became a frozen wasteland long ago. Only Earth, uniquely among the planets, has persisted with an adequate stability over the last 4 billion years to allow liquid water to remain on its surface and an atmosphere just thick enough to keep its climate calm, not too hot and not too cold. Events have rocked us, and extremes of temperature have waxed and waned, but never outside of the parameters needed to harbour life. In a chaotic solar system filled with planetary might-have-beens, Earth is a shining example of stability, and the evidence for this is to be found in every nook and cranny of the planet. Today, Earth is dominated by life. The land and seas are teeming with millions upon millions of species, with thousands of new life forms discovered each year. Somehow, even when disaster threatened, the Earth has remained a living world. While endless species have come and gone, life has always persisted. It's woven into the fabric of the planet, an integral part of every continent and every ocean. Life plays a crucial role in maintaining the balance of the atmosphere that keeps our planet temperate. But we know for certain it cannot last. The Kamchatka Peninsula in eastern Siberia is one of the most inhospitable places on Earth. A volcanic wasteland, peppered with thousands of hot springs, it's here that we find some of the toughest living things. Extremophiles survive here that are able to withstand temperatures and pH levels higher than any other land-based life forms we have ever discovered. Kamchatka is part of the Pacific Ring of Fire, and despite its remoteness, biologists have long been enticed here to explore its toxic, bubbling cauldrons for signs of life. Complex life, animals and plants, struggle to survive in temperatures above 50 degrees Celsius, so searching for life here is all about searching for single-celled life forms, bacteria and archaea, ancient microorganisms, that are somehow able to endure in this hostile environment. Life forms like Acidilobus aceticus, an archaea that can be found in a hot spring where the water is so acidic it reaches a pH of 2, and where temperatures rise to 92 degrees Celsius. In other parts of the hydrothermal field, bacteria like Desulforella acetivorans have been discovered, which happily live in pools that are touching 60 degrees Celsius, but it's these that are the real hotheads. In one of the biggest and hottest pools investigated by scientists, a large number of microbes have been found living in temperatures approaching 97 degrees, making it one of, if not the, hottest environment ever studied for signs of life on land. But to find the greatest hotheads on planet Earth, you need to look not on land, but deep beneath the sea. In the furthest depths of the Atlantic, around the black smoker hydrothermal vents blurting out of the ocean floor, we found strains of archaea that can survive temperatures of 122 degrees Celsius, and perhaps even higher. These rare life forms live at the very edges of biology, Unique adaptations to their cellular chemistry enable the proteins and nucleic acids that create the structure of the microorganism to function, while the membranes that are protecting the cells utilize different fatty acids and lipids to keep the cells stable at the higher temperatures. Perhaps there are even tougher life forms that we are yet to discover, but the thermophilic microorganisms that we have so far identified and investigated in places like Kamchatka all point to the fact that life has its limits. Evolution by natural selection can only adapt so much, and even though it's impossible to imagine what life on Earth will look like in a few 100 million or even a few billion years' time, we know that biology is constrained by thermodynamics. And so we can say with some certainty that there will come a time when the Earth is too hot for any living things to exist. Natural selection will eventually run out of options as the laws of physics outplay it, and all life will come to an end. When this will happen, no one can be certain. But as the sun ages and grows hotter, temperatures on Earth will rapidly rise. Today, the average surface temperature on the planet is 14.9 degrees Celsius. But with just a 10% rise in the sun's luminosity, the average temperature will rise to 47 degrees Celsius and climbing. The increased temperatures will raise great storms across the planet. The rains will remove carbon dioxide from the atmosphere, and it will be locked away as newly formed sedimentary rock. Trees and plants will struggle as they are robbed of the gas that sustains them, until eventually photosynthesis will cease. The lungs of our planet will fail, and the precious oxygen that green plants and algae produce will dwindle. With the primary food source gone, the food chain will collapse and the age of complex life on Earth will draw to a close. Heat-loving extremophiles may flourish for millions of years more, but eventually nuclear physics will have its way, and as average temperatures race above 100 degrees Celsius, the last pockets of life will be extinguished from the Earth. We can say with confidence this is going to happen because we can plot the future of our Sun far more precisely than the future of the Earth. Our understanding of nuclear physics allows us to predict what happens inside the cores of stars, and thus we can see the past, present, and future of stars like ours written across the night sky. The heavens are filled with shining examples of stars that give us a glimpse into the future of our Sun. Arcturus, for example, in the constellation Boötes, is one of the brightest stars in the northern hemisphere. It's around the mass of the Sun, perhaps a little bit heavier, and so in the distant past would have had remarkably similar characteristics to our own star. Today, though, Arcturus is 6 to 8 billion years old, potentially 3 billion years older than the Sun, and as it is no longer a main sequence star, it is now in the red giant phase. Its fuel exhausted, it has swollen up to 25 times its original diameter, and is around 170 times as luminous, despite the fact that as its core slowly burns out, it is cooling. To see even further into the future, we need to look towards the brightest star in the northern sky, Sirius. The dog star, as it's commonly known, is twice the mass of the Sun and still fully in the main sequence. But obscured by the glare of Sirius A is a faint companion, Sirius B. This is a star that has already burnt through its fuel, swollen into a red giant, and the outer layers have drifted off into space, leaving the fading core of the star about the size of the Earth, known as a white dwarf. These stars are just two examples amongst many that point us towards the ultimate fate of our Sun, a fate that we believe will play out over the next 5 billion years or so. Just like Arcturus, as the Sun exhausts its hydrogen fuel, its outer edge will inflate and it will enter a red giant phase. Expanding millions of kilometers out into space, it will engulf Mercury first. Venus's fate will be sealed next as the Sun expands further. Some models predict that Earth may just escape the fiery end of its neighbors, heated to 1,000 degrees Celsius, but hanging on beyond the edge of the dying star as its orbit extends out due to the lessening mass of the Sun. Dead but not destroyed, Earth and Mars will orbit as burned-out relics of their former selves. The era of the 4 rocky inner planets will be over. The billions of lives lived on the surface of one of them nothing but a distant memory. But within our solar system lies another family of rocky worlds, whose moment in the sun may be to come. Far beyond the asteroid belt, millions of miles away from the sun-drenched planets of the inner solar system, the gas giants of Jupiter and Saturn are home to another family of rocky worlds. Jupiter alone has 79 known moons orbiting it, a menagerie of satellites of multiple shapes and sizes. We've been peering at these moons since Galileo Galilei spotted 4 of them, Io, Europa, Ganymede and Callisto, known as the Galilean moons, over 400 years ago, with his telescope transforming our understanding of our place in the solar system. Today we have explored the Galilean moons not just from afar, but close up, and found them to be dynamic worlds. Io is fiercely volcanic, and Europa, the ice moon, shows tantalizing evidence on its surface pointing to a subsurface ocean sitting below its icy crust. Ganymede and Callisto make up the final 2 Galilean moons, and just like Europa, they are rocky worlds with an abundance of water ice on their surfaces, and perhaps their own oceans lurking beneath. These 3 rocky, frozen worlds are all sitting in the cold outreaches of our solar system, touched by the distant sun but barely warmed, lying dormant until perhaps one day the aging sun will reach out and turn these bodies into ocean worlds for the very first time. The next planet out, Saturn, also has its ever-growing family of moons. Amongst its collection of over 60 confirmed satellites are Titan, the only known moon with a dense atmosphere and liquid lakes on its surface, though they are primarily methane, not water, and Enceladus, a frozen ice moon just like Europa with a liquid ocean deep beneath its ice. We will come to Enceladus in detail in Chapter 4, but for now it's intriguing to note that this icy moon may be our best current candidate as a second life-sustaining world in our solar system. Until we go back and explore further, we can't be certain what lies below its surface. But the possibilities that the Cassini probe has so tantalizingly hinted at make it one of the most exciting places for us to visit within the next generation of interplanetary expeditions. All these ice worlds, sitting dormant in the frozen reaches of the solar system, offer the promise of a very different future, one in which the rocky worlds of the inner solar system have been reduced to cinders, and a new generation of worlds waits to awaken. Ice worlds will become water worlds, warmed by the expanding sun, until our dying star ultimately collapses into a white dwarf.
Outwards to the Milky Way. Newton's laws are the keys to understanding our place in our local neighborhood. Coupled with precision observations of the motion of the planets and moons, they allow the scale and geometry of the solar system to be deduced and their positions to be calculated at any point in the future. The nature and location of the stars, however, requires an entirely different approach, because at first sight they appear to be point-like and fixed. The observation that the stars don't appear to move is important if you know something about parallax, as the ancients did. Parallax is the name given to a familiar effect. Hold your finger up in front of your face and alternately close each of your eyes, keeping your finger still. Your finger appears to move relative to the more distant background, and the closer your finger is to your face, the more it appears to move. This is not an optical illusion. It's a consequence of viewing a nearby object from 2 different spatial positions, in this case the 2 slightly different positions of your eyes. We don't normally perceive this parallax effect because the brain combines the inputs from the eyes to create a single image, although the information is exploited to create our sense of depth. Aristotle used the lack of stellar parallax to argue that the Earth must be stationary at the center of the universe, because if the Earth moved, then the nearby stars would be observed to move against the background of the more distant ones. Thousands of years later, Tycho Brahe used a similar argument to refute the conclusions reached by Copernicus. Their logic was completely sound, but the conclusion is wrong because the nearby stars do move relative to the more distant background stars as the Earth orbits the Sun, and indeed as the Sun orbits the galaxy itself. You just have to look extremely carefully to see the effect. Amongst the thousands of stars visible to the naked eye, 61 Cygni is one of the faintest. It's not without interest, being a binary star system of two orange K-type dwarf stars, slightly smaller and cooler than the Sun, orbiting each other at the lethargic rate of around 700 years. Despite the pair's relative visual anonymity, however, 61 Cygni has great historical significance. The reason for this quiet fame is that this faint star system was the first to have its distance from Earth measured by parallax. Friedrich Bessel is best known to a physicist or mathematician for his work on the mathematical functions that bear his name. Pretty much any engineering or physical problem that involves a cylindrical or spherical geometry ends up with the use of Bessel functions, and in blissful ignorance, you will probably encounter some piece of technology that has relied on them in the design process at some point today. But Bessel was first and foremost an astronomer, being appointed director of the Königsberg Observatory at the age of only 25. In 1838, Bessel observed that 61 Cygni shifted its position in the sky by approximately 2/3 of an arcsecond over a period of a year as viewed from Earth. That's not very much. An arcsecond is 1/3600th of a degree. It is enough, however, to do a bit of trigonometry and calculate that 61 Cygni is 10.3 light-years away from our solar system. This compares very favourably with the modern measurement of the distance, 11.41 plus or minus 0.02 light-years. Parallax is so important in astronomy that there is a measurement system completely based on it, which allows you to do these sums in your head. Astronomers use a distance measurement known as a parsec, which stands for per arcsecond. This is the distance of a star from the Sun that has a parallax of 1 arcsecond. 1 parsec is 3.26 light-years. Bessel's measurement of the parallax of 61 Cygni was 0.314 arcseconds, and this immediately implies that it's around 10 light-years away. Even today, stellar parallax remains the most accurate way of determining the distance to nearby stars, because it is a direct measurement which uses only trigonometry and requires no assumptions or physical models. On the 19th of December 2013, the Gaia space telescope was launched on a Soyuz rocket from French Guiana. The mission will measure, by parallax, the positions and motions of 1 billion stars in our galaxy over 5 years. This data will provide an accurate and dynamic 3D map of the galaxy, which in turn will allow for an exploration of the history of the Milky Way, because Newton's laws, which govern the motions of all these stars under the gravitational pull of each other, can be run backwards as well as forwards in time. Given precise measurements of the positions and velocities of 1% of the stars in the Milky Way, it is possible to ask what the configuration of the stars looked like millions or even billions of years ago. This enables astronomers to build simulations of the evolution of our galaxy, revealing its history of collisions and mergers with other galaxies over 13 billion years, stretching back to the beginning of the universe. Newton and Bessel would have loved it. Stellar parallax, when deployed using a 21st century orbiting observatory, is a powerful technique for mapping our galaxy out to distances of many thousands of light-years. Beyond our galaxy, however, the distances are far too great to employ this direct method of distance measurement. In the mid-19th century, this might have appeared an insurmountable problem, but science doesn't proceed by measurement alone. As Newton so powerfully demonstrated, scientific progress often proceeds through the interaction between theory and observation. Newton's law of gravitation is a theory. In physics, this usually means a mathematical model that can be applied to explain or predict the behavior of some part of the natural world. How might we measure the mass of a planet? We can't weigh it directly, but given Newton's laws, we can determine the planet's mass very accurately if it has a moon. The logic is quite simple. The moon's orbit clearly has something to do with the planet's gravity, which in turn has something to do with its mass. These relationships are encoded in Newton's law, and careful observation of the moon's orbit around the planet therefore allows for the planet's mass to be determined. For the more mathematical reader, the equation is m planet plus m moon equals 4 pi squared a cubed over gp squared, where a is the time average distance between the planet and the moon, g is Newton's gravitational constant, and p is the period of the orbit. This equation is in fact Kepler's third law, discovered empirically by Kepler in 1619. Kepler's laws can be derived from Newton's law of gravitation. Under the assumption that the mass of the planet is far larger than the mass of the moon, this equation allows for the mass of the planet to be measured. This is how theoretical physics can be used to extract measurements from observation, given a mathematical model of the system. To measure the distance to objects that are too far away to use parallax, therefore, we need to find a theory or mathematical relationship that allows for a measurement of something, anything, to be related to distance. The first relationship of this type, which opened the door to all other methods of distance measurement out to the edge of the observable universe, was discovered at the end of the 19th century by an American astronomer named Henrietta Leavitt.
Mars is a mirror for our dreams and nightmares. To the naked eye, the planet exhibits a reddish hue, blood red in the imagination, god of war, star of judgment. Through a small telescope, it is the most Earth-like of planets, with cinnabar deserts and white polar ice caps. A world we could imagine visiting, perhaps even settling in. 19th century astronomers convinced themselves they saw plains and mountain ranges, and canals delivering meltwater from high latitudes to arid equatorial cities. Some thought the Martians a peaceful civilization, far in advance of our own. Others saw threat. Across the gulf of space, minds that are to our minds as ours are to those of the beasts that perish, intellects vast and cool and unsympathetic, regarded this earth with envious eyes, wrote H.G. Wells in his classic science fiction novel The War of the Worlds in 1897. The nature of Mars remained a mystery until well into the 20th century, because the planet is small and far away, and therefore difficult to view with ground-based telescopes. Even the Hubble Space Telescope, high above the distorting effects of Earth's atmosphere, produces images which would not at first sight have prevented Wells from publishing. With a little imagination, the ice caps, high clouds, and dark regions circling the deserts could be mistaken for evidence of a water cycle feeding the seasonal advance and retreat of vegetation. Photographs from the first flyby of Mars by NASA's Mariner 4 spacecraft on the 15th of July 1965 abruptly laid to rest the romantic notion of Mars as Earth's habitable twin or potential foe. These images revealed an arid surface reminiscent not of our blue planet, but of our desiccated moon. Overnight, we discovered for certain that Earth is the only planet in the solar system capable of supporting complex life. And contemporary accounts of the impact of the Mariner 4 flyby suggest that this was a powerful realization. In November 1965, the Bulletin of the Atomic Scientists carried an article entitled "The Message from Mariner 4," and the message was bleak. The shock of Mariner's photographic and radiometric reports is caused not only by their denial of the terrestrial image of Mars, but by the revelation that there is no second chance, at least not in the solar system. President Lyndon B. Johnson was reported as commenting, it may just be that life as we know it, with its humanity, is more unique than many have thought." The hesitation in the first few words is revealing. Here is Mars as a symbol of our cosmic isolation. It is as though deep, or perhaps not so deep, in the subconscious, the 1960s power brokers all the way up to the president suddenly understood that the Earth is far more fragile and precious than a dispassionate analysis of their Cold War brinkmanship might suggest. Or perhaps the perspective delivered by exploration is always shocking. Apollo 8's Earthrise, the photograph that delivered such a positive end to a troubled 1968 by setting the blue Earth against the grey moon, was 3 years away. but Red Mars provided a foretaste. In response, Carl Sagan co-authored a paper suggesting, somewhat playfully, that all was not lost. Mariner 4 took only 22 photographs with a resolution of over a kilometre, in a strip crossing the region in which the astronomer Percival Lowell had sketched canals from his observatory in Flagstaff, Arizona at the turn of the 20th century. From the warmth of the Arizona desert, Lowell wrote that Mars was chilly, but no more so than the south of England, which certainly supported a civilization of sorts. Using several thousand photographs of a similar resolution taken by meteorological satellites in Earth's orbit, Sagan and his co-authors found only a single feature that unambiguously indicated the presence of a civilization: Interstate Highway 40 in Tennessee. They concluded that Mariner 4 would not have detected human civilization had it flown by Earth. We do not expect intelligent life on Mars, but if there were intelligent life on Mars comparable to that of Earth, a photographic system considerably more sophisticated than Mariner 4 would be required to detect it. The non-existence of an extant Martian civilization was confirmed by the Mariner 9 mission in November 1971, the first spacecraft to orbit another planet. Mariner 9 achieved a photographic resolution of 100 meters per pixel, and no sign of intelligent life, past or present, was detected. The twin Viking landers in 1976 failed to detect even microbial life, although the combined results of the suite of microbiology experiments carried by the spacecraft are not considered to be unequivocal, because Martian soil chemistry is, to coin a phrase from the official NASA report, enigmatic and could conceivably have masked any biological activity. In hindsight, the fact that Mars is not teeming with life today is not so surprising. Mars orbits 50 million miles further from the Sun than Earth, and receives less than half the solar energy. It is a small world with a tenuous atmosphere that provides little insulation or greenhouse warming. NASA's Curiosity rover in the Gale crater has measured midday temperatures above 20 degrees Celsius, but in the early hours of the morning it has experienced minus 120. As Alfred Russel Wallace wrote in 1907, any attempt to transport water across the Martian surface today would be the work of madmen rather than of intelligent beings. There are no canals, no cities, and no envious eyes. The planet is a frozen, hyper-arid desert, too far from the Sun to support complex life. Yet it hasn't always been this way. Observations from our fleet of orbiting spacecraft and landers have revealed a complex and varied past. Once upon a time, the red planet was glistening blue. Streams ran down hillsides, and rivers wound their way through valleys, carved by a water cycle from land to sky and down again, from mountains and highlands to the sea. This presents a great challenge for planetary scientists. Put simply, nobody would have been surprised if Mars had always been an inert rock because it is a small planet far from its star. But the geological evidence is unequivocal. The surface tells a different story. Mars, then, remains an enigma. As a wandering red star, it stirred the imagination of the ancients. As a telescopic image, too small and shifting for visual or intellectual clarity, it became our twin. When spacecraft flew by, it shocked us into considering our cosmic isolation. The red planet was relegated in our collective consciousness to the status of just one more rock, glistening in the night. Then we landed, and discovered a world that was once habitable, and could be again. A map of Mars can be read like a history book. Unlike Earth, where constant weathering, tectonic activity and volcanism have erased the deep geological past, Mars has been relatively quiescent for most of its life. The scars of collisions from the first turbulent billion years after the formation of the solar system can still be seen from orbit. Ancient cataclysms documented below a thin film of dust. NASA's Mars Global Surveyor spacecraft spent 4.5 years mapping Mars in the late 1990s and provided detailed maps with colours corresponding to differences in altitude. Just as on Earth, there is significant variation, but the geological features on our smaller sister world are much bigger and bolder. The highest elevations on Mars are found on the Tharsis Rise, a great volcanic plateau and home to the largest volcano in the solar system, Olympus Mons. At over twice the height of Everest, Olympus Mons towers 25 kilometers above the lowlands of Amazonis Planitia to the west, and its base would fit inside France just about. Cutting a deep scar across Tharsis to the southeast of Olympus Mons is Valles Marineris, named after the Mariner 9 spacecraft that discovered it, a canyon that dwarfs anything on Earth. The Grand Canyon would fit into one of its side channels. The lowest points on Mars are found in the Hellas Impact Basin, the largest clearly visible impact crater in the solar system. From the highest points on the crater rim to the floor, Hellas is over 9 kilometers deep. It could contain Mount Everest. The atmospheric pressure at the floor is twice that at the rim, high enough for liquid water to exist on the surface, in a narrow range of temperatures. These are extreme altitude differences for a small world. Over 30 kilometers from the summit of Olympus Mons to the floor of Hellas. On much larger Earth, for comparison, there is only 20 kilometers difference between the summit of Everest and the Challenger Deep in the depths of the Mariana Trench. The most striking and ancient elevation difference on Mars is that between the northern and southern hemispheres of the planet, known as the global dichotomy. Mars is an asymmetric world. The northern hemisphere is on average 5.5 kilometers lower in altitude than the southern. There is no consensus as to how the dichotomy formed, other than that it was early in the planet's history, and before the large impacts which created the Utopia and Chryse basins around 4 billion years ago. At some later time, the northern lowlands were resurfaced by volcanic activity in a similar fashion to the smooth lunar seas, which accounts for their lack of cratering relative to the much more ancient terrain to the south. The oldest terrain on Mars is found in the Noakis Terra region of the southern highlands. It is characterized by heavy cratering reminiscent of the far side of the Moon. Even small craters in the Noakian highlands are heavily eroded, which suggests the regular, if not persistent, presence of liquid water. There are dry river valleys and deltas, and evidence of water pooling in the craters and overflowing their walls, forming interconnected networks of lakes. This is how we know Mars was once a warmer and wetter world, at least occasionally. The evidence is written across the land of Noah. In contrast, the younger terrain of Hesperia Planum displays much less evidence of regular erosion by water, but bears the scars of occasional catastrophic floods that cut deep valleys over very short periods of time, and may have formed temporary large lakes or seas. The Amazonis Planitia region shows little sign of flowing water, fewer impact craters, and less evidence of active volcanism, suggesting it was formed more recently, when Mars was significantly less geologically active. The persistence of surface features over many billions of years in the Noakian, Hesperian, and Amazonian regions has led to the historical epochs of Mars being named after the distinctive terrains that still bear the characteristic marks of the climate and geological activity that formed and sculpted them. The Noakian period was the earliest and wettest, and coincided with the origin of life on Earth around 4 billion years ago, when conditions on both worlds appear to have been very similar. The Martian atmosphere may have been denser than Earth's and dominated by carbon dioxide, but significant questions remain about how such an atmosphere could have warmed Mars sufficiently to deliver the warm, wet climate, and how that atmosphere was lost. The MAVEN spacecraft currently in orbit around Mars aims to answer this question, as we'll discuss later in this chapter. The Noakian period ended as Mars became increasingly cold and arid around 3.5 billion years ago, just as life was gaining a foothold on Earth. The Hesperian period, the time of catastrophic floods, ran from the end of the Noachian to around 3 billion years ago, when Mars entered its current frozen, arid phase, punctuated by occasional volcanic activity and the large-scale movement of ice, but with very little evidence of flowing water. The long 3 billion-year freeze from the end of the Hesperian to the present day is known as the Amazonian. This is a summary of what we know about Mars. The whys pose a significant challenge to planetary scientists. Given a warm, wet, and seemingly stable world early in its history, what triggered the loss of atmosphere and descent into modern-day aridity? What happened to the water on Mars? Was it lost to space, or does it persist today as surface ice or in subsurface rocks or reservoirs? If so, how much water is still accessible? Could we exploit the ancient reservoirs of Mars to support a human colony? And perhaps most significantly of all, did life arise on the planet during the Noachian period, coincident with the origin of life on Earth? And could that life still be present on Mars today? The current fleet of spacecraft in orbit around Mars and roving across its surface has been designed to answer these questions. Mars today is a planet buzzing with activity. Communications to Earth and the Martian Internet are managed by the Mars Reconnaissance Orbiter, MRO, an orbiting bridge between worlds. MRO carries the HiRISE instrument, a camera with resolution high enough to see basketball-sized features on the Martian surface. The Mars Color Imager Marquee camera monitors Martian weather, and the Compact Reconnaissance Imaging Spectrometer for Mars, CRISM, identifies mineral deposits, particularly those formed in the presence of surface water. Orbiting with the MRO is the Mars Atmosphere and Volatile Evolution Mission, MAVEN. This cameraless spacecraft operates between 150 kilometers and 6,000 kilometers above the Martian surface, measuring the composition of the atmosphere at different altitudes and observing how the tenuous gases are stripped from the planet by the solar wind. Mars Odyssey is the veteran of the orbiting fleet, having arrived in 2001 and still being operational in a polar orbit, searching primarily for water ice on the surface. Mars Express is a European Space Agency mission that is delivering high-resolution photographs, mineralogy data, radar investigation of the near subsurface, and atmospheric measurements, including the search for methane, a gas that on Earth is associated with biological activity. India's Mangalyaan space probe is primarily a technology demonstrator, but it carries a secondary scientific package capable of investigating atmospheric composition. The newest arrival at Mars is the joint European Space Agency Russian ExoMars Trace Gas Orbiter, which will observe seasonal changes in the Martian atmosphere and search for subsurface water deposits. The spacecraft will form the communications bridge for ESA's ExoMars rover, due to land in 2021. The two most recent explorers of Mars are the Opportunity and Curiosity rovers. The Opportunity rover landed on the Meridiani planum close to the Martian equator on the 25th of January 2004, with a planned lifetime of 90 Earth days. In a spectacular testament to the Jet Propulsion Laboratory's engineering excellence, Opportunity remained operational until a planet-wide dust storm covered its solar panels in June 2018, after over 14 years and a journey of 45 kilometers on the surface of Mars, exploring the Endurance, Victoria, and Endeavour craters. On the 13th of February 2019, Opportunity was finally declared dead. Opportunity's younger and far larger companion on Mars is Curiosity, the most massive and most capable spacecraft ever to touch down on a planet beyond Earth. The landing itself was a tour de force of engineering ingenuity and audacity. The enormity of the mission is best described through the words of Alan Chen, operations lead at NASA for the Curiosity mission, at 10:31 PDT on the 5th of August 2012, watching the landing at the Jet Propulsion Laboratory alongside the team. The engineers described it as 7 minutes of terror. 7 minutes to maneuver a spacecraft that had taken 8 years to design and build, with a program cost of more than $2.5 billion, from 13,000 miles per hour at the top of the Martian atmosphere to a soft landing on the surface of the planet. The tension reflected the high stakes. The Mars Science Laboratory mission, to give the lander and orbiter their full title, was a high-risk flagship science mission in the same category as Voyager, the Hubble Space Telescope, Viking and Cassini, and was beset by cost and schedule overruns and controversy. This is in many ways unsurprising. New technologies and ambitious scientific objectives are difficult to implement and achieve, and in part because of this deliver great rewards. In hindsight, nobody would question the value of any of these missions, which have delivered some of the greatest insights and most inspiring images in the history of exploration. Yet this never prevents bean counters and rival scientists with agendas, and more charitably, budgetary challenges of their own, whinging and even considering cancellation. This is naive. Funding for science is almost always grudging from a political class whose view of the acquisition of knowledge is utilitarian. The far deeper value of exploration as a critical part of the internal voyage of our species, bringing us into direct confrontation with the mystery of our existence, is lost on them, at least until occasional Johnsonian, President, not Alexander Boris de Pfeffel, moments. It may just be that life as we know it with its humanity is more unique than many have thought, and we must remember this. Which means that a cancellation of one project does not mean an uplift in funds for another. More likely the budget will be lost to science. At the time of writing, the same issues plague another NASA flagship mission, the James Webb Space Telescope. As Robert D. Baum wrote in an op-ed article for Space News in December 2008, at the height of the Mars Science Laboratory controversy, when implementing flagship missions, cost and schedule overruns are not uncommon, but history shows that the mission return often eclipses the expenditure. The Hubble Space Telescope experienced a development cost overrun several times its approved project budget, and was launched much later than originally planned. In hindsight, would any rational space scientist not concede that the return from Hubble was worth the investment? Given the febrile atmosphere, however, no amount of philosophy or reason would mitigate the costs of failure of the Mars Science Laboratory mission. A landing accident was both possible and unthinkable. Delivering almost a ton of fragile rover onto the surface of Mars with pinpoint accuracy is not trivial, which is perhaps why the chosen engineering solution seemed, not to put too fine a point on it, daring. Mars has a thin atmosphere, so slowing down a spacecraft when it's traveling around 10 times faster than a bullet is hard. And yet the atmosphere is thick enough to apply sufficient frictional heating to destroy a spacecraft without adequate protection, and turbulent enough to cause significant uncertainty in the landing site of an unsteered vehicle. This renders the more obvious engineering solutions redundant. You can't simply deploy a parachute and float to the surface. The 1970s Viking landers used a combination of heat shields during aerobraking, parachutes, and retro-rockets with success. But the Curiosity engineering team dismissed this tried-and-tested solution. It did not allow for high enough precision, or for the gentle landing required for the pinpoint delivery of a large rover with delicate wheels. The Viking landers had legs built like tanks. The Viking landers also carried their heavy descent rocket systems with them to the ground, which didn't matter because they stayed put. Curiosity would have had to lug all this unnecessary mass around Mars for years. The Opportunity rover, her sister ships Spirit and the earlier Mars Pathfinder, employed a combination of aerobraking, parachutes, rockets, and airbags to cushion the falling spacecraft. But these previous rovers were lightweight in comparison, at just over a fifth of the mass of the gargantuan Curiosity. A rover of this size and complexity bouncing over the surface in an airbag cocoon was not considered feasible, primarily because of the sheer mass of the airbag system needed to cushion the impact. The lightweight Opportunity rover's landing system was almost twice the mass of the rover itself. The chosen Entry, Descent and Landing Procedure, EDL, for Curiosity was described by mission lead Adam Stelzner as the result of reasoned engineering thought. A beautiful example of the truism that reasoned engineering thought and common sense, at least of the sort possessed by the average golf club bore, do not always match up. The Curiosity EDL appears to the untrained eye to be bonkers, or maybe overcomplicated, but it wasn't, and it worked. Tucked up inside a protective shell, Curiosity encountered the outer layers of the Martian atmosphere 125 kilometers above the surface and traveling at around 20,000 kilometers per hour at 10:23 p.m. Pacific Daylight Time on the 5th of August 2012. The spacecraft, at this stage cocooned inside a protective enclosure, flew entirely under the control of its onboard computers, with no input from mission control on Earth. This was the first time an autonomous guided entry system was employed for an interplanetary mission, using a combination of thrusters and the ejection of balance masses to shift the center of mass and trajectory of the spaceship and guide it with a design accuracy of around 10 kilometers towards the chosen landing site. This guided rather than ballistic trajectory allowed for a much wider choice of landing sites for Curiosity than for the previous landers, which required around 100 kilometers of flat, safe land surrounding the nominal touchdown point. But it also required the rover to fly itself. The round-trip travel time for a radio signal to Mars was over 13 minutes when Curiosity landed, making control from the Jet Propulsion Laboratory in California impossible. During the first stage of descent, a heat shield constructed from a unique material known as pica, phenolic-impregnated carbon ablator, protected Curiosity from peak temperatures of around 2,000 degrees Celsius, generated by friction in the thickening Martian atmosphere. 4 minutes after beginning the entry phase, slowed to just under 3,000 kilometers per hour, Curiosity's parachute deployed at an altitude of 11 kilometers above the surface. The supersonic parachute is a vast and complex structure, 80 suspension lines over 50 meters long, attached to a 16-meter canopy. Having slowed to a velocity of 700 kilometers per hour with the help of the parachute, the heat shield was jettisoned at an altitude of 8 kilometers, allowing the onboard radar to get a view of the ground and deliver high-precision altitude and velocity measurements. With the parachute fully unfolded in relatively dense, low-level Martian atmosphere, Curiosity drifted in the Martian sky for 80 seconds, descending ever more slowly. At an altitude of 1.8 kilometers, traveling at a sedate 280 kilometers per hour, the NASA timeline calls for a deep breath as Curiosity separated from the parachute system and dropped in freefall towards Mars. For engineers, says the NASA website, it's like jumping out of a plane for the first time. The freefall drop was designed to allow Curiosity to separate far enough from the parachute system so that it wouldn't accelerate back into it when 300 meters further down, its retro-rockets fired and the powered descent phase of the landing began. For the Viking landers, this was the final phase. But for Curiosity, after the rockets had delivered the rover to an altitude of just 20 meters with a descent velocity of less than 1 meter per second, almost a hover, the audacious final phase of the landing protocol kicked into action, the sky crane. The rover slowly departed the rocket cradle, attached by 3 nylon wires and an umbilical cord of electrical connections 7.5 meters in length. 4 of the rockets, angled away from the vertical so as not to damage the rover, continued to fire, allowing the whole delicate system to approach the surface at walking pace. At 5 meters from the surface, Curiosity unfurled its wheels, stowed for the 8-month journey from Earth. At 10:32 p.m., the rover confirmed its wheels were in contact with the Martian surface and issued one last command through the electrical umbilical up to the sky crane. I'm down, cut the cables, and fly away. after a 500 million kilometre journey, Curiosity was delivered safely to Mars just 2.4 kilometres from its nominal landing point. A triumph of engineering ingenuity and brilliance. Curiosity was sent to Mars to explore Gale Crater, a 150-kilometre wide impact crater formed during the late Noachian or early Hesperian period, when liquid water would have been present at least occasionally on the surface. In the great tradition of astronomy, the crater is named after the Australian amateur astronomer, planetary observer, comet hunter, and occasional banker, Walter Frederick Gale, who discovered a host of comets as well as a number of geological features on Mars at the turn of the 20th century, using self-built telescopes in his backyard. The primary reason for choosing Gale Crater was the unusual central structure Mount Sharp, or Aeolis Mons, which rises over 5 kilometres above the crater floor. There is still debate about precisely how Mount Sharp formed, but the layers visible from orbit along its flanks suggest that it is the weathered remains of sedimentary rocks which once filled the crater and were laid down over time after the impact. Subsequent erosion by the relentless Martian winds removed much of the surrounding rock to reveal the ancient crater floor once more, while leaving the towering central structure intact. Deep, exposed sedimentary layers are extremely enticing to geologists, because a cross-section through rock is a cross-section through time. As surface and atmospheric conditions change, different sorts of rock are laid down and chemically modified. As Curiosity ascends the slopes of Mount Sharp, it climbs forwards through Martian time, and scientists are close behind. Joy Crisp, the deputy project scientist from NASA's Jet Propulsion Laboratory, explained the choice of landing site in the weeks before launch. Mount Sharp may be one of the thickest exposed sections of layered sedimentary rocks in the solar system. The rock record preserved in those layers holds stories that are billions of years old, stories about whether, when, and for how long Mars might have been habitable. Just as the layers of exposed rock in the Grand Canyon on Earth reveal the story of our planet, the exposed sedimentary layers of Mount Sharp are a storybook that the winds of Mars have opened, ready for Curiosity to read. At the time of writing, Curiosity has travelled almost 19 kilometres from its landing site on the flat plains to the lower slopes of Mount Sharp, stopping along the way at each interesting site to characterise the geological environment. Curiosity's suite of scientific instruments is the most sophisticated ever installed on a spacecraft. The rover is a mobile geological laboratory capable of analysis of the Martian surface and the layers just beneath. NASA loves acronyms. Curiosity acquires samples using the SSS, the Surface Sampling and Science System. It is made up of 3 parts: the SASPAR, Sample Acquisition, Processing and Handling Subsystem, SAM, Sample Analysis at Mars Instrument, and CHEMIN, Chemistry and Mineralogy Instrument. The main components of SASPAR, which is mounted at the end of Curiosity's robot arm, are an integrated scoop and sample processing system, Chimera, and a drill for acquiring surface and subsurface samples. The Scoop and Sample Processing System surely has one of the most inventive of all NASA acronyms. CHIMRA, pronounced Chimera, after the multi-headed creature of Greek mythology, which stands for the Collection and Handling for In Situ Martian Rock Analysis Tool. Someone deserves an award for that. These are transferred into SAM, which includes a gas chromatograph, a mass spectrometer, and a tunable laser spectrometer, and CHEMIN, the first X-ray diffraction experiment ever flown in space, and the most sophisticated modern technique for characterizing mineral samples on Earth. The science returned from Curiosity is only just beginning, as older data are analyzed and published, and new data from its climb up the slopes of Mount Sharp and through Martian geological time continues. But current results are consistent with, and greatly enhance the detail of, our picture of a planet that was warmer and wetter when Gale formed around 3.5 billion years ago. In early October 2012, Curiosity rolled to a halt at a place the geologists christened Rock Nest and scooped up a handful of Mars. The sample of dust, dirt, and finely grained soil was fed into the SAM and heated to 835 degrees Celsius. The baking process revealed the presence of significant amounts of carbon dioxide, oxygen, and sulfur compounds. SAM's analysis also suggested the presence of carbonates, which form in the presence of water. Perhaps most surprising of all, the soil from Rock Nest didn't just provide circumstantial evidence for ancient water. Around 3% of the sample's mass was water, suspended as small ephemeral droplets of salty liquid. Curiosity is sitting on the floor of a lost lake, a body of water that filled Gale at the Noachian-Hesperian boundary. The patterns of sedimentary deposits suggest the lake rose and fell in multiple cycles over tens of millions of years. A transient landscape of ancient streams, deltas, and ponds is bounded by the border of the crater. When alighting on ancient riverbeds running down from the crater's rim, Curiosity has found sulfur, nitrogen, hydrogen, oxygen, phosphorus, and carbon, all the necessary building blocks for life. Summarizing the results in August 2017, Michael Mayer, NASA's lead scientist for the Mars exploration program, said, "A fundamental question for this mission is whether Mars could have supported a habitable environment. From what we know now, the answer is yes." In June 2018, two new discoveries strongly reinforced the idea that Mars was once a habitable world, and maybe still is. Curiosity found complex organic molecules a few centimeters below the surface, in rocks known as mudstone that form from silt deposited on lake beds. This means that all the ingredients for life were present at the time when Gale Crater was filled with water. Detected molecules include benzene, toluene, propane, and butane. Even more tantalizingly, Curiosity also observed a strong seasonal variation in methane levels in the Martian atmosphere today, reaffirming and enhancing previous observations of methane spikes from orbit. The important additional information from Curiosity was that the methane peaked repeatedly in the warm summer months and declined in the cooler winter, which is what would be expected if the methane had a biological origin. This is not irrefutable evidence of life on Mars today by any means. It's thought that geological processes may be able to account for such a seasonal variation, although if this were Earth, a biological explanation would be favored. The appropriately cautious Michael Mayer had this to say in June 2018. "Are there signs of life on Mars? We don't know. But these results tell us we are on the right track." Science is a humble and cautious pursuit, and from the time of Viking we've known that Martian soil chemistry is notoriously complex and can easily catch out the unwary scientist. So we should leave it there. Curiosity continues its journey through Martian geological history emboldened. It is certainly driving across an ancient lake bed where, for a reasonably extended period over 3 billion years ago, conditions were favorable and all the ingredients for life were present. While we shouldn't speculate or read too much into the results to date, we can let our imaginations wander for a moment to picture what Gale Crater might have been like during the late Noachian, when life was gaining a foothold on her sister world. We stand on the shores of a lake partially filling Gale, fed by runoff from snowmelt on the far northern rim. Where Mount Sharp now stands, a small island breaks the surface blue, not the mountain of today, but a small central peak left over from the impact. A place of grand beauty, where each Martian evening the pale sun sets in the west beyond the island, rays glinting dimly off the still waters, interrupted by the shadow of the peak out to the crater's edge. A sundial, marking the passing of time, on a lake populated by microbial Martians.
The Earth is replete with features named after rogues, because history is the province of the rich and powerful, and the deserving rarely become either. To find more worthy geographical nomenclature, it is necessary to look further afield, to a place that escaped the attention of the vain. The dark side of the Moon is such a place, because nobody had seen it until the Soviet spacecraft Luna 3 photographed it in 1959. It isn't dark, by the way. It permanently faces away from Earth due to an effect called tidal locking, and receives the same amount of sunlight as the familiar Earth-facing side. The first humans to see it were the crew of Apollo 8, when Bill Anders memorably described it as looking like a sand pile my kids have played in for some time. It's all beat up, no definition, just a lot of bumps and holes. Lacking the smooth lunar maria, the dark side is an expanse of craters, and many of these have been named entirely appropriately after deserving scientists. Giordano Bruno is there, of course, alongside Pasteur, Hertz, Millikan, D'Alembert, Planck, Pauli, van der Waals, Poincaré, Leibniz, van der Graaf, and Landau. Arthur Schuster, the father of the physics department at the University of Manchester, is honoured. And tucked away in the southern hemisphere, next to a plain named Apollo, is a 65-kilometre wide, partly eroded crater called Leavitt. Henrietta Swan Leavitt was one of the Harvard computers, a group of women employed to work at the Harvard College Observatory by Professor Edward Charles Pickering. By the late 19th century, Harvard had collected a large amount of data in the form of photographic plates, but the professional astronomers had neither the time nor resources to process the reams of material. Pickering's answer was to hire women as skilled and cheap analysts. Scottish astronomer Wilhelmina Fleming was his first recruit, whom he employed after proclaiming that even his maid could do a better job than the overworked males at the observatory. Fleming became a respected astronomer. She was made an honorary member of the Royal Astronomical Society in London, and amongst many important published works, discovered the Horsehead Nebula in Orion. Buoyed by this successful policy, Pickering continued to expand his computers throughout the later years of the 19th century, bringing Henrietta Leavitt into the team in 1893. Pickering assigned her to the study of stars known as variables, whose brightness changes over a period of days, weeks, or months. In 1908, Leavitt published a paper based on a series of observations of variable stars in the Small Magellanic Cloud, which we now know to be a satellite galaxy of the Milky Way. It consists of a detailed list of the positions and periods of 1,777 variable stars, and towards the end a brief but extremely important observation. It is worthy of note that in Table 6 the brighter variables have the longer periods. It is also noticeable that those having the longest periods appear to be as regular in their variations as those which pass through their changes in a day or two. This discovery immediately caught the interest of Pickering, and for good reason. If a star's intrinsic brightness is known, then it is a simple matter to calculate its distance. Put very simply, the further away an object is, the dimmer it appears. Leavitt and Pickering published a more detailed study in 1912, in which they proposed a simple mathematical relationship between the period and intrinsic brightness of 25 variable stars. This relationship is known as the period luminosity relation. All that was required to calibrate the relation was a parallax measurement of the distance to a single variable of the type observed by Leavitt. If this could be achieved, then the distance to the Small Magellanic Cloud could be obtained. In 1913, the Danish astronomer Einar Hertzsprung, in a spectacularly accurate piece of astronomical observing, managed to measure the distance by parallax to the well-known variable star Delta Cephei. Delta Cephei has a period of 5.366341 days and lies 890 light-years from Earth, according to modern measurements by the Hubble Space Telescope. Because of its historic place as the first of Leavitt's variable stars to have its distance measured, these stars are now known as Cepheid variables. Inexplicably, even though Hertzsprung managed to get the parallax measurement and the distance to Delta Cephei correct, his published paper quotes the distance to the Small Magellanic Cloud as 3,000 light-years, which is badly wrong. The modern-day measurement is 170,000 light-years. There is speculation that Hertzsprung made a simple typographical error in the paper and for some reason couldn't be bothered to correct it. In any case, the technique had been established, And 2 years later, Harlow Shapley published the first of a series of papers that refined the method and led him to the first measurement of the size and shape of the Milky Way. He concluded that the galaxy is a disk of stars around 300,000 light-years in extent, with the Sun positioned around 50,000 light-years from the center. This is roughly correct. The Milky Way is around 100,000 light-years across, and the Sun is about 25,000 light-years from the center. This was an important moment in the history of astronomy, because it was the first measurement that relegated the solar system from being the center of everything. It's true that few, if any, astronomers would have claimed otherwise by the turn of the 20th century, but science is a subject that relies on measurement rather than opinion. The journey into insignificance had begun.
The solar system is in fact a system. Although we might feel isolated on a ball of rock in the dark, that is an illusion. No planet is an island. The system evolves as one. Draw a diagram of the food chain underpinning all complex life on Earth today, and at the base is a stream of photons generated 150 million kilometers away inside the Sun. Green plants are the interface between a star and civilization. Our understanding of Mars demonstrates that a planet's relationship with the Sun is not all light and sweetness. The star can provide the energy for life, but the solar wind can also destroy life or prevent it from ever emerging through the damage it can cause to planetary atmospheres. The solar wind emerges from the Sun's atmosphere, known as the corona. The temperature at the Sun's surface is 6,000 degrees Celsius, but the temperature of the corona is over 1,000,000 degrees Celsius, heated by energy transferred from the surface by the powerful solar magnetic field, twisted and coiled by the star's rotation. At such high temperatures, atoms cannot hold together. Electrons are ripped away from atomic nuclei, and matter exists in a fourth state, not solid, liquid, or gas, but a soup of negatively charged electrons and positive ions known as a plasma. Some of these particles are moving so fast that they escape the Sun's embrace completely, streaming outwards across the solar system at velocities in excess of 800 kilometers per second. This is the solar wind. When these high-energy charged particles reach Earth, most do not smash directly into atoms at the top of our atmosphere, because we are protected by our magnetic field. They are deflected harmlessly by stretching and distorting the field out on the night side of the planet. The stretched field occasionally reconfigures, accelerating electrically charged particles back down the magnetic field lines to the Earth's poles, where they collide with atoms and molecules in the upper atmosphere, exciting them and causing them to emit light. This is the aurora, the northern and southern lights. From Earth, the aurora can be seen by those lucky enough to be far enough north or south on the right night, when the sky is clear, the Sun is active, and the interplanetary magnetic fields are favorably aligned. From the lofty vantage point of the International Space Station, the aurora reveals itself as halos dancing around the poles. It is an unforgettable sight, undoubtedly one of nature's wonders. But as is often the case in science, and in life for that matter, the experience is greatly enhanced by knowledge. The lights, dancing faster than the eye can see, or perhaps the brain can comprehend, are a direct result of the structure of atoms. Electrons shifting between allowed energy levels, determined by the number of protons in the atomic nucleus that holds them captive. High-altitude oxygen glows red. An atom is struck by a charged particle accelerated down the Earth's magnetic field lines towards the pole. The interaction shifts an electron into a long-lived, excited configuration. If the atom is not involved in a collision in the thin air for around 100 seconds, an eternity in atomic time, the electron will shift down closer to the nucleus, and a red photon will be emitted. At lower altitudes, a different reconfiguration inside oxygen atoms causes the emission of green photons. This time the atom must avoid collision for around a second, still an atomic eternity in the denser air. Excited nitrogen molecules add a deep red or pink to the lower edges of the towering curtains of light during intense displays. This is quantum mechanics written across the sky, the structure of atoms revealed. To calculate the colors, physicists treat the electrons as waves trapped inside a deep well created by the electric charge of the protons. Particles imagined not as tiny flecks of matter, but as fields that can span great volumes of space. The energy to drive the display comes from nuclear fusion reactions inside the Sun, a factory 1,000,000 times the volume of Earth, converting hydrogen into helium at a rate of 600 million tons per second. The weak nuclear force acts slowly and grudgingly to convert protons into neutrons in the core. Nuclear alchemy that results in the creation of neutrinos, which stream across 150 million kilometers at close to the speed of light before passing unhindered through the entire planet on their journey to infinity. Thus, 60 billion per square centimeter stream through your head every second without even a nudge, because your head is almost entirely empty space, and neutrinos hardly ever come close enough to interact with your sparsely distributed molecules. It might happen once in your lifetime. The nuclear forces at work inside the Sun also assembled the heavy elements that make up your body inside old stars long ago from hydrogen and helium forged in the first few seconds after the Big Bang: carbon, oxygen, nitrogen, sulfur, phosphorus, and iron. Gravity assembled the stars by forcing the collapse of primordial interstellar clouds, causing them to heat up in their centers and triggering the nuclear reactions that release the energy to halt the collapse for a few billion years, long enough for life to emerge in the gradient between the nuclear furnaces and the chill of the expanding universe. All of these thoughts are ignited in the imagination by the auroral display. Our experience is enhanced by knowledge. A central component of the web of physical processes that make the aurora shine is our magnetic field, which deflects the solar wind harmlessly past our planet and allows it to return in a much subdued form to the poles. Without this, the processes that Maven observes stripping the atmosphere of Mars would happen on Earth. The magnetic field is one of the most important differences between our worlds. Earth's magnetic field is generated by what is known as a dynamo, which is easy to explain in broad brush terms, but extremely complex and not fully understood in detail. The basic physics is simple. Earth's core is composed largely of molten iron, which is an electrically conducting fluid. Plumes of molten liquid rise and cool as they approach the mantle, and the Earth's rotation swings these columns around into circulating, rising and falling flows. This circulating flow acts as a dynamo and generates a magnetic field. The stability of the dynamo is related to the temperature gradient between the core and the mantle, the radius of the core itself, the rate of rotation of the planet, and numerous other subtleties. The rate of heat flow through the mantle is affected by geological processes including plate tectonics and volcanism. The precise nature of the flows depends on the constituents of the core other than iron, for example the sulfur content and distribution, and so on. It's fiendishly complicated, and because of this complexity, our planetary magnetic field gives every indication of being a delicate phenomenon. It was certainly delicate on Mars. We suspect there was once a Martian dynamo, because the Martian crust is still partially magnetized in places, particularly in the ancient southern highlands, suggesting that these rocks cooled in the presence of a global magnetic field. The Hellas impact basin, which formed around 4 billion years ago, shows no sign of magnetization, suggesting the dynamo shut down before this impact. Impact basins that formed over 4.05 billion years ago do show signs of magnetization. The Martian meteorite ALH 84001, dated at 4.1 billion years old, also shows clear signs of having formed in the presence of a magnetic field. These observations lead to the current baseline view that Mars had a magnetic field not unlike Earth's, which seems to have switched off just before the Hellas impact. From that point onwards, the atmosphere was exposed to the full force of the solar wind and the MAVEN results tell us that this was likely the key driver for the loss of the Martian atmosphere. It would be tempting, but wrong, to suggest that the loss of the magnetic field was the trigger that drove the change from the Noachian to the Hesperian. The timescales probably don't match, and in any case the loss of the magnetic field wouldn't have led to an immediate loss of the atmosphere. Sputtering is a gradual process which still continues today. There have been speculative attempts to link the switch-off of the dynamo to the Hellas impact, or multiple impacts around the time of the late heavy bombardment. The idea is that the heating of the mantle can disrupt the heat flow out from the core, in turn disrupting the smooth convective flows. At the time of writing, the sequence of events is reasonably well established, but there is no consensus on how or even if they are causally linked. A complicating factor is the relative instability of the Martian orbit. The planet's obliquity, the tilt of its spin axis, varies by tens of degrees over timescales of a few 100,000 years, in response to gravitational interactions with the other planets and the Sun. In comparison, Earth's axis drifts gently between 22.1 and 24.5 degrees in a 41,000-year cycle, and even this small change is responsible in part for Earth's periodic ice ages. Imagine what happened to the Martian climate when the polar regions with their reservoirs of carbon dioxide and water ice tilted towards the Sun by 20 or 30 degrees. The stability of Earth's spin axis is maintained by the damping effect of the Moon, which is unusually large relative to our planet. The Earth-Moon system might almost be regarded as a double planet system. The more we learn about other worlds, the more fortunate our presence on Earth appears. Despite all this marvelous complexity, the simple thought with which we began this chapter probably captures the spirit of why Mars died. The red planet is simply too small. It lost its heat more quickly than Earth from its smaller core and through its thinner mantle and crust. Geological activity fell markedly after reaching a peak during the Hesperian, and the planet faded. The atmosphere, held more tenuously than Earth's because of the planet's lower mass and gravitational pull, and unprotected by a magnetic shield, was stripped away by the solar wind, and the surface approached temperatures more in tune with an orbit far from the Sun. Mars's fate was sealed during its formation 4.5 billion years ago. It is too small and too far away from the Sun to have remained a vibrant, active world. Today, faint auroras still dance in the Martian skies, as photographed by ESA's Mars Express spacecraft. Blue ghosts of a Martian past generated by localized magnetic hotspots scattered across the planet, and the last traces of carbon dioxide in the atmosphere, energized by the relentless solar winds. Despite its 3 billion-year quiescence, Mars had a bright and active adolescence that echoes down the ages and may yet have profound consequences for us, confined for now on her planetary neighbor a solar system's lifetime away. There may have been, and may still be, life on Mars. We're looking hard, and the next generation of spacecraft may find evidence for Martians within the next decade. The discovery of a second Genesis would have important philosophical, scientific, and cultural consequences. It would mean that, given the right conditions, liquid water, active geology, and a sprinkling of organics, we would know that life emerges with a sense of inevitability through the entirely predictable action of the laws of nature. It would be confirmation that we, along with every living thing on our planet today, are an outgrowth of the planet, an extension of geology. We would understand that whatever magic we perceive in the depths of our souls has its origins in the interface between water and heat and minerals and gas. We are bubbling chemistry that thinks. If it happened on 2 neighboring planets in a single solar system, it happened everywhere. We would understand that we are part of a grand living universe. We are not God's children, but we are also not alone. Of even greater importance, I think, is the role that Mars must play in our future. Mars is rich in potential. It has reservoirs of frozen or even liquid water below the surface, and a great wealth of mineral resources, all the things that are necessary to support a civilization. Because of its history, this is a world in waiting, a treasure island in stasis. I think in my lifetime there will be Martians. The Martians will be us. We will go to Mars and make it our home, partly because there is nowhere else to go. Mars is the only planet beyond Earth on which we could even contemplate a landing in the near future. The message from Mariner 4 was not interpreted correctly. There is a second chance for us on Mars, when we feel ready to take it. I don't mean that we will leave Earth en masse for the new world. This is manifest nonsense. The Earth is by far and away the best planet we know of anywhere in the universe. We were born of it, and sculpted precisely and perfectly to flourish on it through the action of evolution by natural selection. Yet it is possible now to build a colony on Mars. I imagine a group of pioneers on the new world, living off the land and constructing the infrastructure necessary for tens, hundreds, and ultimately thousands of individuals to follow in their footsteps across the solar system and extend the human frontier for the first time in many centuries. Frontiers are important. The intellectual frontier is the domain of science, and where would we be without the pioneers who felt drawn there? The physical frontier is the domain of adventurers, engineers, and dreamers. And dreamers need somewhere to go. In Werner Herzog's film Encounters at the End of the World, a man named William Gierser describes the sort of person who gravitates to Antarctica, the last of Earth's frontiers. I like to say, if you take everybody who's not tied down, they all sort of fall down to the bottom of the planet. So that's how we got here, you know? We're all at loose ends, and here we are together. I remember when I first got down here, I sort of enjoyed the sensation of recognizing people with my travel markings. I was like, hey, these are my people. PhDs washing dishes and linguists on a continent with no languages. Mars is the step beyond the Antarctic, and perhaps we all need to take it in our imaginations. Our civilization feels untethered to me. We're at a loose end, huddled in a tiny corner of our system. We watch the wandering planets and the wheeling stars and the cycles of day and night, and wonder what the hell we're doing. We're all linguists on a continent with no languages. As a consequence, we scrabble around, eking out the ever more precious resources on Earth, trying to expand and build more stuff and grow in a thin shell of air on the two-dimensional surface of a small rock, giving little thought for the three-dimensional path marked by the lights in the night. Robert Zubrin, the visionary engineer whose work has inspired, amongst others, Elon Musk, likes to say that ideas have consequences, and the worst idea in the history of humanity is that we must compete for limited resources. This is false. The solar system contains raw materials beyond our needs or desires, and they will become resources when we choose to access them. The international tensions created by the competition for earthbound resources are based on the entirely false and dangerous idea that resources are limited. False, false, false. We have the technology, and perhaps as we drift ever more aimlessly, we may discover the will to unlock the unlimited treasures in the vast solar system of which we are a part. We need to shift our collective consciousness. We burn too bright for this world alone, but that does not mean we should extinguish the flame. We must forge a new path that transcends competition between nations, that requires the wholesale rejection of the mindset that mistakenly compels us to retreat or fight over dwindling resources on a single groaning planet. We must transform ourselves into a multi-planetary, spacefaring civilization, and this begins with the colonization of Mars, an achievable goal forged from the human desire to explore and expand without pushing up against someone else's border fence or damaging our planet beyond repair. Imagine the magnificent intellectual and physical vistas, the new technologies, the opportunities, the excitement of creating a new society. the joy of extending our collective experience and hopes and dreams to a new world and worlds beyond. Mars has a pivotal role to play in our future. If we don't go there, we'll never go anywhere. And if we go nowhere, we'll die here. Breathing new life into the old red planet will breathe new life into us. It will be our first step beyond the cradle and onwards to the stars. The Age of Planetary Surfaces. Earth before life, 4.5 billion years ago, was no nascent Eden, closer to the realm of Hades than the Garden of God. Molten and smouldering, cloaked in toxic clouds through which the young sun could barely break to signal the coming dawn. The planet still trembled from the aftermath of a glancing collision with Mars-sized Theia, now fragmented into a ring of debris that, given time, coalesced with the ejected rubble of Earth to form the Moon. 4 billion years later, two people who owed their existence to the energetic geology of Hadean Earth stepped onto the surface of the coalesced rubble and considered their position in the firmament. From their vantage point, Armstrong and Aldrin viewed a peaceful, pristine planet that has been many different worlds since its formation. How do we know? How can we speak with any authority of events that happened billions of years ago, beyond not only memory, but also life on Earth itself? How is such a timeline calibrated? The answer lies in the rocks. Apollo delivered many treasures, countless engineering breakthroughs, a generation inspired, Earthrise from Apollo 8, the simple joy of exploration. But scientifically speaking, the treasure was rock. 382 kilograms of rock collected from 6 landing sites. On the Moon, as on Earth, rocks can be dated with great accuracy, using the natural clocks provided by the radioactive decay of certain atoms. The chemical element rubidium, for example, occurs naturally and quite commonly in a form known as rubidium-87, which is found in many potassium-rich minerals. It is unstable, with a half-life of 48 billion years. This means that over a period of 48 billion years, half of the rubidium-87 atoms that were present in a rock when it formed will have decayed away, transmuting into another sort of atom, strontium-87. An older rock will have fewer rubidium-87 atoms and more strontium-87 atoms. There is a little more to it than that, of course. How do we know how many rubidium and strontium atoms were present when the rock formed? The clever part of the dating procedure is that we don't need to know. The method, called the isochron method, relies on the fact that there is another naturally occurring form of strontium, which is not produced by radioactive decay, known as strontium-86. Strontium-86 is stable and chemically identical to strontium-87. The only difference is that it has one more neutron inside its nucleus. This means that any strontium-86 atoms inside a rock today were present when the rock originally formed. By counting the number of rubidium-87, strontium-87 and strontium-86 atoms in a selection of samples taken from a rock, it is possible to calculate the absolute time elapsed since the rock formed. On Earth, some of the oldest crustal rocks are found off the southwest coast of Greenland at a place called Ishwa. Using rubidium-strontium dating, we know these rocks were formed 3.66 billion years ago, with an uncertainty of 0.06 billion years. The oldest known rock on Earth was found in Jack Hills, Western Australia. It formed 4.404 billion years ago, with an uncertainty of 0.008 billion years. All known samples from Earth's crust are younger than 4 billion years old, because the seething surface of the Hadean Earth meant that rocks were constantly being melted and reformed, resetting the radiometric clocks. The same analysis can be carried out on meteorites that have fallen to the surface of Earth from space. The majority, over 1,000 known, formed between 4.4 and 4.6 billion years ago, which is consistent with independent estimates for the age of the solar system, using, for example, helioseismology measurements of the amount of helium in the Sun's core. The youngest of the moon rocks returned by the Apollo astronauts were 3.2 billion years old, and the oldest were 4.5 billion years old. 12 of the samples were over 4.2 billion years old. The variation in age of the moon rocks at the Apollo landing site is extremely interesting and important, and it forms the basis of the most accurate technique for dating areas of the moon from which we have no rock samples. We can make a graph showing the age of the rocks collected from each Apollo landing site, and also the Russian Luna 24 robotic sample return mission, plotted against the number of craters per square kilometre at the site. The dark blobs around the labels of the various missions will represent the uncertainty of the measurements of the ages of the rocks and the crater counts. Two very low and uncertain points from the craters Copernicus and Tycho are from rocks collected by Apollo that are thought to have been thrown into the landing sites by the impacts that created these two distinctive lunar craters in the much more recent past. Two solid lines curve up across the plot, bounding the measured points. Older sites have more craters, which is easy to understand because there's been more time for meteorite impacts to build up. Surfaces that were created in the more recent past, such as the Copernicus crater, have experienced many fewer subsequent impacts. Imagine now that there's an area of the moon from which we have no samples, but we do have photographs of that location from space. We count the number of craters per square kilometre. Let's say we get an average of 0.0002 craters above a diameter of 4 kilometres per square kilometre. This allows us to say that the surface formed somewhere between around 3.2 and 4 billion years ago, similar in age to the Apollo 17 landing site. This is one of the simplest uses of the graph. More importantly for our purposes, we can extrapolate the graph from the Moon to Mars. We have to make some model-dependent estimates of how the number of impacts changes because Mars is a larger planet with a stronger gravitational pull, and to account for Mars's different place in the solar system closer to the asteroid belt, the source of most of the impacting objects. We can do this with some confidence, and this is the primary way we estimate the absolute age of the different regions of Mars. The Noachian terrain is the oldest and has the highest density of craters, followed by the Hesperian and the Amazonian. The northern lowlands have been resurfaced by volcanic activity in the more recent past, which we know because they're relatively devoid of craters, much like the lunar seas. In this way, the absolute dates we quote for events on Mars are all ultimately tied to the radioactive dating of moon rocks, and this is one of the main reasons why the Apollo rock samples from different landing sites are so valuable scientifically. There's another key line on the graph, a dashed line we'll call constant production rate. The number of craters plotted against age would follow this line if the Moon had been subjected to a constant rate of impacts throughout its history. The measurements follow this line until we get to the surfaces around 3.8 to 4 billion years old, when the number of craters increases dramatically, implying that in the early history of the solar system, there was a time when the rate of impacts was much greater than today. That's not surprising. We might expect that the young solar system would have been filled with leftover rubble from the formation of planets, and so a more violent place. But there is a complication. If we assume that the impact rates seen on the oldest lunar terrains, such as the Apollo 16 landing site in the Descartes Highlands, were sustained all the way back to the Moon's formation, then the impact rate would have been impossibly high. The amount of mass falling on the surface of the Moon would have been similar to the mass of the Moon itself. We know that didn't happen, so the assumption is that the rise of the impact rate curve on the graph is in fact a spike that peaked around 3.9 billion years ago, and then returned to the much lower impact rate from earlier times. This violent spike in the rate of impacts from space is known as the late heavy bombardment. The cause of the late heavy bombardment is not known, but a leading theory is that Neptune changed its orbit from inside to outside that of Uranus. and the resulting gravitational disturbance deflected a maelstrom of icy objects in the distant Kuiper belt towards the planets of the inner solar system. We might reflect on the interconnected nature of knowledge and of the solar system. Exploration of the moon provided us with the intellectual tools to date the surface of Mars. Using the scars delivered by objects deflected into the inner solar system by events that occurred far away in space and time, beyond the orbit of either world.
On the 24th of June 1947, Ken Arnold, an amateur pilot from Scobie, Montana, was flying over Mount Rainier, one of the most dangerous volcanoes in the world. Arnold was an experienced pilot with thousands of flying hours, and this implied he was a trustworthy observer. On returning to the airfield, he claimed to have seen 9 objects flying in the mountain skies, describing them as flat like a pie pan and like a big flat disk. He estimated that the disks were flying in formation at speeds of up to 1,920 kilometers per hour. The press jumped on the story, coining the term flying saucer, and within weeks, hundreds of similar sightings were reported from all over the world. On the 4th of July, a United Airlines crew reported seeing another formation of 9 disks over the skies of Idaho, and 4 days later, the mother of all UFO stories exploded at Roswell, New Mexico, with the confirmation and then rapid retraction by the United States Air Force of a recovered flying disc. An alien craft crash-landed on Earth. I'll put my cards on the table here. I believe in UFOs. That is to say, I believe that there have been sightings of flying things in the sky that the observers were unable to identify, some of which were objects. But I do not believe for a moment that these were spacecraft flown by aliens. Occam's razor is an important tool in science. It shouldn't be oversold. Nature can be complex and bizarre. But as a rule of thumb, it is most sensible to adopt the simplest explanation for an observation until the evidence overwhelms it. My favourite response to the criticism that dismissing the possibility of alien visitations to Earth is unscientific was provided by physicist and Nobel laureate Richard Feynman in his Messenger lectures at Cornell University in 1964. Some years ago, I had a conversation with a layman about flying saucers. Because I am scientific, I know all about flying saucers. I said, I don't think there are flying saucers. So my antagonist said, is it impossible that there are flying saucers? Can you prove that it's impossible? No, I said, I can't prove it's impossible. It's just very unlikely. At that he said, you are very unscientific. If you can't prove it impossible, then how can you say that it's unlikely? But that is the way that is scientific. It is scientific only to say what is more likely and what less likely, and not to be proving all the time the possible and impossible. To define what I mean, I might have said to him, listen, I mean that from my knowledge of the world that I see around me, I think that it is much more likely that the reports of flying saucers are the results of the known irrational characteristics of terrestrial intelligence than of the unknown rational efforts of extraterrestrial intelligence. It is just more likely. That is all. Irrespective of the veracity of the stories of mutilated cows, crop circles, and violated Midwesterners at the hands of these alien visitors, the cultural impact of these early sightings was very real. America quickly entered into a media-fueled love affair with alien invaders in shiny discs, brandishing anal probes. Why didn't they use MRI scanners, a non-Freudian would surely ask. Of all the hundreds of thousands of references to flying saucers that began to appear in the media, a cartoon by Alan Dunn, published in the New Yorker magazine on the 20th of May 1950, found its way into the lunchtime conversation of a group of scientists at the Los Alamos National Laboratory in New Mexico. Enrico Fermi was one of the greatest 20th century physicists. Italian by birth, he conducted his most acclaimed work in the United States, having left his native country with his Jewish wife Laura in 1938 as Mussolini's grip tightened. Fermi worked on the Manhattan Project throughout World War II, first at Los Alamos and then at the University of Chicago, where he was responsible for Chicago Pile 1, the world's first nuclear reactor. In a squash court underneath a disused sports stadium in December 1942, Fermi oversaw the first man-made nuclear chain reaction, paving the way for the Hiroshima and Nagasaki bombs. After the war, Fermi settled as a professor in Chicago, but he often visited Los Alamos. During one of these visits in the summer of 1950, Fermi settled down for lunch with a group of colleagues including Edward Teller, the architect of the hydrogen bomb, and fellow Manhattan Project alumni Herbert York and Emil Konopinski. At some point, talk turned to the recent reports of UFO sightings and the New Yorker cartoon, stimulating Fermi to ask a simple question that turned a trivial conversation into a serious discussion. Where are they? Fermi's question is a powerful and challenging one that deserves an answer. It has become known as the Fermi paradox. There are hundreds of billions of star systems in the Milky Way galaxy. Our solar system is around 4.6 billion years old, but the galaxy is almost as old as the universe. If we assume life is relatively common, and on at least some of these planets intelligent civilizations arose, it follows that there should exist civilizations far in advance of our own, somewhere in the galaxy. Why? Our civilization has existed for around 10,000 years, and we've had access to modern technology for a few hundred. Our species, Homo sapiens, has existed for 250,000 years or so. This is a blink of an eye in comparison to the age of the Milky Way. So if we assume we are not the only civilization in the galaxy, then at least a few others must have arisen billions of years ahead of us. But where are they? The distances are not so vast that we cannot imagine traveling between star systems in principle. It took us less than a single human lifetime to go from the Wright brothers to the moon. What might we imagine doing in the next 100 years, or 1,000 years, or 10,000 years, or 10 million years? Even with rocketry technology as currently imagined, we could colonize the entire galaxy on million-year timescales. The Fermi paradox simply boils down to the question of why nobody has done this, given so many billions of worlds and so many billions of years. It is a very good question.
The crater counting techniques developed from our exploration of the Moon allow us to place our observations of Mars today in historical context. They allow us to construct an absolute timeline. If we see evidence that water once flowed across a surface or pooled within a crater, and we can date the area using crater counting, then we can estimate when the water flowed and when it disappeared. As we've discussed, curiosity is exploring Gale and painting a vivid picture of what happened there. Crater counting allows for an estimate of when, independent from the rover's ground-based measurements. A recent analysis using images from orbit taken by MRO found 375 craters ranging in size from 88 meters to 23 kilometers inside Gale crater, implying an age of 3.61 billion years, with an uncertainty of around 60 million years. This places the formation of the crater and the geological events that played out inside it during the late Noachian, early Hesperian, and this time frame is consistent with observations of the presence of water at many other sites of a similar age. Consistency over a wide range of independent observations is extremely important in science. One site or set of observations alone may be tantalizing, but rarely compelling. Multiple independent observations reduce the uncertainty and give scientists more confidence in their understanding. When our goal is to understand the sequence of events on an ancient landscape far away that no human has ever visited, caution and consistency are both vital commodities. Since we have only one active rover at present, and landings are by their nature rare and confined to limited geographical regions, orbital observations of much wider areas of the planet are a vital tool. MRO's HiRISE camera has provided some of the most beautiful and detailed high-resolution photographs in the history of space exploration, covering over 99% of the Martian surface. Features as small as a meter wide can be seen in these images, and the camera can also operate in the infrared, allowing for the identification of different minerals at the surface. There are many beautiful photographs in the MRO library that reveal evidence of persistent lakes and river systems, particularly across the Noachian terrain in the southern highlands. Sites such as the Jezero crater clearly show meandering river channels draining into deltas. Some images, constructed using both visible light and data from the spacecraft spectrometer, reveal well-defined river channels flowing out of the crater, and the presence of carbonates and clays that form where there is persistent liquid water. For these reasons, the Jezero crater is one of the 3 prime targets for NASA's Mars 2020 rover. Some of the more recent finds are associated with the Arabia Terra region, which sits between the Noachian southern highlands and the great lowlands of the north, where water could have flowed towards a possible northern ocean. Researchers from University College London and the Open University studied an area of Arabia Terra equivalent to the size of Brazil, using high-resolution imagery from MRO. The study mapped a network of over 17,000 kilometers of ancient river channels, not the usual excavated dry river valleys, but rather a network of inverted channels, raised lines of sand and gravel laid down on the riverbeds that persisted while the land around them eroded away long after the rivers dried. Similar ghost rivers are seen in desert environments on Earth in Utah, Oman, and Egypt, where erosion rates are slow. The identification of the ghost rivers allows for Arabia Terra to be identified as a fossilized floodplain, somewhat like the lower sections of the river Ganges on Earth, the lowland interface between mountain rivers and the sea. This is an important discovery because it feeds into a long-standing and still unresolved scientific debate about the nature of the Noachian climate. Nobody disputes that rivers once flowed on Mars, or that many impact craters were once home to lakes. The key question is one of longevity. Was Mars warm and wet for long periods of time, or was it for the most part a frozen planet on which water occasionally melted, perhaps triggered by sporadic volcanic activity or shifts in the planet's orbit? The tension arises because climate modelers find it very difficult to simulate an ancient Martian atmosphere thick enough to deliver a stable climate over hundreds of millions of years that would have been lost at a sufficiently fast rate to produce the Mars we see today. In a recent review, for example, Robin Wordsworth concludes, "The weight of geochemical and geomorphological evidence points towards a late Noachian hydrological cycle that was intermittent, not permanently active. And the latest state-of-the-art Martian climate simulations suggest a water-limited early Mars with episodic melting episodes may be a suitable paradigm for much of the later Noachian and early Hesperian climate." Before the recent analysis of the Mars Global Surveyor data, it was thought that there was a relative absence of river channels on Arabia Terra, and this was interpreted as support for a frozen, episodically wet Mars. Ice may have been concentrated in the southern highlands, and so lower elevations like Arabia Terra may have been generally more arid and therefore devoid of river channels. This appears not to be the case. Arabia Terra was once very wet indeed. This debate has no consensus resolution at the time of writing, which reminds us of important points about both our knowledge of Mars and science in general. We are describing and attempting to understand and contextualize events that happened over 3.5 billion years ago, at or around the time that life on Earth began. That is an immense span of time, during which orbital parameters have changed, solar output has varied, and innumerable impact events have cratered the planets. Tracing the evolution of an atmosphere backwards through time from today's measurements, anchored by geological and geochemical evidence from a few landing sites and orbital imagery, is extremely difficult. Suffice to say, there remains an unresolved tension between Mars's small size and large distance from the Sun, and the clear evidence of an ancient water cycle, episodic or persistent. As Wordsworth writes in the introduction to his review, the nature of the early Martian climate is one of the major unanswered questions of planetary science. The complexity and apparent intractability of the mystery is reason enough for many scientists to study Mars. The character of the scientist requires not only comfort with, but attraction to the unknown, an acceptance of and delight in the complexity of nature. There is no simple story of any planet. They are each too big and too old and subject to too many variables. We might reflect on what that means for our own existence, as individuals and as a species. The specific fact of our existence is inextricably linked with the evolution of our planet through an incomprehensible web of cause and effect stretching back via major and minor events, many beyond Earth itself, and filtered by the multidimensional sieve of evolution by natural selection. This connects us with every living thing that went before, back to the origin of life almost 4 billion years ago, and the origin of our planet 500 million years before that, and the origin of the solar system and the laws of nature who knows when, perhaps during the Big Bang, or perhaps infinitely far away in time. There's a lot we can't know. The search for certainty is a fool's errand, and the lesson is to find delight in not knowing, while simultaneously committing to extending the domain of the known. That's the key to science, the key to happiness, and the only reasonable response to the existential challenge of existence, because it is the truth. If you don't like that, comfort yourself with the fact that the domain of the knowable is vast, possibly infinite, and perhaps paradoxically, the knowable things about Mars may exceed those about Earth. Because Mars has been in deep geological freeze for much of its life, it is easier to research the deep past than it is on Earth. And that deep past may include the origin of life. Traces of the geochemical alchemy that led to the emergence of self-replicating, information-carrying carbon molecules on Earth 4 billion years ago weathered away long ago, although clues may be found in the common structures and chemistry of living things today. On Mars, however, geochemistry was frozen and archived in regions such as Arabia Terra. If, therefore, life began or even still exists subsurface on Mars, such a discovery may deliver insight into our own origins that would simply not be possible by studying the weathered, ever-changing ecosystems of Earth. This may be the gift of unknowable Mars. She's less unknowable than Earth. The Eridania region of the Southern Highlands may provide the most compelling evidence yet of a warm, wet, early Mars, with conditions not dissimilar to Earth at the time when life began. The analysis we describe below is a beautiful example of how the suite of science instruments aboard multiple spacecraft in orbit around Mars can be combined with our knowledge of cratering rates on the Moon to characterize an environment and trace its history back through deep time. It is also a beautiful example of the interconnected nature of science and the value of exploration. We've already met the elevation maps from the Mola aboard the Mars Global Surveyor. This topological data, in concert with visual data from MRO revealing the location of valley networks, suggests that the Eridania Basin was once a giant lake, possibly the largest ever to exist on Mars, 1.5 kilometers deep in places, and containing 3 times more water by volume than the Caspian Sea on Earth. We know the terrain is late Noachian, around 3.7 billion years old, from crater counting. The Chrism spectrometer on board MRO reveals the mineralogical composition of different areas of the Eridania Basin, and this can be used in conjunction with the topological and visual data to build a 3-dimensional picture of the landscape and its chemical composition. In the deepest areas of the Eridania Basin, magnesium and iron-rich clay minerals are common, laid down as sheets of saponite, talc, serpentine, and so-called tot clays. These are characteristic of seafloor environments on Earth. Materials known as iron-rich phyllosilicates are also seen, which are again characteristic of terrestrial seafloor deposits. The mineral jarosite is detected, suggestive of the chemical weathering of sulfite deposits. There are many different carbonate signatures containing iron, manganese, magnesium, and calcium. Higher up the basin walls, chlorides are found, which are indicative of evaporation in shallower water. The most likely explanation for the origin of the deep clay, carbonate and sulfite deposits, it's argued, is volcanic activity on the floor of a deep lake, because very similar deposits are seen at hydrothermal sites on Earth. The iron minerals detected are similar to those formed in the iron-rich early oceans of Earth, prior to the release of large amounts of oxygen into our atmosphere by photosynthesis. All this beautiful topological, visual, geophysical and geochemical data can be combined to produce a picture of what was happening in the Eridania Basin around 3.7 billion years ago. The geochemistry of the low-lying regions is indicative of a deep-sea, volcanically active hydrothermal environment, with the salt-rich deposits at higher elevations suggestive of slow evaporation in shallower waters. The basin contained an iron and mineral-rich ocean, energized by active volcanism deep below the waves. A cauldron of complex geochemistry, stirred by the constant flow of energy from the inner planet. This is a striking conclusion because at the same time, a few 100 million kilometers across the solar system on Earth, many biologists believe that life began in similar deep-sea volcanic environments. The theory that life on Earth began in hydrothermal vent systems is mainstream, although not universally accepted by any means. The idea is partly based on the observation that all living organisms on Earth today share a chemistry associated with the establishment of gradients in the concentration of protons across membranes, known as chemiosmosis. Proton gradients are also characteristic of the geochemistry of alkaline hydrothermal vent systems in acid oceans, which were common on the young Earth and perhaps the young Mars. An analysis published in 2017 claims to have detected evidence of biological activity in rocks laid down by hydrothermal activity at least 3.77 billion years ago in the Nouveau-Guitook crustal belt in Quebec, near the Greenland Ishua rocks. The evidence comes from tube-like coils of the iron oxide mineral hematite, similar in size and form to structures laid down by iron-oxidizing bacteria in hydrothermal environments today. It's possible that the rocks at Nouveau-Guitook are much older. A radiometric date using the samarium-neodymium decay process suggests an age of 4.28 billion years, which would make them by far the oldest rocks on Earth, and an astonishingly early date for biological activity. These findings are controversial, in part because of the difficulty of understanding how Earth's active geology has modified the samples over such vast timescales. This is where Mars may have an advantage over Earth in helping us to understand the processes by which the chemistry of a planet became the chemistry of life. The environment at Eridania is far better preserved than that at Nouveau-Guitook. It has been in sterile, almost deep freeze conditions for over 3 billion years, the ultimate laboratory for studying the origin of life, if indeed life began on Mars. The story of the Eridania Basin and the possible scientific promise it holds was pieced together by using the results from different instruments on different spacecraft over many years, spanning several scientific disciplines: geology, chemistry, spectroscopy, laser altitude ranging, and photography. The estimate of the age of the surface required the Apollo lunar rock samples from 50 years ago, and radiometric dating techniques which required an understanding of nuclear physics. The estimate of the age of the surface requires a model of the entire solar system in order to interpret the measured crater density, which illustrates another important idea. The solar system is a system. No planet is an island. No planet can be understood in isolation, just as the structure of any one living thing on Earth cannot be understood in isolation. Organisms are a product of evolution by natural selection, the interaction of the expression of genetic mutations and mixing with other organisms in the ecosystem and the wider environment. The planets formed in a chaotic maelstrom from motions as random as the impact of a cosmic ray on a strand of primordial DNA. And whatever worlds emerged from the chaos have had their histories shaped profoundly by their mutual interactions throughout their evolution. The late heavy bombardment is a beautiful example. If indeed we discover that life began in the Eridania Basin, what a magnificent illustration of the unity of knowledge that would be. Understanding developed over centuries, the life's work of thousands of explorers, field geologists, chemists, biologists, astronauts, engineers, distilled into the discovery of a second Genesis. But more than that, because of the pristine nature of the ancient environments on Mars, such a discovery would deliver an insight into our own origins that may not be available to us here on Earth. Mars is a time capsule, containing the frozen chemistry of an ancient world similar to the Earth when life began. But while Earth's deep past has been largely erased by 4 billion years of geology and the action of a complex global living ecosystem, which has transformed the planet and its atmosphere beyond all recognition, Mars is a fossil from the deep past. This raises the wonderful possibility that another world, albeit an integral part of our system, may be the key to decoding the mystery of the origin of life here, the reason we exist. It's almost as if we have to leave the cradle in order to truly understand it. Around 3.5 billion years ago, change was underway on Mars. The warmer, wetter episodes that characterized the planet for millions of years during the Noachian became less frequent, and the climate drifted, imperceptibly at first, towards the colder, arid state we recognize today. The water that flowed freely over the surface during the Noachian became locked away in giant reservoirs of ice. Lakes turned solid, and rivers ran dry. The planet wasn't dying, far from it. The fireworks of the late heavy bombardment had faded, but rumbles from the deep maintained the violence. The shield volcanoes of Tharsis, including the mighty Olympus Mons, continued to build even as global temperatures plummeted, and subsurface lava flows occasionally melted the reservoirs of ice, leading to catastrophic floods that challenged the imagination in their scale and violence. The age of Noah became the Hesperian, the age of floods, or rather less portentously and more accurately, the age of occasional floods. The Hesperian period is named after the Hesperia Planum, a giant lava field to the northeast of the Hellas Basin in the southern highlands. The plain was resurfaced partly by the volcano at its center, Tyrrhenus Mons, and spans almost 2 million square kilometers. First photographed by Mariner 9 in 1972, it's a relatively flat landscape with few visible rock formations. The most prominent surface features are the craters that allow us to date it. Tyrrhenus Mons is a very different volcano to Olympus Mons and the giants of Tharsis. It's much more ancient, fully formed not long after the Hellas impact 4 billion years ago, and it erupted through water or frozen ground, a process that produces large amounts of ash rather than lava, what geologists call a pyroclastic eruption. As a result of its age and composition, Tyrrhenus was more prone to erosion than the giants of Tharsis, and today stands only 1.8 kilometers above Hesperia Planum. The Hesperian period was coincident with increased volcanic activity, particularly at Tharsis. But there's not necessarily a causal link between volcanic activity and the transition from the Noachian to the Hesperian. What is clear is that volcanism became the dominant geological force on Mars as the long-lived water cycles waned and cratering rates declined after the late heavy bombardment around 3.5 billion years ago. This is seen in both surface features and mineralogy. Hesperian surfaces are richer in sulfates rather than the clays and carbonates of the Noachian. Sulfates form in the more acidic atmospheric conditions created by the release of sulfur dioxide from volcanoes. While volcanic activity was the dominant force sculpting the smoother Hesperian landscapes, there are spectacular and notable exceptions where water reasserted its dominance, if only for a moment. Ekus Chasma is an unremarkable valley today. Images taken by MRO reveal a deep, steep-sided depression lying to the north of the Mariner Valley. At 100 kilometers long, 10 kilometers wide, and between 1 and 4 kilometers deep, It would be impressive on Earth, but is dwarfed by the magnificent neighbouring Valley system. 3.5 billion years ago, on frozen Hesperian Mars, however, things were different. High above, on the Tharsis Rise, lava surged upwards through the crust and met great reservoirs of ancient ice, releasing vast amounts of water that raged down from the southern highlands. The meltwater was funneled towards Eccles Chasma, where it created one of the briefest and yet most spectacular wonders of the solar system. The waters from the highlands came tumbling over the cliffs, roaring 4 kilometers down into the valley below, over the largest known waterfall in the history of the solar system. Around 350,000 cubic kilometers of water cascaded through the valley, the equivalent of a cube 70 by 70 by 70 kilometers, in less than 2 weeks. This being Hesperian Mars, the atmosphere was not substantial enough for the liquid to persist on the surface, and the water disappeared as quickly as it came, leaving scant evidence of the great falls etched into the canyon walls. Eccles Chasma was unique in scale, but the cycle of volcanic eruption followed by fleeting catastrophic floods was repeated in many locations across the planet throughout the Hesperian. However, in the thinning atmosphere, the presence of liquid water was probably always fleeting, increasingly so as time passed. Hesperian became Amazonian around 3 billion years ago, plus or minus 500 million years or so. When a Mars expert is asked the question, when did the Amazonian begin, they will usually say, depends who you ask. But certainly by 2 billion years ago, long before there was complex multicellular life on Earth, Mars was pretty much indistinguishable from the planet we see today. The red planet didn't die entirely. Volcanic eruptions persisted and have occurred in the very recent past at Tharsis. There may yet be eruptions in the future. But we do know that Mars changed from a world that supported liquid water on the surface under a thick atmosphere, via a period dominated by intense volcanic activity and episodic floods, into a hyper-arid frozen planet with a tenuous atmosphere, more befitting its small size and place in the solar system. This drama played out very roughly during the first 1.5 billion years of its life. The challenge is to understand why. Losing atmosphere. The climate of a rocky planet is a complex dynamic system shaped by myriad interactions, feedbacks, and instabilities, and inevitably changes over geological timescales. The thin envelope of atmospheric gases can be affected dramatically by volcanic and tectonic activity and impacts from space, and on longer timescales by shifts in orbit and tilt, and changes in solar output. Earth seems to be a remarkable exception. The most dramatic atmospheric change over the last 3 billion years has been the gentle introduction of oxygen by photosynthesis. Mars today has a thin atmosphere composed primarily of carbon dioxide. We know this atmosphere must have been significantly thicker in the past, quite possibly at an even higher pressure than that of modern-day Earth, because there was once liquid water on the surface. Mars must therefore have lost most of its original atmosphere, and it's important to understand where it went and why. The ancient atmospheric carbon dioxide molecules could have frozen out onto the surface in the polar ice caps, become locked away in the subsurface as carbonate minerals, or they could have been lost to space, or some combination of all three. To measure the composition of the Martian atmosphere today and understand how it evolved over time, a dedicated mission arrived in orbit in September 2014. MAVEN, the Mars Atmosphere and Volatile Evolution mission, has no high-definition cameras and provides no dramatic photographs of the surface, because the questions MAVEN was designed to answer are about the invisible envelope of gases surrounding the planet. If curiosity is the extension of our hands and MRO our eyes, MAVEN is our nose, sniffing the air for clues to the past. The spacecraft operates in a highly elliptical orbit, bringing it as close as 150 kilometers above the surface, and out beyond 6,000 kilometers. This eccentric path means that on every orbit, MAVEN experiences a wide profile of the Martian upper atmosphere, allowing it to build a three-dimensional picture of the gases that still remain and how their distribution changes with altitude and time. MAVEN's measurements show that Mars is losing atmospheric gases today at a rate of about 2 kilograms a second. The question is, how is the atmosphere being lost, and where is it going? The MAVEN team carried out an ingenious analysis based on observations of the concentrations of two different isotopes of the noble gas argon, argon-36 and argon-38. Argon-38 is chemically identical to argon-36, but it's heavier because it has two additional neutrons inside its nucleus. The ratio of argon-38 to argon-36 is sensitive to the rate at which the atmosphere is being lost to space through a process known as sputtering. High-speed, electrically charged particles from the solar wind hit atoms in the upper atmosphere and literally knock them out into space. Because argon-36 is lighter than argon-38, the relative abundance of argon-36 in the upper atmosphere is enhanced. In technical terminology, argon-36 has a larger scale height than argon-38. This means that argon-36 is preferentially lost to space through sputtering, and the ratio of argon-38 to argon-36 increases. Since there's no other way that argon can be removed from the atmosphere, it doesn't react with anything, and it doesn't freeze at anywhere near the temperatures seen on Mars, the argon measurements provide a very clean indication of the way the Martian atmosphere is affected by the solar wind. By using measurements from MAVEN at different altitudes during its elliptical orbit, and surface measurements of the argon isotope ratio from Curiosity, this beautifully elegant experiment enabled the team to determine that 66% of the argon in the Martian atmosphere has been lost over the planet's 4.5 billion year lifetime. Once this rate of argon loss has been determined, the rate of other atmospheric components can be calculated. The published results concluded: the evidence from MAVEN observations suggests that a large fraction of the Martian volatile inventory has been removed to space, and that loss to space has been an important process in the evolution of the Martian atmosphere through time. In particular, a large fraction of the dominant component of the Martian atmosphere, the powerful greenhouse gas carbon dioxide, has been lost to space through the interaction with the solar wind, with a smaller fraction being locked away in subsurface carbonate deposits, and an even smaller fraction stored as frozen carbon dioxide in the polar ice caps. These changes, the authors conclude, appear to be large enough to account for the change in the Martian climate inferred from the planet's geomorphology. Without declining levels of greenhouse gases in the atmosphere to keep in warmth and protect its lakes and oceans, Mars was destined to become a frozen desert world. But why has Earth not suffered the same fate? We are, after all, closer to the Sun, and bathed in a more violent solar wind. Why has our atmosphere survived the solar onslaught for several billion years, after the Martian atmosphere was stripped away?
Nicholas Copernicus was born in the Polish city of Torun in 1473 and benefited from a superb education after being enrolled at the University of Krakow at 18 by his influential uncle, the Bishop of Warmia. In 1496, intending to follow in the footsteps of his uncle, Copernicus moved to Bologna to study canon law, where he lodged with an astronomy professor, Domenico Maria de Novara, who had a reputation for questioning the classical works of the ancient Greeks, and in particular their widely accepted cosmology. The classical view of the universe was based on Aristotle's not unreasonable assertion that the Earth is at the center of all things and that everything moves around it. This feels right, because we don't perceive ourselves to be in motion, and the sun, moon, planets and stars appear to sweep across the sky around us. However, a little careful observation reveals that the situation is in fact more complicated than this. In particular, the planets perform little loops in the sky at certain times of year, reversing their track across the background stars before continuing along their paths through the constellations of the zodiac. This observational fact, which is known as retrograde motion, occurs because we are viewing the planets from a moving vantage point, the Earth, in orbit around the Sun. This is by far the simplest explanation for the evidence, although it is possible to construct a system capable of predicting the positions of the planets months or years ahead and maintain Earth's unique stationary position at the center of all things. Such an Earth-centered model was developed by Ptolemy in the 2nd century and published in his most famous work, Almagest. The details are extremely complicated and aren't worth describing in detail here because the central idea is totally wrong and we won't learn anything. The sheer contrived complexity of an Earth-centered description of planetary motions can be seen in Ptolemy's model, which shows the apparent motions of the planets against the stars as viewed from Earth. This tangled Ptolemaic system of Earth-centered circular motions, replete with the arcane terminology of epicycles, deferents, and equant, was used successfully by astrologers for thousands of years to predict where the planets would be against the constellations of the zodiac, presumably allowing them to write their horoscopes and mislead the gullible citizens of the ancient world. And if all you care about are the predictions themselves, and your philosophical prejudice and common-sense feeling of stillness require the Earth to be at the center, then everything is fine. And so it remained until Copernicus became sufficiently offended by the sheer ugliness of the Ptolemaic model to do something about it. Copernicus's precise objections to Ptolemy are not known, but sometime around 1510 he wrote an unpublished manuscript called the Commentariolus, in which he expressed his dissatisfaction with the model. I often considered whether there could perhaps be found a more reasonable arrangement of circles, from which every apparent irregularity would be derived, while everything in itself would move uniformly, as is required by the rule of perfect motion. The Commentariolus contained a list of radical and mostly correct assertions. Copernicus wrote that the moon revolves around the Earth, the planets rotate around the Sun, and the distance from the Earth to the Sun is an insignificant fraction of the distance to the stars. He was the first to suggest that the Earth rotates on its axis, and that this rotation is responsible for the daily motion of the Sun and stars across the sky. He also understood that the retrograde motion of the planets is due to the motion of the Earth and not the planets themselves. Copernicus always intended Commentariolus to be the introduction to a much larger work, and included little, if any, detail about how he had come upon such a radical departure from classical ideas. The full justification for and description of his new cosmology took him a further 20 years, but by 1539 he had finished most of his 6-volume De Revolutionibus, although the completed books were not published until 1543. They contained the mathematical elaborations of his heliocentric model, an analysis of the precession of the equinoxes, the orbit of the moon, and a catalogue of the stars, and are rightly regarded as foundational works in the development of modern science. They were widely read in universities across Europe and admired for the accuracy of the astronomical predictions contained within. It's interesting to note, however, that the intellectual turmoil caused by our relegation from the centre of all things still coloured the view of many of the great scientific names of the age. Tycho Brahe, the greatest astronomical observer before the invention of the telescope, referred to Copernicus as a second Ptolemy, which was meant as a compliment, but didn't accept the sun-centred solar system model in its entirety, partly because he perceived it to be in contradiction with the Bible, but partly because it does seem obvious that the Earth is at rest. This is not a trivial objection to a Copernican solar system, and a truly modern understanding of precisely what at rest and moving mean requires Einstein's theories of relativity, which we'll get to later. Even Copernicus himself was clear that the sun still rested at the centre of the universe. But as the 17th century wore on, precision observations greatly improved due to the invention of the telescope and an increasingly mature application of mathematics to describe the data, and led a host of astronomers and mathematicians, including Johannes Kepler, Galileo, and ultimately Isaac Newton, towards an understanding of the workings of the solar system. This theory is good enough even today to send space probes to the outer planets with absolute precision. At first sight, it's difficult to understand why Ptolemy's contrived mess lasted so long, but there is a modern bias to this statement that is revealing. Today, a scientifically literate person assumes that there is a real, predictable universe beyond Earth that operates according to laws of nature, the same laws that objects obey here on Earth. This idea, which is correct, only emerged fully formed with the work of Isaac Newton in the 1680s, over a century after Copernicus. Ancient astronomers were interested primarily in predictions, and although the nature of physical reality was debated, the central scientific idea of universal laws of physics had simply not been discovered. Ptolemy created a model that makes predictions that agree with observation to a reasonable level of accuracy, and that was good enough for most people. There had been notable dissenting voices, of course. The history of ideas is never linear. Epicurus, writing around 300 BCE, proposed an eternal cosmos populated by an infinity of worlds, and around the same time Aristarchus proposed a sun-centered universe about which the Earth and planets orbit. There was also a strong tradition of classic orthodoxy in the Islamic world in the 10th and 11th centuries. The astronomer and mathematician Ibn al-Haytham pointed out that whilst Ptolemy's model had predictive power, the motions of the planets represent an arrangement that is impossible to exist. The end of the revolution started by Copernicus around 1510, and the beginning of modern mathematical physics can be dated to the 5th of July 1687, when Isaac Newton published the Principia. He demonstrated that the Earth-centered Ptolemaic jumble can be replaced by a sun-centered solar system and a law of universal gravitation, which applies to all objects in the universe and can be expressed in a single mathematical equation: F equals G times m1 m2 over r squared. The equation says that the gravitational force between two objects, a planet and a star, say, of masses m1 and m2, can be calculated by multiplying the masses together, dividing by the square of the distance r between them, and multiplying by g, which encodes the strength of the gravitational force itself. G, which is known as Newton's constant, is, as far as we know, a fundamental property of our universe. It is a single number which is the same everywhere and has remained so for all time. Henry Cavendish first measured G in a famous experiment in 1798, in which he managed, indirectly, to measure the gravitational force between lead balls of known mass using a torsion balance. This is yet another example of the central idea of modern physics. Lead balls obey the same laws of nature as stars and planets. For the record, the current best measurement of G is 6.67 times 10 to the minus 11 Newton-meter squared per kilogram squared, which tells you that the gravitational force between two balls of mass 1 kilogram each 1 meter apart is just less than 10,000 millionths of a Newton. Gravity is a very weak force indeed, and this is why its strength was not measured until 71 years after Newton's death. This is a quite brilliant simplification, and perhaps more importantly, the pivotal discovery of the deep relationship between mathematics and nature which underpins the success of science, described so eloquently by the philosopher and mathematician Bertrand Russell. Mathematics, rightly viewed, possesses not only truth, but supreme beauty, a beauty cold and austere like that of sculpture, without appeal to any part of our weaker nature, without the gorgeous trappings of painting or music, yet sublimely pure, and capable of a stern perfection such as only the greatest art can show. The true spirit of delight, the exaltation, the sense of being more than man, which is the touchstone of the highest excellence, is to be found in mathematics as surely as in poetry. Nowhere is this sentiment made more clearly manifest than in Newton's law of gravitation. Given the position and velocity of the planets at a single moment, the geometry of the solar system at any time millions of years into the future can be calculated. Compare that economy. You could write all the necessary information on the back of an envelope with Ptolemy's whirling offset epicycles. Physicists greatly prize such economy. If a large array of complex phenomena can be described by a simple law or equation, this usually implies that we are on the right track. The quest for elegance and economy in the description of nature guides theoretical physicists to this day, and will form a central part of our story as we trace the development of modern cosmology. Seen in this light, Copernicus assumes even greater historical importance. Not only did he catalyze the destruction of the Earth-centered cosmos, but he inspired Brahe, Kepler, Galileo, Newton, and many others towards the development of modern mathematical physics, which is not only remarkably successful in its description of the universe, but was also necessary for the emergence of our modern technological civilization. Take note, politicians, economists, and science policy advisors of the 21st century. A prerequisite for the creation of the intellectual edifice upon which your spreadsheets, air-conditioned offices, and mobile phones rest was the curiosity-driven quest to understand the motions of the planets and the Earth's place amongst the stars. Matching the observations of the wandering stars, the planets, of the night sky with the idea that the Earth was at the center of the solar system required extremely complex models. In the case of Venus, combining the Earth at the center with the observations meant that Venus had a circular orbit around a point midway between the Earth and the Sun, so-called epicycles, with all the other planets having similar complicated orbits around various points scattered around the solar system. Placing the Sun at the center of the solar system, with the planets arranged in their familiar order, with the Moon orbiting the Earth, gave a much simpler system.
It's a story that began before the solar system even truly existed. 5 billion years ago, a vast interstellar cloud of dust and gas, at least 65 light-years across, that's 6.1 times 10 to the power of 14 in kilometers, began to collapse and coalesce under its own enormous weight. Fragmenting into a collection of smaller, dense cores, one of these gigantic clumps formed what is known as the pre-solar nebula, the embryo from which every part of our solar system would develop. In this dense cloud of gas comprised almost entirely of hydrogen and helium, hung every atom that would go on to form the Sun, the planets, and every element that would define the character of each of these worlds, including the ingredients of life, the components of you and me. What triggered this cloud beyond the tipping point and on to the next stage of its stellar evolution is lost in the eons of time. But astonishingly, we have been able to pull together scraps of evidence to guide us. By studying some of the oldest meteorites ever discovered on the surface of the Earth, we've been able to get a glimpse of the time when it all began. Locked away inside these ancient meteorites are the unmistakable signatures of rare forms of iron that we believe can only have been created under a very specific set of conditions. The only place in the universe where these rare isotopes can be formed is at the heart of giant, short-lived stars at the very moment they explode. In other words, they are the product of supernovae. This clear chemical fingerprint from rocks dating back to the earliest days of the solar system, over 4.5 billion years ago, suggests that our solar system emerged among a cluster of thousands of stars in a large stellar nursery, perhaps not unlike the Orion Nebula, the star-forming region that lies closest to the Earth at 1,500 light-years away, which can even be spotted with the naked eye in the night sky. Amongst this original stellar cluster were massive stars that would have dwarfed our own, all burning hard and fast. It appears that as one of these stars reached the end of its life, its death created a supernova, and with it a shock wave that rippled through the distant origins of our solar system, causing dense regions within the pre-solar nebula to rapidly collapse. This moment provided the precise conditions for a new star to form, and thus the story of our solar system began. For the first 50 million years after the Sun was born, our corner of the universe was shrouded in darkness. The only light, the dim red glow of our embryonic star, a T Tauri-type star, struggling to shine through the very earliest years of its infancy. From that original cloud of gas, the Sun forming at its center would swallow up 99% of all the matter in the solar system, leaving just a tiny fraction that would go on to form the other planets. Yet when, after around 50 million years, the Sun's nuclear furnace ignited, its light revealed that one giant planet had already scooped up much of the remaining matter, a world 300 times more massive than the Earth is today. Jupiter, the oldest of all the planets, was there to witness the sun's first dawn. In fact, we think Jupiter had been there from almost the very beginning of the solar system. Evidence suggests that just 1 million years after the birth of the sun, Jupiter had already formed a core 20 times more massive than the Earth, orbiting the dark sun and dividing the building material of the solar system into 2 distinct regions, each with a slightly different chemical makeup, that we would be able to observe in the signature of meteorites that fell to Earth billions of years later. Within just a few million years, this young giant was 50 times as massive as the Earth, and it would go on growing in the dark. By the time the temperature and pressure at the center of the sun had risen so high that hydrogen began to fuse and light up the heavens, entering the main sequence phase of its life in which it continues today, Jupiter was fully grown. Under the cover of darkness before the sun's first dawn, this planet had taken up its position of power, a formidable force that would transform the destiny of every planet that would follow. King of planets. To the Romans, Jupiter was the king of the gods, the ruler of the heavens, and a figure of power who drove forward the all-conquering Roman army with a thunderbolt in one hand and an eagle by his side. The name Jupiter itself means sky father, and it's constructed from the Latin words dies, day or sky, and pater, father. And, as is often the case with mythology, there is a truth lurking amongst the legend. In size alone, Jupiter is by far the biggest planet in the solar system. Its mass is a staggering 1,900 trillion kilograms. That's 2.5 times bigger than all of the other planets in our solar system combined. It's so big, in fact, that if you were an alien species observing our system from a distant part of the galaxy, the Sun and Jupiter might well be all you could see. With a diameter of 142,984 kilometers at the Jovian equator, the Earth would fit inside Jupiter over 1,300 times. And yet this giant of a planet is made almost entirely of gas, comprising 89% hydrogen and 10% helium. It is far less condensed than any of the rocky planets, and has a density far smaller than that of the Earth, 1.326 grams per cubic centimetre, compared with Earth's 5.513 grams per cubic centimetre. For all of its size, Jupiter also has the shortest day of any planet, completing a single rotation every 9 hours, 55 minutes and 30 seconds, as it whips around on its axis at 45,000 kilometers an hour. In the last 50 years, our knowledge of Jupiter has grown exponentially, and with it we've gained a deeper understanding of the role it has played in the shaping of the solar system. No longer just the beautiful banded world we see through our telescopes. This is a planet that we have explored up close, our eyes and ears living within the Jovian system for years at a time. The first close-up glimpse of the giant planet came with the cameras of the Pioneer 10 spacecraft in 1973. This was the first of our planetary explorers to cross the great boundary of the asteroid belt, and from an approach of just over 130,000 kilometers, it was able to take close-up images. In total, Pioneer 10 sent back over 500 precious pictures of this distant world, before flying onto the very edges of the solar system to complete its mission. Just over a year later, Pioneer 11 followed hot on the heels of its sibling craft and swept within 43,000 kilometers of Jupiter's cloud tops before heading on towards Saturn. Voyager 1 and 2 passed by Jupiter in the late 1970s, taking the first extraordinary images of not just the planet but its moons too, as part of their own grand tour of the solar system. This was an historic moment, as Fran Bagenal, scientist on the New Horizons mission, explains. We had hints, but it wasn't until Voyager went up close and personal and took amazing pictures of the moons of the planet that we really began to get a sense of just how complex the worlds around Jupiter are and what a variety there is. The Galileo spacecraft became our first explorer to actually live in the Jovian system. Entering orbit around the planet on the 7th of December 1995, Galileo spent 2 years touring Jupiter and allowed us to explore as never before. thanks to its audacious deep dive directly into the planet. A probe that was released from the craft collected data for almost an hour as it parachuted down through 150 kilometers of Jupiter's atmosphere, before it was destroyed by the intense pressure and temperature. Galileo was also the first mission to explore the extraordinary moons of Jupiter in any detail, helping us to see for the first time that Jupiter lies at the center of an extraordinary system with more natural satellites than any other planet, holding 79 moons in its orbit at the time of writing. 12 of these satellites have been discovered since the beginning of 2017. It's almost certain that the number will rise in the coming years, too, as we're able to explore the Jovian system in even greater detail. The vast majority of Jupiter's moons, 63, are not much more than fragments of rock, none bigger than 10 kilometers in diameter, and are captured asteroids that now orbit the planet rather than the Sun. But at the other end of the scale, Jupiter has 4 giant moons. Fiery Io is the most volcanically active world in the solar system, its surface littered with lakes of lava, while icy Europa is at the other extreme, with its frozen surface protecting a global ocean of water beneath. Marbled Ganymede is Jupiter's largest satellite, and the only moon we know of that has its own magnetic field, while Callisto, the outermost of Jupiter's Galilean moons, is also thought to be home to a subsurface ocean. Each moon has a unique, intriguing character, and they are all visible to us here on Earth, using nothing more than a pair of binoculars. We'll come back to these moons later in the chapter. Then, in August 2011, NASA launched its latest mission to Jupiter, Juno. After traveling for 5 years, the spacecraft reached Jupiter in July 2016 and entered into a perilous elliptical orbit that took it from 8 million to just 4,000 kilometers above the cloud tops of Jupiter's surface. Juno is a mission designed to probe for Jupiter's origin and evolution, which it does by carrying instruments to measure the planet's composition and its magnetic and gravitational fields, allowing it to build up a detailed picture of the interior. It also has the best camera we've ever pointed at Jupiter, which since 2016 has been sending back the most incredible images of the giant planet ever taken. We'll let Heidi Becker, a Jet Propulsion Laboratory physicist and the radiation monitoring investigation lead on the Juno mission, explain the detail of this incredible piece of technology. The Star Tracker is an 18-pound camera because it's passed with tungsten in order to keep the radiation out. What JunoCam's images have shown us is that Jupiter is like going to an impressionist art gallery. It's seeing Jupiter and those atmospheric features up close with the highest resolution that's ever been achieved. We're seeing the zones and belts, the jet streams of Jupiter, in more detail than ever before. For all the majesty and wonder these probes have brought us, Jupiter remains a vast, distant planet, sitting on average 588 million kilometers away from us here on Earth. It's easy to think of this world as a benign beauty, a jewel to marvel at. But what makes Jupiter the true king of the heavens is not just its beauty, but its influence over the unfolding story of the solar system. As we've explored this world ever closer, we are discovering that Jupiter's effect on the fates of entire planets is far more direct and violent than we ever imagined. Its massive gravitational field exerts control not just over its moons, but also over every asteroid, every world, and every life force in the solar system, whose destinies it still holds in its vast reach. To understand the awesome power of Jupiter, we don't need a billion-dollar spacecraft, a rocket, or even a telescope. All we need to do is to look no further than the ground beneath our feet. The surface of our planet is littered with the evidence of our distant godfathers' meddling. Written across our planet in the violent gravitational handiwork of Jupiter are, at the most recent count, 190 visible impact craters, not to mention the thousands more that have long disappeared as the active geology of the Earth's surface has continually renewed itself. One of the most famous is the Meteor Crater, also known as the Barringer Crater, in the northern Arizona desert. which measures more than 1,000 meters across and at its deepest point drops 100 meters below the crater rim. In the late 19th century, geologists believed this vast feature had been created by the San Francisco volcanic field that lies just a handful of miles to the west. But in 1903, Daniel Barringer, a mining entrepreneur and sometime hunting friend of Theodore Roosevelt, began an extensive investigation of the crater and published a set of findings suggesting that it had not been created by a volcano, but rather by a large incoming projectile from outer space. This was the first time anyone had suggested such a theory, and Barringer backed it up with a host of geological evidence, including the discovery of around 30 tons of large iron oxide fragments from the suspect meteorite. At the time, there was much skepticism that an incoming meteor could create such a massive geological feature. But ignoring the overwhelming scientific consensus, Barringer put his money and reputation firmly where his mouth was and formed the Standard Iron Company. The company was created with the sole aim of mining the crater for the 100 million tons of iron ore that Barringer believed lay in the ground, having been deposited by the incoming meteorite. Even at 1903 prices, if he'd been right, that amount of iron ore would have been worth over $1 billion. So unsurprisingly, he continued to dig down to depths of over 400 meters in his pursuit of the meteoric remains. Unfortunately for Barringer, it would take him 27 years of mining to find out what we know today. The meteorite that impacted in that Arizona desert was not only much smaller than he predicted, with current measurements suggesting it was around 300,000 tons, 300 times less than he had thought, but also, with the benefit of advanced studies in such impacts since then, most of the nickel-iron meteorite that fell was vaporized as it struck the ground at around 43,000 kilometers per hour. Barringer's money evaporated not quite as quickly as the meteorite, but by 1929 operations at the site had stopped, and most of his fortune had gone. It would be 50 years before Barringer's work would be fully and finally verified with a landmark publication in 1963. A paper by Eugene Shoemaker and his colleagues, more of him later in the chapter, analyzed the similarities between the geology of the Barringer site and the craters that had recently been created as a result of testing nuclear weapons in Nevada. Shoemaker was able to show that the shocked quartz, also known as coesite, that was identified at Barringer crater, could only have been formed at the enormously high pressures and temperatures created by a nuclear explosion, or in the case of the Arizona crater, by the extraordinary impact dynamics of a 300,000-ton meteorite crashing into the ground. We know now that the giant rock that created the crater, like most of the meteorites that strike the Earth, was once an asteroid, just one of the millions of rocks that circle the Sun between the orbits of Mars and Jupiter. Most of these have been in a stable orbit for billions of years. The rocky leftovers of the birth of the solar system, they orbit in an eternal junkyard of planetary cast-offs. But occasionally, one of these huge rocks is propelled towards the inner solar system, and more often than not, we think the nudge that causes it comes from Jupiter. Why this should happen, and how Jupiter exerts its power not just over the asteroid belt, but over all the worlds around our Sun, is a story we are only just beginning to understand. From our home here on Earth, it's hard to imagine the vast reaches of space that extend beyond our little bubble and the huge expanse of time over which events in the cosmos play out. But all the evidence suggests that around 4.5 billion years ago, Jupiter's orbit began to change, and as it did so, it triggered a period of unprecedented violence, during which the young solar system was utterly transformed. We know this because the marauding planet left a trail of destruction in its wake that we've only just begun to explore. As we've attempted to uncover the 5 billion-year history of our solar system, we've repeatedly looked to the 8 planets and the moons that orbit them to provide clues that fill in the gaps in our story. In the last 50 years, dozens of missions have crossed our thin blue line on the way to those worlds, but only once have we sent a spacecraft to explore a very different type of world, to search amongst the rubble of our solar system's earliest days
and explore the handful of worlds that never quite made it. Sometimes the answers lie in the gaps. Launched on the 27th of September 2007, the Dawn space probe took off from Cape Canaveral on a mission to explore the two largest objects in the asteroid belt, Vesta and the dwarf planet Ceres. This $450 million project was part of NASA's low-cost Discovery program, one of a series of missions designed to be faster and cheaper to deliver. But this was no B-list mission for NASA. Equipped with the most advanced ion propulsion system ever used in outer space, Dawn would be able to reach the asteroid belt and become the first craft in the history of human exploration to enter orbit around Ceres. And yet, without a major planet in its itinerary, the attention of the world only seemed to glance towards this mission, and for the most part its extraordinary findings slipped between the gaps of public attention. The aim of the Dawn mission was simple. This would be the first spacecraft to travel to the asteroid belt, the first to orbit an object in this uncharted region of the solar system, and the first to visit a dwarf planet. All in all, this mission profile was designed to allow scientists a rare chance to travel deep into the past and glimpse the earliest moments in the origin of our solar system. The mission allowed us to explore the evolution of Vesta and Ceres, two very different objects, frozen in time for billions of years since they faltered and failed in the process of becoming fully fledged planets. To travel to the asteroid belt would be a slow but steady voyage for Dawn. After hitching a conventional ride into space on the Delta II rocket, the spaceship began firing its thrusters to orientate and propel itself away from the Earth and towards Mars. The ion thrusters on Dawn were an efficient but gentle form of propulsion for the spacecraft, taking 4 days at full throttle to accelerate the craft from 96 kilometers per hour. It's not exactly a sports car, but when it comes to efficiency, the ion propulsion system is difficult to beat. Powered by a 10-kilowatt solar array, Dawn's engines ran for almost 6 years across the 11-year lifetime of the mission, propelling the craft across space using less than 400 kilograms of its xenon fuel supply, while reaching speeds of 41,360 kilometers per hour. Its trajectory took it on a 16-month journey to Mars, where a gravitational kick sent it on its way out to the asteroid belt, and onwards towards Vesta, its first destination. Almost 500 million kilometers from the Sun, the asteroid belt lies halfway between Mars and Jupiter, the boundary line between the 4 rocky worlds that orbit closest to the Sun and the giant gas and ice planets that lie beyond. Made up of millions of pieces of rock from the dawn of the solar system, it's a graveyard of failed planets, remnants from the heyday of planetary construction. We often imagine the asteroid belt to be a dense, unnavigable mass of tumbling rock, but in reality it's something quite different. The total mass of all those rocks is estimated to be 3 times 10 to the power of 21 kilograms, which, although an enormous-sounding number, is just 4% of the mass of our Moon, with a third of that mass found just in the largest object, Ceres. The rest of this cosmic junkyard is made up of objects covering a vast range of different sizes. On one end of the scale, we think there are at least a couple of hundred asteroids larger than 100 kilometers in size. Then come a million or so stretching to at least 1 kilometer or more, and a countless spread of smaller objects number in the millions and billions, depending on how small you want to go. All of this sounds like it should make for a crowded environment full of collisions, the perfect location to form the basis of a computer game or disaster movie. But even with that many objects, the space they occupy is so unimaginably vast, spread out across 13 trillion cubic miles of space, making the average distance between any 2 large asteroids approximately 2 million miles, or 8 times the distance from the Earth to the Moon. These distances are so large that when we send spacecraft to the outer solar system, the chances of hitting anything are so small that the engineers don't need to make any course corrections to pass through. In fact, if you were standing on an asteroid, you'd be lucky to see another one, and if you did, it would appear as little more than a tiny point of light in the darkness.
As it travelled through this vast emptiness in the early summer of 2011, the Dawn spacecraft slowly began to bring its first target into view. From a distance of over 1.2 million kilometres, Dawn took its first photograph of Vesta against the backdrop of 1,000 stars. Over the next 2 months, Dawn homed in on Vesta, chasing it across the vast reaches of space to arrive at this, the second largest rock in the belt. Entering its orbit on the 16th of July 2011, Dawn became the first spacecraft to enter within the gravitational hold of an object in the asteroid belt. And for the next 14 months, it would explore this extraordinary ancient object, providing a glimpse of our solar system in the very earliest days of its life. When 4 Vesta, to give it its full name, was first discovered by the German astronomer Heinrich Olbers in 1807, it was the 4th asteroid to be discovered after Ceres, Pallas, and Juno, hence the 4 in its formal designation. Olbers was convinced he had found the remains of a lost planet, destroyed in some long-ago collision. Even so, just like the other 3 objects, at first Vesta was given full planetary status, bringing the number of classified planets in the solar system at that time to 11. It wasn't until 1845, nearly 40 years later, that a flood of further discoveries began that quickly increased the number of objects in this region to a point where it was clear they couldn't be classified as planets. And so in the 1850s, 15 planets became 8, and the classification of these objects as a different class of minor planet, asteroids, had begun. 160 years later, as Dawn began its year-long residency in the vicinity of Vesta, it soon became apparent that Olbers' suggestion that this was a fragment of a long-lost planet was not so far off. Vesta is a spheroid-shaped rock, 530 kilometers in diameter and pockmarked with impact craters. The most striking example of these is the crater Rhea Silvia, which at 500 kilometers wide and 20 kilometers deep is one of the largest impact craters in the solar system. At its center is a mountain that rises into the blackness 22 kilometers from the crater floor, making it the second tallest peak in the solar system after Mars's Olympus Mons. What's particularly extraordinary about this crater is that we've long suspected that a particular class of meteorite found on Earth, known as HED meteorites, actually come from material that was blown off the surface of Vesta when this impact occurred around 1 billion years or so ago. Using Dawn's instrumentation, we were able to directly measure the geology of rocks in Rhea Silvia, and when compared with the samples on Earth, we were able to conclude that they are of the same origin. In one of the most beautiful examples of geological analysis in the history of the subject, we now know that we can hold a piece of this faraway asteroid in our hands and directly analyze the secrets hidden within it. When taken all together, the HED meteorites and the findings from the Dawn spacecraft have enabled us to paint a detailed picture not just of Vesta today, but also of its history. Dawn has revealed to us that Vesta has a metal-rich core, just like all of the terrestrial planets, including Mercury, Mars, Venus, and Earth. And analysis of its surface geology has enabled us to date the formation of the asteroid to a couple of million years after the first solid objects began to take shape in the solar system. These are just 2 of the clues that point us to an extraordinary conclusion. Vesta is perhaps the last remaining example of a protoplanet, a half-formed world from the very earliest days of the solar system. Frozen in time, this is a stage that every world we know of passed through, including the Earth. Vesta was on the way to becoming a planet almost 4.5 billion years ago, but something happened to stop its progress. While other worlds went on to flourish, and other protoplanets disintegrated in the violent collisions of the early solar system, Vesta somehow seemed to survive, a fossil of planetary formation for us to not only look at, but through a quirk of fate, actually hold. But this was not the end of Dawn's dive into our deep history. Departing Vesta after 14 months of study, Dawn fired its ion drive, leaving the orbit and heading off for its second planetoid rendezvous, at the largest of all the asteroids, Ceres. Ceres' secrets. Dawn arrived at the dwarf planet Ceres in early March 2015, and from the very first moments of its observations, it sent back some astonishing images. Very little was known about Ceres before our spaceship arrived, but it soon became clear that this was a rock with far more of a story to tell than we could ever have imagined. A story that would help reveal a new perspective on the deep history of our solar system and the enormous influence Jupiter has exerted over it. The Italian astronomer Giuseppe Piazzi discovered Ceres on the 1st of January 1801, and at first he reported his findings as the discovery of a new comet in the region of space between Mars and Jupiter. But it seems from the start that all of his instincts told him this was something else. In announcing his observations in a letter to two fellow astronomers, he noted that since its movement is so slow and rather uniform, it has occurred to me several times that it might be something better than a comet. Piazzi and his colleagues speculated that rather than a comet, they might have found something even more spectacular, a new planet. But after just 41 days of observation, Piazzi fell ill. The path of the newly discovered object strayed into the direct glare of the sun, and in a twist of high astronomical drama, the newly found planet Ceres was lost. With just a tiny number of observations across a small piece of sky, calculating Ceres' orbit was deemed impossible using the mathematics of the time, and many contemporary great mathematical minds predicted it might never be found again. It would take the work of a young German mathematician, Friedrich Gauss, to solve the problem. Attracted to the difficulty and elegance of using mathematics to compute the orbit from just a few coordinates, Gauss pioneered a novel mathematical method that allowed him to calculate the path of Ceres using just 3 of Piazzi's original observations. On the very last day of 1801, 2 astronomers using Gauss's methods searched the region of the sky to which the calculations guided them, and to everyone's delight and relief, recovered Ceres from the darkness. Gauss became a mathematical superstar, and Ceres, firmly back in our sights, was stamped with the classification of a planet. For the next 50 years, Ceres and its companions, Vesta, Pallas and Juno, remained listed as planets until, as we have seen, the discovery of a raft of other objects in this region of space gave rise to our identification of the asteroid belt, and for Ceres it was downhill from there on, until in 2006 it was classified as a dwarf planet. For the next 160 years, little was known about this tiny planet orbiting the Sun at a distance of 413 million kilometers. We knew that it was the biggest object in the asteroid belt, and the only object amongst the millions of asteroids that was large enough to have been rounded by its own gravity. We could also make a good approximation of its size, at around 1,000 kilometers in diameter, and composition, rock and ice, what else? But when it came to surface features, even the powerful eye of the Hubble Space Telescope could make out only the vaguest of features, intriguingly strewn across its surface. It would take Dawn's arrival for us to truly understand the complexity of this world and its history. Even in the early approach phase of the mission, Dawn was able to capture a quality of imagery that at once gave a new perspective on the long-hidden surface. It was no surprise to find it heavily cratered, but while speeding towards Ceres, Dawn beamed back a series of mysterious images, revealing a number of bright spots on the surface of what we had thought would be a dull, dead and frozen world, not what you would expect on a planet that was assumed to be entirely geologically inactive. The brightest of all of these highly reflective areas was imaged near a massive crater known as a crater. At 92 kilometers wide and 2 kilometers deep, it's one of the biggest on the surface of Ceres. Spot 5, as it became known, is in the center of the crater and became the focus of intense investigation as Dawn began its 3.5-year residency in orbit around Ceres. The crater is thought to have formed from a large-scale impact around 80 million years ago, and so the presence of what appeared to be geological active material on the surface was particularly surprising, and at first left the mission scientists perplexed. Not only that, but a haze was also seen to periodically appear above Spot 5, suggesting something was going on beneath the surface. After detailed analysis using Dawn's full range of imaging and spectroscopic capabilities, we now believe that Spot 5 is the result of a geological hotspot. The brightness created by the highest concentration of carbonate minerals ever found outside the Earth, in a dome structure right in the center of the crater. Why does this matter? Well, we know that this type of salt can only be formed in the presence of liquid water, and it's almost certain that an impacting asteroid could not have delivered such material to the surface of Ceres, so the upwelling in which it's found suggests that it comes from deep within this world. It now seems that Spot 5 is the remains of an ice volcano, one that is perhaps still partially active, and thus able to create the haze we have observed. The two brightly coloured patches inside it are thought to be the salty residue left by this ancient formation, deposits of sodium carbonate from an erupting ice volcano that may have first been triggered by the impact that created the crater. However, the dome-like shape upon which the deposits sit is almost certainly evidence of geological activity below the surface, suggesting that hydrothermal activity was involved in bringing the salts to the surface. And Spot 5 is far from isolated. We've now seen areas like the ones in Akator all over the surface of Ceres, and this begins to paint a tantalizing picture of Ceres' past, a past where heat from within the planet created a subsurface ocean, or at least localized pockets of water that surged upwards in the form of great ice volcanoes, bringing with them on the asteroid the carbonate salts that we see sparkling today. As Dawn delved deeper beneath the surface, the surprises kept coming thick and fast. Dawn was able to accurately measure the overall density of Ceres and found it to be 2.16 grams per cubic centimetre, which is less than you'd expect for a rocky body. Ceres is about 2/3 the density of our Moon, which suggests that as well as rock, the asteroid must also hold significant amounts of water ice. This had been suspected long before Dawn arrived, but with our eyes and ears now at work, as Dawn circled Ceres, it was able to take precise measurements and so uncover anomalies in its orbit that revealed something remarkable about this lump of rock and ice. By carefully mapping the shape and gravitational field, we found that the rock and ice weren't evenly distributed. It appears that Ceres' interior is nothing like that of other asteroids in the belt. Instead, it appears to have a rocky core surrounded by an ice-rich crust. This is not the jumbled structure of an asteroid. The differentiation into layers that was discovered by Dawn is something we only see in planets. It seems that around 4.5 billion years ago, Ceres had taken its first steps to becoming a fully fledged world, and then something went catastrophically wrong. So we now think that 4.57 billion years ago, a young rocky planet began to form in the region we call the asteroid belt. In its infancy, this protoplanet was a water world, warmed from within by the heat left over from the violence of its birth. Even in this frozen region of space, orbiting 413 million kilometers away from the weak young sun, a deep saltwater ocean encircled the young Ceres, protected from the freezing temperatures of space beneath a thin layer of ice. Across this ancient embryonic world, ice volcanoes broke through, transforming and renewing the surface as it was bombarded by the bodies that swarmed around it. Today we see just the lifeless remains of this geologically active world in the distinct mountainous landscape and sparkling salts that clothe it. But the subsurface ocean is long gone, locked away as a thick layer of ice between the surface and the core. This is a nascent planet that has been in deep stasis for billions of years. Frozen in time, it is a precious piece of history, an artifact that allows us to glimpse our origins and understand just how precarious a time this was for every planet, including our own. We now think that before Ceres could fulfill her potential, a great disturbance sent shock waves through what would eventually become the asteroid belt and cut its young life short. The vast amounts of rock and ice that made this part of the young solar system such a rich breeding ground for the birth of planets was wiped clean of almost all of its building material, leaving just a fraction of the material needed to build a planet, and nothing from which Ceres could grow. Computer simulations suggest that originally the asteroid belt contained enough material to build a planet the size of Earth, and perhaps that was once Ceres' destiny. Perhaps it was even destined to become a subterranean water world capable of supporting and nurturing life. But before any carbon chemistry could spark into seeds of life, Ceres' fate was sealed, triggered by the wanderings of a giant that lay beyond in the darkness. We now suspect that at this early time in the life of the solar system, as Jupiter circled the young sun, something caused the giant planet to change course and spiral inwards towards the sun, ploughing right through the asteroid belt. The resulting gravitational chaos scattered the contents of the asteroid belt far and wide. Embryonic planets were knocked out from their orbits. The building material of these planetesimals was thrown out and in towards the sun. Jupiter's charge displaced 99.9% of the material in this region of space, leaving Ceres half-formed, half-built, but with nothing more from which to grow. In this part of the solar system at least, the planetary construction business was shut down for good.
Let us now return to Frank Drake's equation and use it as intended as a framework to address in a systematic manner the question of our solitude. Recall that the equation consists of a series of terms which, when multiplied together, give an estimate of the number of currently contactable civilizations in the Milky Way galaxy. At the 1961 Green Bank meeting, only the first term, the rate of star formation in the Milky Way, was known with any precision. Over half a century later, we can do much better. The next term in the equation is the fraction of stars in the Milky Way that have planets orbiting around them, most definitely a prerequisite for an intelligent civilization to emerge. It's true that the civilization may not have remained confined to its home world, and we will discuss this possibility later on. But it must be true that for life to emerge and evolve to the point where it can build spacecraft, a planet of some sort is required. This space we declare to be infinite. In it are an infinity of worlds of the same kind as our own. Giordano Bruno, 1584. The existence of alien worlds has been speculated about for many centuries. Ever since Copernicus began the process of demoting our solar system from its preferred place in the cosmos, it has been natural to assume that at least some of the stars in the sky must have planetary systems. Yet despite this seemingly common-sense conclusion, reached by virtually every right-thinking astronomer from Giordano Bruno onwards, the existence of other planets remained nothing more than an educated guess well into my lifetime. The vast distances between the stars and the limitations of technology locked us inside our own solar system with no way of seeing beyond. Throughout the 19th century, a number of astronomers claimed to have detected distant planets, but all these observations proved to be flawed. Today, the picture couldn't be more different. The night sky is known to be awash with worlds. One of the more enticing of the known solar systems is located around a slightly smaller, cooler version of our Sun called Kepler-62. Around 1,200 light-years from Earth in the constellation of Lyra, the system has been widely studied because it has at least 5 planets. 2 of them, Kepler-62e and Kepler-62f, are particularly interesting because they are Earth-like in both size and distance from the star. Bathed in Kepler-62 shine, these worlds may, if they have the right atmospheric conditions, support oceans of liquid water on their surfaces. We will discuss the significance of this in the context of life later on. The discovery of extrasolar planets has been possible due to the rapid development of precision astronomical instruments, both space-based and terrestrial, that allow us to see beyond the bright glare of stars to the worlds that lie in the shadows. Imagine looking at our solar system from the nearest star system to Earth, Alpha Centauri. The system is 4.37 light-years away and consists of 2 sun-like stars, one slightly more massive than the other, orbiting each other with a period of approximately 80 years. The red dwarf Proxima Centauri is probably a distant, gravitationally bound component of the system, making it a loosely bound triple star. Looking back towards Earth from 40 trillion kilometers with the naked eye, our Sun would look like any other solitary star. Detecting exoplanets is no easy task because planets are vanishingly small and faint, masked by the brightness of their parent stars, and directly imaging them remains a major technical challenge. To step out of the glare has required the development of indirect methods of detection based on surprisingly sensitive technologies. On the 21st of April 1992, the first conclusive detection of an exoplanet was made by radio astronomers Alexander Vorschan and Dale Frail, working at the Arecibo Observatory in Puerto Rico. They were hunting for planets around a pulsar known as PSR 1257+12, located 1,000 light-years from Earth, using a delicate method of indirect observation known as pulsar timing. Pulsars are spinning neutron stars, some of the most exotic objects in the universe. PSR 1257+12 is 50% more massive than our Sun, but has a radius of just over 10 kilometers. It is, in effect, a giant atomic nucleus, spinning on its axis every 0.006219 seconds. That's 9,650 RPM. As you may gather from this rather precise statement, it's possible to measure the spin rates of pulsars with great precision by timing the interval between pulses of radio waves emitted from the stars like a lighthouse. Vorschan and Frail reasoned that if a large enough planet was orbiting a pulsar, the gravitational tug should shift the arrival times of the radio pulses by enough to be detectable. And sure enough, they found 2 planets orbiting PSR 1257+12 and measured their masses and orbits. Planet A has a mass of 0.020 times the mass of Earth and orbits the star once every 25.262 days. Planet B is 4.3 times the mass of Earth and orbits once every 66.5419 days. Subsequently, a third planet has been discovered with a mass of 3.9 times that of Earth and orbiting every 98.2114 days. Pulsar astronomy is indeed a precision science. This was an historic observation, but of limited direct interest to SETI, since there is absolutely no chance that life could survive the hostile environment around such a violent astronomical object. It was, however, an existence proof, the first discovery of planets beyond our solar system, and a surprising one at that. To search for Earth-like planets around Sun-like stars required the development of different but equally beautiful methods of observation. The first of these to be deployed was the radial velocity method. A star doesn't sit still at the center of a solar system with planets orbiting around it. Rather, the star and planets orbit around their common center of mass. The center of mass of a solar system with a single star will always be inside the star itself, because it carries virtually all of the mass, but the star will still wobble around the center of mass of the system as seen from Earth. This planetary-induced wobble is small, but measurable. In our solar system, Jupiter causes our Sun to wobble backwards and forwards with a velocity change of approximately 12.4 meters per second across a period of 12 years. The Earth's effect is minute in comparison, inducing a velocity change of just 0.1 meters per second over a period of a year. In the 1950s, future Green Bank pioneer Otto Struve suggested that such a planetary-induced wobble could be detected using the Doppler effect. When a star moves towards the Earth, its light is shifted towards the blue part of the spectrum, and when it moves away from the Earth, its light is shifted towards the red part of the spectrum. By making measurements of the specific frequencies, i.e. colors of light absorbed by chemical elements in the star's atmosphere, and measuring how much these are shifted relative to the known frequencies as measured here on Earth, the motion of the star backwards and forwards can be determined over a period of time, and this can be used to calculate the orbital period of the planet and to estimate its mass. If there's more than one planet, the motion of the star will be more complicated, but since the orbital periods of the planets are regular, the contributions of the different planets to the star's wobble can be figured out. Struve was one of the first respected scientists to publicly state his belief in extraterrestrial life. In the 1950s, however, the spectrographs used to measure red and blue shift were only able to detect velocity changes of a few thousand meters per second, and at the Green Bank meeting, he could only speculate that his technique would one day confirm his prejudice that planetary systems are common. Struve didn't live long enough to see his method applied, dying just 2 years after Green Bank, long before technology caught up with his ambition. It took until 1995 for 2 Swiss astronomers, Michel Mayor and Didier Queloz, to detect a planetary-induced Doppler shift using the Observatoire de Haute-Provence in France. The team discovered a planet orbiting the Sun-like star 51 Pegasi, located 50.9 light-years from Earth. This planet is named 51 Pegasi b, but its nickname is Bellerophon, after the mythological Greek hero who rode Pegasus, the winged stallion. Since its historic discovery, Bellerophon has been observed and examined in quite some detail, and it is no second Earth. It is a deeply hostile world, orbiting its parent star every 4 Earth days, on a trajectory that takes it far closer than Mercury approaches our own Sun. Unlike Mercury, Bellerophon is a gas giant planet, with a mass 150 times that of the Earth, and a surface temperature approaching 1,000 degrees Celsius. Although only half the mass of Jupiter, it may have a greater radius because the high surface temperature causes it to swell. Such exoplanets are known as hot Jupiters, big enough and close enough to cause a significant wobble in their parent stars, which is why these types of worlds were discovered first by the early planet hunters. The first evidence of a potential Earth-like planet arrived in 2007, when Stéphane Audrey and his team at the European Southern Observatory in Chile announced the discovery of a planet around the red dwarf star Gliese 581, just over 20 light-years from Earth. This was the second planet to be discovered in this system, but Gliese 581c made headline news around the world because of its apparent Earth-like qualities. This planet is a rocky world, about 5 times as massive as Earth, and possibly the right distance away from its parent star to support liquid water on the surface, the stuff out of which science fiction dreams are made. Further research has cast doubt on the idea that Gliese 581b might have the necessary conditions to support life, but in March 2009, the second Earth hunters got their own dedicated scientific instrument, and with it a cascade of new data became available. The Kepler Space Telescope has transformed our knowledge of the distribution of planets in the Milky Way. Kepler is not a general-purpose instrument with multiple detectors and myriad ambitions. The telescope was designed for one purpose: to look for Earth-like planets. Free of the distorting effects of the Earth's atmosphere, Kepler carries a high-precision photometer, an instrument that has measured the light intensity from over 100,000 stars considered stable enough to support life on planets around them. Kepler searches for planets using a technique known as the transit method. If a planet passes across the face of a star as seen from Earth, the observed brightness of the star will drop by the tiniest of margins. Kepler's photometer is so sensitive it can measure changes in brightness. To use precise astronomical language, we should say changes in the apparent magnitude of less than 0.01%. Observing repeated dips in brightness allows the orbital period of the planet to be measured, and the details of the changes in the brightness, combined with knowledge of the orbit, allows the size and mass of the planetary candidate to be estimated. The transit method has been extremely successful in the hunt for exoplanets, but the technique is not entirely reliable, often throwing up false positives. Once a promising candidate is found, the location is passed to ground-based telescopes for further analysis, and if confirmed, the planets are classified as discoveries. Kepler has used the transit method of planet hunting on a quite extraordinary scale, since it became fully operational in May 2009. As I write in July 2014, NASA's Exoplanet Archive lists 1,737 confirmed planets, over 50% of which have been discovered using the Kepler data. This number is all the more staggering because Kepler is only capable of detecting a very small number of the planetary systems in our galaxy. Kepler views around 0.3% of the sky in the constellations of Cygnus, Lyra and Draco, and even in this small patch, the telescope can only detect planets that pass directly in between their parent star and Earth. If the plane of the planetary orbits is orientated at the wrong angle, which is more likely than not, Kepler will not see any planets. Furthermore, Kepler only observed for 4 years, and because it has to see more than one transit to measure an orbit, it is blind to planets that orbit with periods greater than 4 years, which is the case for all the outer planets in our solar system. And finally, Kepler only sees stars out to a distance of approximately 3,000 light-years, whilst our galaxy has a diameter of 100,000 light-years. Kepler's data set, then, contains only a tiny fraction of the planetary systems out there. All of these losses can be corrected for in a statistical sense, and when the numbers are crunched, we have a reliable observation-based number to put into the Drake equation. The fraction of stars that have planetary systems is close to 100%. On average, there is at least one planet per star in the Milky Way galaxy, and we can insert the second term with confidence. Fp equals 1. The extraordinary Kepler mission was expected to last until 2016, but technical malfunctions may mean the telescope has now finished its planet hunting activity. Even so, the huge volume of data is still being worked through, and indications suggest it may have captured evidence for up to 3,000 more planets circling distant stars. This is encouraging for SETI enthusiasts, but in the hunt for civilizations, it's not the number of planets out there that really matters. Rather, it's how many of those planets are capable of supporting life. This is the next term in the Drake equation, the average number of planets per star that has planets that can support life, NE. This is sometimes referred to as the Goldilocks question. How many of those billions of planets are not too hot and not too cold, but just right to allow life to exist on their surface?
How do we know such a dramatic turn in the solar system's history took place? The greatest evidence has come not from our own system, but from the study of other star systems and their planets, a field of science that has exploded in the last 30 years. Until the 20th century, the only evidence of how planetary systems formed and functioned came from one single source, Earth's solar system. Our own backyard was the one place that we had the technology to study, and that meant our view of how a planetary structure worked was deeply skewed towards the seemingly simple structure of a star at the center, 4 small rocky planets orbiting it, then a ring of millions of rocky pieces, remnants from its formation, followed by a series of 4 more planets, the gas giants. It has a pleasing, regular structure about it, all the rocky planets sitting close to the star and the gas giants orbiting further out. We supposed this must be the natural order of things, the way that solar systems have to form. But that all changed when the technology arrived to allow us to detect planets around distant stars. It soon became clear that our solar system is not typical at all. It may, in fact, be very odd indeed. In most of the planetary systems we've observed, the setup is remarkably different to our own. As we have extended our gaze and explored the structure around other stars with the help of exoplanet hunting technology like the extraordinary Kepler telescope, we've begun to see that one of the most commonplace categories of planet is completely missing from our own. Inward of Mercury, our solar system is essentially an empty void. But look at the equivalent region around most stars we have studied, and we often find it packed with a completely different class of planet, super-Earths. These worlds are between 2 and 8 times the mass of the Earth, with thick hydrogen-rich atmospheres. They sit incredibly close in to their stars, orbiting at a rate that makes the head spin. The first discovery of a super-Earth around a main sequence star like our own was made back in 2005 by a team led by Eugenio Riviera, using data from the Keck Observatory in Hawaii. Gliese 876d is an exoplanet almost 7 times the size of the Earth, which is orbiting just 3 million kilometers away from its red dwarf star, Gliese 876. Thought to be a rocky planet with surface temperatures estimated to approach 341 degrees Celsius, with an orbital period, year, of just under 2 days, this is a world completely inhospitable to life. To understand why this rocky planet is found so close in to the Sun, we need to understand the rest of the planetary system, and in the case of Gliese 876, That means looking at the 3 other planets circling further out from the star. The first of these planets to be discovered, and one of the earliest ever observations of an exoplanet, is 876b. Discovered in 1998 by the legendary planet hunter Jeff Marcy, we believe this world is a gas giant at least twice the size of Jupiter, but orbiting much closer to its parent star. In fact, at just 0.2 AU, 30 million kilometers, this massive planet is orbiting much closer in than Mercury orbits the Sun. At that distance, 876b zooms around on its orbit once every 61 days, compared with Jupiter's stately 12-year journey around the Sun. Either side of this giant planet are 2 other worlds, 876c, a gas giant 3/4 the size of Jupiter, and 876e, a planet we think is about the same size as Uranus. All 4 of these worlds orbit within a distance less than the orbit of Mercury. It's as if the whole planetary system has been squashed, packed in tightly around the star, and this configuration is far from rare. As we've explored more and more planetary systems, we've discovered this combination of super-Earths and close-orbiting gas giants is the nearest to a normal layout we observe. What underlies this is the fact that planetary systems are not the static and stable systems we had always assumed them to be. Far from the heavens being full of planets following eternal clockwork rhythms, most systems, including our own, are chaotic, dynamic, and turbulent. The reason for this is that, particularly early on in the infancy of a new system, planets frequently migrate, forming in one part of the system before wandering off into different zones. There are a number of different mechanisms behind these wanderings, but perhaps the most formative on the evolution of a planetary system is the Type 2 migration that occurs to gas giants early on in their lives. A gas giant planet like Gliese 876c would almost certainly have begun its life far further out than it is today, in a region more akin to where we see Jupiter or Saturn in our own solar system. At the very earliest stages of its existence, as this newly formed planet orbited within the cloud of gas and dust of its formation, the planet began to clear a path in its wake, and in doing so triggered a process that would transform its orbit. A shift in its gravitational interactions with the gas-rich disk would have slightly reduced its angular momentum and sent the planet on a different course, spiraling inwards towards the star at the center of the system. This seems to be a common path trodden by many gas giants around distant stars, and is the reason we find a preponderance of so-called hot Jupiters, massive gas giants sitting so close to a star that they orbit it in less than 10 days. The effects of these migrations have an impact far greater than just this, though. In ploughing inwards, a migrating gas giant like Gliese 876c ends up clearing vast areas of space, halting any planetary formation, and instead pushing material inwards towards the star, creating the perfect scenario for super-Earths like 876d to form. This cosmic pinball is the reason why so many of the planetary systems we've been able to explore follow the pattern of hot-ish Jupiter and super-Earths. But why not ours? What was different about the history of our solar system that led to the more expansive layout we see today? Scientists suspect the answer lies with our own gas giant, Jupiter, and the journey it took across the young solar system. The story of Jupiter begins not in the far reaches of the solar system, 778 million kilometers from the Sun, where it orbits today, but much closer in. We now think that almost 5 billion years ago, Jupiter formed around 520 million kilometers, 3.5 AU, from the Sun. At this time, the young giant was still surrounded by the disk of gas and dust from which it had arisen. But Jupiter began to slowly but surely clear its path through the cloud and debris. Over a relatively short period of time of just a few million years, the path through its orbit became completely clear, and just like the huge gas giants we've observed around alien stars like Gliese 876, this caused Jupiter to start spiraling inwards towards the Sun. This process was driven by the gravitational interaction between Jupiter and the cloud of gas, which, as it fell into the Sun itself, effectively dragged the planet with it. This was no subtle shift in Jupiter's orbit. While it spiraled inwards, it would keep falling closer and closer to the Sun, passing through the region of asteroid belt and robbing planetary hopefuls like Ceres and Vesta of the material they needed to complete the journey to planethood. But this was just the start of Jupiter's reign of terror. Further and further the young Jupiter fell, until it reached the vicinity of where Mars orbits today, just 225 million kilometers or so from the Sun. This was no quiet visitor to our local neighborhood. A planet of this size can wreak havoc just by its proximity, and Jupiter's arrival in the inner solar system did just that, transforming the destiny of many of the emerging new worlds, including our own. Lee Fletcher, from Jupiter Icy Moons Explorer mission, explains this action as a tug-of-war. Between the orbits of Mars and Jupiter, we have a large accumulation of objects, rocky objects mostly, known as the asteroid belt. They're not able to form and agglomerate into a complete planet because of the constant tug-of-war between the gravitational forces of the Sun and of Jupiter. So what we see today is a large disk of objects that could be the remnants left over from the formation of our solar system. To understand just how powerful a presence Jupiter must have been as it marauded around the inner solar system, we need to look no further than the worlds it has in its iron grip today. Jupiter has, at the time of writing, 79 known moons held in its orbit by the powerful gravitational field that is generated by the planet's enormous mass, a powerful force field that reaches out from the planet deep into the solar system. It's what has made Jupiter so destructive in the past, and through our exploration of the Jovian system, we have also witnessed its awesome power today. Nowhere is this power more dramatically revealed than on Io, the closest of all the moons to Jupiter. Io orbits just 350,000 kilometers from the cloud tops of its mother planet, a distance that makes it a gravitationally tortured world. A volcanic vision of hell, this is the most geologically active object in the solar system, with over 400 active volcanoes, from which lava flows stretch hundreds of kilometers across the moon's surface, and vast clouds of pyroclastic material blow hundreds of kilometers up into space, creating distinctive umbrella-shaped plumes above its surface. The surface of Io is perhaps the closest that our solar system has to offer of a vision of hell, and all of this activity is created not by ancient internal heat as we see on our planet Earth, but by the power and the influence of Jupiter's gravitational pull. Here on Earth, the volcanism that we see across our planet is driven by a combination of the heat that remains from our planet's violent formation and that which is released from the decay of radioactive elements locked away in the planet's interior. This heat, combined with the high pressures below the surface, creates the molten rock that pools within the mantle layer of the Earth, and then in certain places this magma finds a route to the surface, creating a volcano. On Io, the volcanism is nothing like this. Instead, it's being generated by a completely different mechanism, a process called tidal heating, that is driven in large part by its proximity to Jupiter and the gravitational tug-of-war between other nearby moons. Io is caught between the vast mass of Jupiter on one side and the three other Galilean moons, Europa, Ganymede, and Callisto, on the other, a dynamic that pulls in different directions to violent effect. It's a dynamic that we see in part on our planet every day, as the force of gravity flexes its muscles in the interaction between the Earth and the Moon, creating the twice-daily ebb and flow of our tides. On Earth, the gravitational tug of the Moon creates a tidal force that moves vast volumes of water around the planet, with the biggest difference between low and high tide creating a shift of a maximum of 12 meters in the height of water. The same principle also applies on the surface of the Moon, where the gravitational pull of the Earth creates tides not of water, but of rock. Moon tides are small changes in the height of rocks on the lunar surface caused by the pull of the Earth's gravity. In the case of the Earth-Moon system, these rock tides are measured in just a few centimeters, but Io tells a very different story. Io is roughly the same distance from Jupiter as our Moon is from Earth, and both moons are of equal size. But because Jupiter is so much more massive, the tidal forces it generates are much greater.
with the gravitational pull of Jupiter moving the bulge of rock tides up to 100 meters between low and high tide. That's 5 times the height of any tide here on Earth, lifting the levels of solid rock up and down. In fact, Io contains the least amount of water of any known object in the solar system. But this is not the end of Io's torture. Its relationship with the other large moons, particularly the next moon out, Europa, also adds to the destructive forces that are pulling the very substance of Io apart. Io whips around Jupiter much quicker than our moon goes around the Earth, once again due to the mass of Jupiter, completing an orbit once every 42 hours. If left alone, Io would complete this orbit in a near-perfect circle around the giant planet. But Io is far from alone, and with Europa circling Jupiter precisely once every 2 orbits of Io, it means that in every second orbit, Europa and Io line up, and that rhythmic orbit has consequences. This is what's known as an orbital resonance, and the result is that it gives Io an additional gravitational kick that moves the moon's orbit out of a circle and into an ellipse. Ganymede is also in a resonant orbit with Io in a 1:4 orbital period ratio, and the outcome of this is that as Io orbits, the gravitational forces are constantly shifting and changing, and that stretches and squashes the moon, creating vast amounts of friction that causes its interior to heat up. It's a process called tidal heating, and it's this generation of heat that produces Io's volcanoes, raising the temperature in its interior to over 1,200 degrees Celsius, and creating the violent world of lava lakes and volcanic plumes that we've witnessed through the eyes of Galileo and Voyager. The pull of the 2 moons on Io also stops it gradually falling inwards to Jupiter and being completely ripped apart. Io is an extraordinary example of the power of Jupiter, and a demonstration of how this planet can shape and change the destiny of worlds. Because of its huge mass and the intense gravitational force this produces, any planet or moon that gets too close to it is under threat. While Earth is at a relatively safe distance today, 4.5 billion years ago, as Jupiter moved into the inner solar system, it began to exert its power right in the spot where Mars and our own world were beginning to form. 4.5 billion years ago, the region of the solar system we call home was densely packed with gas and rock, a planetary nursery full of embryonic worlds, each with a different destiny in store. But this fertile space was about to be thrown into chaos by the solar system's most unwelcome of visitors. As Jupiter was pulled from its distant orbit and continued its inwards descent, it paused in this planetary breeding ground. The consequences of this action would be significant and far-reaching. Detailed simulations of the impact this wandering Jupiter would have made suggest that the fate of any super-Earths caught in mid-formation would have been thrown into chaos. The models suggest that Jupiter's inward journey would have driven thousands upon thousands of planetesimals, many over 100 kilometers wide, spiraling into the inner solar system. This planetary breeding ground was turned into a battleground, as Jupiter's presence threw the orbits of any newly forming super-Earths into the overlapping paths of thousands of massive blocks of rock and ice. The result was carnage, a cascade of collisions that blew apart planets and left a trail of fragmentary worlds in its wake, a chain reaction that would culminate in the formation of a spiraling swirl of gas, dust, and rock that would have swept any surviving super-Earths towards the Sun and ultimately to their destruction. In what was just a fleeting moment in the history of our solar system, its destiny changed forever. Our planet would not fit the norm of super-Earths and the tightly packed gas giants that we see across the Milky Way. Instead, we think the inner solar system would have been swept clear of up to 90% of the rocky material thrown in by Jupiter. With just crumbs remaining, 4 small terrestrial planets began to form from the rubble. With Jupiter marauding in its orbit, much of the material that could have gone on to form Mars was lost, leaving the planet with enough scraps to make a planet half its potential size, and transforming it from a possible habitat for life to a world that would freeze and die in its adolescence.
Just that little bit further in, Earth found itself forming in a slightly more substantial ring of gas and dust that would make it the largest of all the terrestrial planets. A lucky escape for our future home, because had Jupiter continued on its inward path, Earth might never have formed at all. But just as it looked like it would sweep everything away, Jupiter stopped in its tracks. On its inward journey, Jupiter had transformed the inner solar system, sweeping away the formative giant planets and leaving just enough material for Mars, Earth, Venus, and Mercury to form. But the stage was now set for another player to enter the story and shift the destiny of both our world and the solar system once again. Waiting in the shadows of the outer solar system, another massive planet was lurking that we now think pulled Jupiter back from the brink. Saturn, a gas giant not as big as Jupiter, but enormous nonetheless, began its own slow drift inwards towards the Sun. Formed much further out than Jupiter, as Saturn began turning inwards, it would have a profound effect on Jupiter's trajectory. As the two giants drew closer together, they became locked in an intimate gravitational dance, an orbital resonance that meant that for every orbit Saturn made around the Sun, Jupiter made 2 circuits, exerting a regular periodic gravitational influence on each other as the two giant worlds passed close by. The result of this orbital resonance between Jupiter and Saturn cleared out all of the gas and dust between the two planets, creating a gap in the disk of the early solar system. And this interaction between the two resonant planets and the gas and dust at the edge of the gap resulted in both planets changing tack. The orbits of both Saturn and Jupiter began to move outwards, away from the Sun, preventing Jupiter from moving any further into the inner solar system. Earth was given a reprieve, and Jupiter was dragged back out into the asteroid belt once more. This change in direction has become known as the Grand Tack Hypothesis, a nod to the action of a sailboat as it tacks and changes course while it travels against the direction of the wind. Just like a sailboat, the theory suggests Jupiter tacked around 1.5 AU from the Sun, in the current orbit of Mars, changing direction and pulling back out to its current orbit at 5.2 AU. It's a theory that's been driven by using advanced computer modeling, which helps to explain many of the inconsistencies between our solar system and the hundreds of other planetary systems we've recently observed. It's the Grand Tack that accounts for the lack of super-Earths and explains the presence of only a handful of small rocky worlds with thinner atmospheres than those observed around other stars. The Grand Tack also allows us to explain the unusually small size of Mars, which simulations predict should be at least half the mass of the Earth, if not bigger, rather than the 0.107 Earth's mass we find it to be. It also helps explain the odd inhabitants of the asteroid belt, transformed by Jupiter's journey not just once but twice across this region of space. This is why we see half-finished planets like Ceres and Vesta left starved of building material, and an asteroid belt that has a surprisingly small mass, with objects that appear to originate from both inside and outside Jupiter's orbit, and have a wide range of eccentric orbits themselves. Jupiter, the father of the skies and ruler of the heavens, had spread its hand far and wide, sculpting the precious solar system we see today in the space of just a few million years. Before coming to rest, though, it would grant one more precious gift to the newly forming planet Earth. As Jupiter was dragged out, crossing the asteroid belt for a second time, it encountered a region full of objects rich in water and bearing minerals, and Jupiter's trajectory caused these objects to be flung back into the inner solar system. They crashed into the young planets and moons with an intensity never seen before or since, in a period known as the Late Heavy Bombardment. It transformed the makeup of the inner solar system, delivering a large percentage of the water Earth holds on its surface today. It's extraordinary to think that it was Jupiter that was responsible for the delivery of the most important ingredient of life, the water that provided an ideal environment for life to spark and thrive in one unbroken line for the last 4 billion years. This story offers an extraordinary understanding of the power Jupiter has wielded over all of our lives. The more we learn about the formation of solar systems, and the more we try to model a system like ours with 4 terrestrial, water-rich planets close to the star and the gas giants further out, the more we learn that perhaps all these things had to happen. These unlikely movements and interactions between the planets were necessary to produce a system like ours, and a planet like ours. So if events like the tack of Jupiter are, as we believe them to be, extremely uncommon, the conditions for the formation of Earth-like planets, terrestrial worlds with plenty of liquid water beneath the gentle pressures of a thin blue line, must be exceedingly uncommon. It's a humbling thought to begin to comprehend that the Earth may not just be a rare rock in our solar system, but a rock that only exists because of the rare system of planets within which it evolved. All the evidence is beginning to suggest that we may be living on a tiny oasis within a vast desert, devoid of life and stretching out across the Milky Way. Today, Jupiter has settled into a regular orbit at the far side of the asteroid belt, its days of marauding through the solar system at an end. Established in a stable orbit for almost 4 billion years, it has looked down on our planet as a distant light in the sky, unchanging while the work of evolution by natural selection has transformed the first sparks of life on Earth into the endless, beautiful forms that we witness today. But although distant and seemingly detached, Jupiter's influence has been far from benign. The history of life on Earth has been interrupted by numerous cataclysms, impacts with asteroids that have fundamentally shifted life again and again. And the hand behind these disruptions? It's Jupiter, that has continued to hold immense sway over our planet, exerting its influence on the asteroid belt with just the smallest of nudges, the difference between existence and extinction. At 16:53 UTC on the 18th of October 1989, the Space Shuttle Atlantis took off from the Kennedy Space Center in Florida, carrying the Galileo spacecraft carefully packed away in its hold. Released into Earth's orbit from the cargo bay just a few hours later, the probe would begin a 6-year journey to Jupiter that would utilize flybys of Earth and Venus to propel it on its 4.6 million kilometer voyage across the solar system. Entering orbit around the giant planet on the 8th of December 1995, Galileo would not only become the first spacecraft to orbit Jupiter, but also the first craft to orbit any of the outer planets. It spent nearly 8 years in the Jovian system and explored the giant planet and its menagerie of moons in intricate detail for the very first time, revealing a host of new discoveries. From precise measurements of Jupiter's atmosphere and observation of its giant thunderstorms, to discovering liquid water under the surface of the moon Europa and the first detailed studies of the intense volcanic activity of Io, this was a mission that opened our eyes to the beauty and diversity of the Jovian system, in a level of detail that we could scarcely have imagined possible. But long before Galileo even arrived, this 2-ton explorer would already have changed our view of the solar system. Entering the asteroid belt in August 1991, Galileo performed the first close-up flyby of an asteroid, passing within 1,500 kilometers of 951 Gaspra, and returning the first detailed images of this rocky remnant back to Earth. Its next close encounter would come almost 2 years later, when flying past 243 Ida, the probe discovered that this asteroid had its own moon. Dactyl, as it has become known, was the first asteroid moon ever to be discovered, and the images are beautiful, a tiny 1.5 kilometer wide object in a chaotic orbit around its parent rock. After this unexpected encounter, Galileo continued its long journey across millions of kilometers of empty space, still 4 years away from its ultimate rendezvous with Jupiter. But by luck rather than judgment, this tiny probe happened to be traveling towards Jupiter
at the precise moment it would be able to witness one of the rarest of shows our solar system has to offer. On the night of the 24th of March 1993, as Galileo sped across the solar system, 3 astronomers working at the Palomar Observatory in California were attempting to spot and track what are known as near-Earth objects, undetected meteors that might be of potential threat to our planet. That evening, David Levy, along with Carolyn and Eugene Shoemaker, took a series of images using the 1.5-foot Schmidt telescope. Lurking in one of them was an unusual artifact that grabbed the attention of the team. Streaking across the image was an object that, although nowhere near the Earth, was of immediate and immense interest. A comet that appeared not only to be unusually close to Jupiter, but also seemed to have multiple nuclei, a fragmented series of rocks trailing across 1 million kilometers of space. In a moment of wondrous astronomical serendipity, the team had discovered the first ever comet in orbit around another planet, a comet that had not only been captured by Jupiter's immense gravity, but had also been pulled apart by it. Shoemaker-Levy 9, as it became known, because it was the 9th comet this team had found, was a comet unlike anything we'd seen before. Quickly confirmed by further studies to be orbiting Jupiter, and thought to have been captured from its solar orbit back in the late 1960s or early 1970s, astronomers were able to wind back through its orbital history and calculate the precise moment the comet was ripped apart. Passing just over 40,000 kilometers above Jupiter's cloud tops on the 7th of July 1992, we think Shoemaker-Levy 9 fell within the planet's Roche limit, and this 5-kilometer comet was ripped apart by the huge tidal forces generated this close to the planet. It disintegrated into 23 pieces visible to us here on Earth, labeled fragments A to W, with the biggest up to 2 kilometers in diameter. This alone was a remarkable discovery, a visual representation of Jupiter's colossal gravitational power. But if that wasn't enough, it quickly emerged from orbital calculations that the comet seemed to be on a trajectory that would ultimately take it straight through the center of the planet. Shoemaker-Levy 9 was on a collision course with Jupiter, and, as if we had scheduled it ourselves, the date of the predicted impact was July 1994. Perfect timing for the spacecraft we already had en route. By the beginning of July 1994, Galileo was 238 million kilometers from Jupiter, on the very edge of the asteroid belt and speeding through space towards its final destination. Ahead of it, comet Shoemaker-Levy 9 was entering its final few days in orbit around the planet. With the first impact expected on the 16th of July, the world's most powerful terrestrial telescopes were trained here, as well as some of our space observatories, from the newly fixed Hubble Space Telescope to the Ulysses spacecraft, which turned its gaze from its primary job of watching the Sun. Even the distant Voyager 2 probe, 6.6 billion kilometers away beyond Neptune, was able to look for radio wave emissions from the impact and employ its ultraviolet spectrometer to make distant observations. But for all of this technology peering across the solar system, there was only one set of eyes that would be able to see the actual first impact. The comet would first hit Jupiter on the side turned away from the Earth, but Galileo was approaching on the night side of the planet, which would give us a unique view not visible from Earth of our first ever observation of a collision between 2 objects in the solar system. The first impact occurred at 2013 UTC on the 16th of July, when fragment A entered Jupiter's southern hemisphere traveling at 60 kilometers a second, hitting the planet with an estimated force of 300 million atomic bombs. With its instruments trained on the impact, Galileo recorded the subsequent fireball, which reached temperatures of over 24,000 degrees Kelvin, creating huge plumes that stretched over 3,000 kilometers high. It was a breathtaking spectacle that quickly came into view from Earth as the rapid rotation of Jupiter brought the impact sites into clear sight, revealing a huge, dark spot on the surface. Over the next 6 days, 21 distinct impacts were observed, as each of the fragments impacted with its own distinct set of characteristics. Fragment G was the largest of all the impacts, striking Jupiter on the 18th of July,
it created a vast scar on the surface of the planet, stretching over 12,000 kilometers across. This extraordinary spectacle continued until the 22nd of July, when Fragment W brought the show to a close, leaving just the scars of the impacts to slowly fade away over the following months. Galileo had given us a ringside seat for this rarest of phenomena. Aided by our technological eyes and ears on Earth and across the solar system, we were able not only to witness a collision like this for the very first time, but also to harvest a vast amount of data. It transformed our understanding of the composition and atmospheric dynamics of Jupiter, allowed us to precisely measure the actual size and composition of the comet itself. But perhaps most important of all, it enabled us to study a cosmic collision firsthand, revealing one of the most important dynamics of Jupiter and the power it exerts over every object and planet in the solar system, including Earth. Before it fragmented, Shoemaker-Levy 9 was at least 2 kilometers wide and weighed over 800 million tons, traveling through the solar system in an orbit that would have taken it hurtling through the inner terrestrial planets, and perhaps even close to Earth. If such an object had hit us, the consequences would have been devastating, sending a vast amount of dust and debris into the air, creating a global smog that would have darkened the planet and cooled the atmosphere, leading to a catastrophic impact on all life on Earth. We will never know whether Shoemaker-Levy would have posed a real danger to our planet, but we do know that Jupiter removed the threat, and such acts of planetary protection are not unusual. The impact of this comet demonstrated in spectacular fashion the role of Jupiter as a cosmic vacuum cleaner. Using its vast gravitational power to capture objects like SL9, by bringing them into its orbit and incinerating them on impact, we think Jupiter acts as the grand protector, luring in objects that might otherwise pose a threat of collision with the Earth. But as we have so often seen with the story of Jupiter, no act is ever truly benevolent. For every potentially dangerous object it shields us from, it can throw another in our direction. That's because of the influence it exerts over all the objects in the asteroid belt. It's easy and quite natural to think of the asteroid belt as a single homogeneous structure, a ring of rocks orbiting in an orderly fashion around the Sun. But it's nothing like that at all. In reality, each of the millions and millions of pieces of rock is following its own individual orbit, distorted and eccentric orbits that create what appears to be a chaotic cavalcade around the Sun. But although there are complex patterns, there is also structure, and nothing has more influence on that structure than Jupiter, the silent conductor of the asteroid belt. In some way, every asteroid dances to Jupiter's tune, whether it's the Trojan asteroids orbiting ahead of and behind Jupiter, or the Hilda asteroids that orbit around in 3 groups, due to the delicate interplay between the gravitational pull of the Sun and that of Jupiter. Every asteroid is in some way caught between the 2 largest objects in the solar system. In such a chaotic, complex system, collisions between asteroids are inevitable, and disturbances to an orbit are commonplace. All it takes is for an asteroid to line up with Jupiter, and the resultant gravitational kick it receives can send an asteroid hurtling outwards, banishing it to the far edges of the solar system, or inwards towards the inner planets. It's by this mechanism that Jupiter continues to exert its influence across every corner of the solar system. Over the last 4 billion years, from its distant orbit 778 million kilometers away from the Sun, Jupiter has repeatedly played with the destiny of our planet and the path of life upon it. The surface of the Earth is strewn with the evidence of cataclysmic collisions that have significantly shaped the history of the planet, from the delivery of huge volumes of water almost 4.5 billion years ago, to the near planet-destroying events of the late heavy bombardment, and even the formation of the Earth-Moon system. All of these momentous events can be linked to the shifting influence of Jupiter and its gravitational stranglehold on objects across the solar system. Over millions of years, the evidence for many of these collisions has been lost or hidden under the ever-changing surface of our planet. But as we've been able to see at impact sites like the Barringer crater, Jupiter's hand is never far away from shaping events on the surface of Earth. The discovery of one such impact crater underneath the Yucatan Peninsula in Mexico back in the late 1970s has revealed evidence of an event that in a single moment changed the course of life on Earth perhaps more profoundly than any other, transforming the very possibility of our own existence. Around 66 million years ago, in the far reaches of the asteroid belt, an object at least 15 kilometers wide was making its final orbit of the Sun. Just one asteroid among millions, this insignificant object had been following the same path for millions, if not billions of years. But then, something changed. Exactly what caused it to alter its path will never be known. But the most likely explanation is that a gravitational nudge from Jupiter pulled it out of its innocuous orbit and sent it on a very different trajectory, a direction that would ultimately bring it on a collision course with Earth. Traveling through space, it would have descended through our atmosphere in just a few seconds, before striking the Earth with a force equivalent to 100 million megatons of TNT. The impact generated a fireball so hot that anything within a 1,000-kilometer radius was instantly vaporized, leaving a crater 180 kilometers wide and 20 kilometers deep. Today, the town of Chicxulub sits near to what we think is the center of the impact site, and lends its name to the crater that stretches out west onto the Yucatan Peninsula and east into the Gulf of Mexico. The evidence for this giant impact doesn't just sit in the partially hidden Chicxulub crater, but also in a thin layer of sediment found throughout the world that contains unusually high levels of iridium. This metal is exceptionally rare in the Earth's crust, but is found in abundance within asteroids. So we believe its presence in the thin layer of sedimentary rocks around the globe dating back 66 million years ago is a direct remnant of the huge rock that struck the Earth. This geological signature is known as the KPG boundary because it marks not just the impact itself, but a boundary between two epochs of life on Earth, the end of the Cretaceous period and the beginning of the Paleogene. It was an event that lasted just a few seconds, but in the aftermath of the impact, millions of tons of sulfurous rock were thrown up into the atmosphere, and during the nuclear winter that followed, 75% of all species were wiped from the face of the Earth, including the largest creatures ever to walk the planet. In a global extinction event that affected every continent simultaneously, the age of the lizards was brought to an end, as almost every species of dinosaur, and many other species as well, vanished in the space. According to Steve Desch, professor of Earth and Space Exploration at Arizona State University, it was an event we would not like to see the likes of again. If something the size of the Chicxulub impactor that killed the dinosaurs were to happen today, it would just be utterly catastrophic for mankind. The most immediate thing is you would have a magnitude 13 earthquake, and then you would have tidal waves that could happen anywhere near water that are miles high, propagating out for thousands of miles in every direction, and that's just for starters. Eventually, so much dust would be kicked up into the atmosphere, it would block sunlight, destroy agriculture, our infrastructure would fail. Today, just traces of the dinosaurs remain. These creatures that ruled the Earth are now nothing more than a dusty history captured in the fossil record. One event, one asteroid, one orbit that was changed by the might of Jupiter. Without the distant planet's intervention, it's possible that those giant lizards might still be here today, and the evolutionary niche that opened up for us with their removal might never have appeared. There are many chance events, not only throughout the history of Earth, but also spanning the entire history of the universe for 13.8 billion years, without which we wouldn't exist. There's an unbroken chain of life stretching back 4 billion years here on this planet. But having said that, there are major events that affected life, and one of them, without doubt, is the asteroid that wiped out the dinosaurs. And so, in that sense, it is true to say that without Jupiter, we wouldn't be here. The godfather of the planets paved the way for humankind to inherit the Earth. and it has looked down on us benevolently ever since, using its immense power to keep us safe. A sleeping giant with its power undiminished. An asteroid impact like the one that cleared the way for us to evolve 65 million years ago would have catastrophic consequences for our civilization, were something similar to strike today. To the naked eye, Jupiter is one of the brightest points of light in the night sky, and through a small telescope it is a beautiful, banded world. It feels distant, eternal, disconnected from events here on Earth. But the more we've learnt about the history of the solar system, the more we've come to understand that that is not the case. Jupiter has played an important and perhaps decisive role in the stories of all the planets, including Earth. You see, the solar system is just that. It's a system, complex, interconnected, and interdependent. So the next time you see Jupiter, just hold your gaze and think for a while about the fact that it is so much more than a point of light, or a planet even. Jupiter is the great sculptor of the solar system, the destroyer and creator of worlds.
What is science? There are many answers, and whole academic careers are devoted to a complex analysis of the historical and sociological development of the subject. To a working scientist, however, I think the answer is quite simple and illuminating, because it reveals a lot about how scientists see themselves and what they do. The great and overused adjective, but not in this case, physicist Richard Feynman gave a characteristically clear and simple description in his Messenger lectures delivered at Cornell University in 1964.
In general, we look for a new law by the following process. First, we guess it. Then we... Now don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, to see what it would imply. And then we compare the computation results to nature, or we say compare to experiment or experience, compare it directly with observations to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make any difference how beautiful your guess is. It doesn't make any difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
Why do I like this so much? The reason is that it's modest, almost humble in its simplicity, and this, in my opinion, is the key to the success of science. Science isn't a grandiose practice. There are no great ambitions to understand why we are here, or how the whole universe works, or our place within it, or even how the universe began. Just have a look at something, the smallest, most trivial little thing, and enjoy trying to figure out how it works. That is science.
In a famous BBC Horizon film broadcast in 1982 called The Pleasure of Finding Things Out, Feynman went further. People say to me, "Are you looking for the ultimate laws of physics?" No, I'm not. I'm just looking to find out more about the world, and if it turns out there is a simple ultimate law which explains everything, so be it. That would be very nice to discover. If it turns out it's like an onion with millions of layers and we're just sick and tired of looking at the layers, then that's the way it is. My interest in science is to simply find out more about the world. The remarkable thing about science, however, is that it has ended up addressing some of the great philosophical questions about the origin and fate of the universe and the meaning of existence, without actually setting out to do so. And this is no accident. You won't discover anything meaningful about the world by sitting on a pillar for decades and contemplating the cosmos, although you may become a saint. No, a truly deep and profound understanding of the natural world has emerged more often than not from the consideration of much less lofty and profound questions. And there are two reasons for this. Firstly, simple questions can be answered systematically by applying the scientific method as outlined by Richard Feynman, whereas complex and badly posed questions, such as why are we here, cannot. But more importantly, and rather more profoundly, it turns out that the answers to simple questions can overturn centuries of philosophical and theological pontificating quite by accident. Reputations count for naught in the face of observation. The famous story of Galileo's clashes with the Inquisition at the height of the Copernican debate, which he certainly did not expect, nobody does, is the archetypal example. Galileo began his university career with the study of medicine, but his imagination was captured by art and mathematics. Between studying medicine in Pisa and returning to his hometown in 1589 to become professor of mathematics, Galileo spent a year in Florence teaching perspective, and in particular a technique called chiaroscuro. Chiaroscuro is the study of light and shadow, and how it can be used to create a sense of depth by accurately representing the way that light sources illuminate objects. Chiaroscuro was one of the most important new artistic techniques to emerge during Galileo's time, allowing a new sense of realism to be portrayed on canvas. Although Galileo spent only a brief time in Florence, the skills he acquired had a great impact on his scientific work. In particular, his carefully developed ability to understand the delicate play of light on three-dimensional shapes, when applied to his later astronomical studies, played an important role in undermining the Aristotelian cosmological edifice, which formed a cornerstone of the teachings of the Roman Catholic Church. The small and seemingly innocuous theological thread on which Galileo unwittingly tugged was made available to him on a visit to Venice in 1609, when he purchased the lenses required to build his first telescope. One of the first objects he turned his perspective tube towards was the moon. With the mind of a mathematician and the eye of an artist, Galileo drew a series of 6 watercolors representing what he saw. These images are both beautiful and revolutionary. Catholic dogma asserted that the moon and the other heavenly bodies were perfect, unblemished spheres. Previous astronomers who had viewed the moon either with the naked eye or through telescopes had drawn a two-dimensional, blotchy surface, but Galileo saw the patterns of light and dark differently. His training in chiaroscuro revealed to him an alien lunar landscape of mountain ranges and craters. I have been led to the conclusion that the surface of the moon is not smooth, even, and perfectly spherical, as the great crowd of philosophers have believed about this and other heavenly bodies, but on the contrary, to be uneven and rough, and crowded with depression and bulges. And it is like the face of the earth itself, which is marked here and there with chains of mountains and depths of valleys. Galileo shared the watercolors with his long-standing friend from Florence, the artist Cigoli, who was inspired to represent this new and radical view of the moon in the grandest of settings. Built in the year 430 by Pope Sixtus III, the Pauline Chapel in Rome documents the changing artistic styles and techniques used to represent the natural world across many centuries. A place filled with shifting examples of how the three-dimensional world can be represented on a two-dimensional surface. Covering the dome of the Pauline Chapel is Cigoli's final masterpiece, a striking fresco depicting a familiar scene of the Virgin Mary bathed in a shaft of golden light surrounded by cherubs and angels. The fresco depicts Mary over what was, for the first time, a detailed, textured, and cratered moon. The Vatican named it the Assumption of the Virgin, unaware perhaps of the philosophical challenge it represented. Here was art representing scientific knowledge, a type of knowledge radically different from historical or scriptural authority, based on observation rather than dogma, and presented unashamedly in a grand setting for all in Rome to see. It is undoubtedly true that Galileo didn't intend to challenge the very theological foundations of the Church of Rome by observing the moon through a telescope. But scientific discoveries, however innocuous they may seem at first sight, have a way of undermining those who don't much care for facts. Reality catches up with everyone eventually. With his depictions of the moon completed, Galileo turned his ever more powerful lenses to other celestial bodies. Between the 7th and the 13th of January 1610, he became the first human to observe Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, now known as the Galilean satellites. For Galileo, This was further evidence to support the work of Copernicus and the physical reality of the heliocentric model. If moons were orbiting Jupiter, Galileo reasoned, it was impossible to argue that the Earth was at the center of the universe, because heavenly bodies existed that did not circle the Earth. Galileo published these observations in the spring of 1610 in The Starry Messenger, and from his correspondence with Kepler, his irritation with the discontent it caused amongst philosophers was clear. "My dear Kepler, I wish that we might laugh at the remarkable stupidity of the common herd. What do you have to say about the principal philosophers of this academy, who are filled with the stubbornness of an asp and do not want to look at either the planets, the moon, or the telescope, even though I have freely and deliberately offered them the opportunity 1,000 times? Truly, just as the asp stops its ears, so do these philosophers shut their eyes to the light of truth." To Galileo's mind, absolute confirmation of Copernicus's heliocentric model was provided by his studies of Venus. Beginning in September 1610, Galileo observed Venus over the course of months, and like the moon, he observed that Venus had phases. Sometimes the planet was lit completely by the sun, but at other times only a crescent appeared to be illuminated. The only plausible explanation for this observation was that Venus was orbiting the sun. This was surely final, compelling evidence of a solar system with the sun at its heart and the planets orbiting around it. It wasn't that simple, of course. Galileo, in what was certainly an ill-judged move, decided to move beyond reporting his scientific observations and instead champion a particular theological and philosophical interpretation of the data, namely that the Church was wrong and that the Earth was most definitely not the center of the universe. This he seems to have done because he wanted to be famous, and famous he became. Copernicus's De Revolutionibus was banned until corrected. The full version was not removed from the banned list until 1758, and Galileo ordered not to repeat his foolish and absurd conclusions. Galileo didn't keep quiet, and he achieved his historical notoriety by being put under house arrest in 1633, where he stayed for the remainder of his life. Many historians characterize Galileo as a bit of an egotistical social climber who brought it all on himself, which is partly true, and yet also desperately unfair. He was undoubtedly a great scientist and a supremely talented astronomical observer. In particular, he was the first to clearly state the principle of relativity which lies at the heart of Newton's laws of motion, namely that there is no such thing as absolute rest or absolute motion. This is why we don't feel the movement of the Earth around the Sun, and why Aristotle et al. Were misled into reading far too much into their stationary feelings. In the hands of Albert Einstein, the principle of relativity can be generalized to freely falling objects in a gravitational field, and this ultimately leads to modern cosmology and the Big Bang theory. But we are jumping ahead again. The purpose of recounting the story of Galileo is not to attack the easy target of the Inquisition, which nobody expects. Rather, it is to highlight the fact that the smallest and most modest of scientific observations can lead to great philosophical and theological shifts that in turn can have a tremendous impact on society. Galileo, by looking through a telescope, doing some drawings, and thinking about what he saw, helped to undermine centuries of autocratic idiocy and woolly thinking. In doing so, he got himself locked up, but also bridged the gap between Copernicus and Kepler, and paved the way for Isaac Newton, and ultimately Albert Einstein, to construct a complete description of the universe and our place within it.
In a little over 6 decades, we've met every one of the planets in our solar system. Traveling at first to our nearest neighbors, we visited Venus, Mars, and Mercury, and found rocky planets covered with the remains of long-lost worlds. Each has a life that followed very different paths. To these planets we returned time and again, staying longer on each visit, exploring deeper, and even touching down onto alien ground. Then we ventured further, beyond the rocky worlds, beyond the ice line, and out to the land of the giants. As we explored Jupiter and Saturn, we began to piece together the extraordinary life story of these gas giants and all the exotic moons in their grasp. But that was just the beginning. Beyond Saturn, out there far into the darkness, lie the most distant planets of the solar system, worlds we can hardly even glimpse from Earth. Uranus, a pale blue marble hanging in the frozen depths of space. Further out, its icy sibling Neptune, and beyond that, Pluto, a world but not a planet, which until now has remained virtually hidden from us in all but name. Each lies not millions but billions of kilometers from Earth, and for this reason only once have we dared to visit them and capture a set of images from the dark. Precious data that allows us to begin to understand the endless mysteries that lie out there, at the outer edges of our solar system and beyond. The scale of the solar system is virtually unimaginable. A landscape laid out across distances impossible to comprehend within the realms of human experience. London to New York is 5,500 kilometers. London to Sydney a mere 17,000 kilometers, while London to the Moon is 384,000 kilometers, and the longest single journey any human has ever completed, the equivalent of traveling 9.5 times around the circumference of Earth. Beyond these journeys, as we look out towards ever more distant destinations, the numbers grow so big so quickly that we've had to invent a different unit of distance altogether in order to give us a containable scale for the vastness of the cosmos. It's based on the mean distance between the Earth and Sun, which is 149,598,000 kilometers, known as 1 astronomical unit, or 1 AU. Today we can measure this distance with relative ease, but calculating that number for the first time with any accuracy was far from an easy task. For near on 2,000 years, many a great mind took measurements, made calculations, and came up with numbers that estimated the distance to the Sun. But it wasn't until the 17th century that we were able to measure for the first time the distance to our star, when Joseph Kepler provided the mathematical underpinning and Edmund Halley the understanding that the transit of a planet could unlock our ability to accurately calculate an astronomical unit. Halley was the first to realize in 1716 that by measuring a transit of Venus, the moment our sister world passes directly between us and the Sun, from different positions around the globe, we could obtain the necessary numbers to allow the geometry to play out. Unfortunately for Halley, he had the right idea at the wrong time, as transits of Venus are enormously rare, coming in pairs approximately once every 120 years. So, in one of the great scientific baton passes of all time, Halley left behind detailed instructions for future astronomers to carry out his plan. 20 years after his death, the 1761 transit of Venus provided the first opportunity to put his theory to the test. In a remarkable combination of collaboration and competition, which occurred in the middle of the Anglo-French 7 Years' War, observers from both these countries travelled all over the world to destinations as far afield as Siberia, Madagascar, Newfoundland, and the Cape of Good Hope, praying for a clear sky to observe and measure the transit. Combined with a similar set of expeditions for the next transit 8 years later, enough data was gathered to allow the French astronomer Jérôme Lalande to calculate the distance between the Earth and the Sun for the very first time, coming up with a pretty accurate figure of 153 million kilometers. Today we no longer need to rely on the rarest of astronomical events to make these measurements. Instead, we have far more direct ways of measuring that have allowed us to plot our journey around the Sun in ever greater detail. Throughout a year, as we follow our elliptical orbit around the Sun, the distance from our planet to the centre of the solar system varies enormously. This means that in early January each year, as we reach the closest proximity to our star, known as perihelion, we are about 147 million kilometers distant. 6 months later, in early July, we reach aphelion, our furthest distance from the Sun, and find ourselves about 5 million kilometers further away, orbiting at around 152 million kilometers away. Exactly what one astronomical unit actually is has therefore been the subject of intense debate and change over the last century, and as we have sent our robotic explorers across the solar system, our ability to directly measure the precise distances between the inner planets using radar and telemetry has yielded endless refinements. So since 2012, we, or the International Astronomical Union on our behalf, have made life much more straightforward by defining one AU as 149,597,870,700 meters, or about 150 million kilometers. Mars, the furthest out of the four rocky planets, sits at 1.5 AU, half as far away from the Sun again as we are. At 2.2 AU, the asteroid belt begins. A swirling carousel of rocks and failed worlds, it stretches out for another 150 million kilometers before coming to an end. Here, at the snow line of our solar system, 3.2 AU away from the Sun, we leave the rocky worlds behind and continue across another 300 million kilometers of space before we reach the first of the giants, Jupiter. And yet here, at 5.2 AU, 780 million kilometers from the Sun, our journey has only just begun. It is almost double the distance again before we reach the next planet, the ringed jewel that is Saturn, sitting 9.6 AU, or 1,434 million kilometers from the center. It is here that the realm of our exploration ends, at the last of the planets that we can say we have truly explored. Mercury, Venus, Mars, Jupiter, Saturn. Each one a world that we have not only visited but resided around. Our robotic explorers orbiting with camera eyes wide open for years at a time. In many cases we've not just looked at but also touched the surface of these worlds and the moons they embrace. Once we get beyond Saturn, the scales change so much, the distances grow so vast and travel times so long, that they are measured not in days and months, but years and decades. Uranus, the first of the ice giants, sits over twice as far away from the Sun as Saturn, orbiting at an average distance of 19.2 AU, or 2.871 billion kilometers. Then Neptune, the farthest of the planets, lies another 11 AU further out, and orbits nearly 4.5 billion kilometers away from the Sun. After it comes Pluto, on the highly elliptical orbit that takes it inside and outside the line of Neptune, but on average sits 5.9 billion kilometers away from the Sun. To reach these worlds is so difficult that in our 60 years of planetary exploration we visited each only once, and spent just the briefest of moments in close proximity to them. We manage a matter of hours in each system, as our spacecraft are propelled at enormous speeds, so fast that they quickly fly past and beyond. But the precious scraps of data they have returned have allowed us to peer through the mysteries that lie out there at the outer edge of our solar system, and start to tell the extraordinary stories that reach deep into the darkness. To reach the outer planets has taken the work of perhaps the greatest of all of our planetary explorers. At the time of writing, in January 2019, the Voyager 2 spacecraft has been in continual operation for 41 years, 4 months, and 19 days. Traveling at 15.341 kilometers per second, it is currently around 119 AU from the Sun, that's 17 billion kilometers away, and has just recently been officially deemed to have entered interstellar space. No longer within the empire of our Sun, the heliosphere created by the solar wind that defines the boundary of our solar system, this little probe weighing less than a family car is the third human-made object after its sibling Voyager 1 and also Pioneer 10 to leave our home star system behind. As it heads out into the void, it is expected to continue to stay in contact with us here on Earth for at least another 6 or 7 years, transmitting its weak radio signals until at least 2025, before slipping off into its final silence around 48 years after its launch, on its way towards a small star called Ross 248, located in the northern constellation of Andromeda. The Grand Tour. It all began on the 20th of August 1977, when the Voyager 2 spacecraft left our planet on board a Titan III rocket, taking off from Launch Complex 41, Cape Canaveral Air Force Base. 2 weeks later, on the 5th of September, the twin probe Voyager 1 would follow hot on the heels of its sibling. Taking the fast lane, Voyager 1 would speed ahead, reaching Jupiter 4 months earlier than Voyager 2, which had been sent on a different trajectory that took it on a slower, longer, more circular course. Making its closest approach on the 9th of July 1979, Voyager 2 swept past Jupiter at a distance of 576,000 kilometers from the planet's cloud tops, gathering a vast amount of data on the giant planet's atmospheric characteristics and its moons. This included the first detailed analysis of the swirling storm known as the Great Red Spot, as well as a 10-hour analysis of the volcanoes of Io, allowing the activity to be calculated by directly comparing the images of the Moon with images Voyager 1 had taken just a few months before. Using Jupiter as a gravitational springboard, Voyager 2 then left the Jovian system behind and continued on a 2-year journey to Saturn. With its closest approach occurring on the 26th of August 1981, Voyager 2 became the third spacecraft to visit Saturn, providing a vast range of pictures and data on the planet, its rings and moons. But it was the next leg of its journey that would be truly groundbreaking, and it was only possible because of the rarest of celestial alignments. Back in 1964, Gary Flando, an aerospace engineer working at the Jet Propulsion Laboratory in Pasadena, California, noticed that an unusual configuration of the 4 outer planets would occur in the late 1970s and early 80s. Flando realized that this particular alignment, which occurs once every 175 years, would potentially allow a single spacecraft to visit all the outer planets using a series of flybys and gravity assists that would provide an opportunity to visit not just Jupiter and Saturn, but Uranus and Neptune for the very first time. Over the next 15 years, NASA began plotting a mission to complete what became known as the Grand Tour. Various plans for the tour were started and shelved as the costs and feasibility of the proposed route came into question, until eventually in 1972, the twin probe Mariner Jupiter-Saturn project was approved with an estimated cost of $360 million. The 2 probes would eventually be renamed the Voyagers, and only one would complete the Grand Tour. Voyager 1 would be sent from Jupiter to Saturn, and then on to its satellite Titan, to attempt to explore the Moon and its intriguing atmosphere. But Voyager 2 would be given the grandest of journeys, and the honor of becoming the first craft to attempt to see Uranus and Neptune close up. Flying past the Saturnian system in late August 1981, Voyager 2 began a journey into the darkness that has yet to be repeated. Over the next 3.5 years, the craft would make its lonely journey outwards towards its unique encounter with the 3rd largest planet in the solar system, a planet that until then we had only ever been able to peer at in the distance. The pale blue marble. The 7th rock from the Sun sits 2 billion kilometers from the Earth, a pale blue marble hanging faintly in our night sky. Barely visible with the naked eye, ancient observers dismissed the object as a star, too slow and too dim to join the family of planets. It wasn't until the invention of the telescope that the real character of this distant object began to emerge. But even then, the discovery of Uranus was a slow one. It began on a cold March night in 1781, Tuesday the 13th between 10 and 11 p.m. to be precise, in the townhouse garden of William Herschel. As the 43-year-old astronomer peered through his 160mm telescope, surveying the sky that night for any small stars he could bring into view, he noticed a dim object that over the course of the next few days appeared to be slowly moving, so he assumed it must be a comet. Reporting his findings to the Royal Society the following month, Herschel still seemed convinced that this was a comet, not a planet, even though he himself suggested that the characteristics of the observation were as planets are. The Astronomer Royal at the time, Neville Maskelyne, whose claim to fame as being the first person to measure the weight of the Earth scientifically for the first time, wrote to Herschel in late April 1781 to share his bafflement. "I don't know what to call it," he wrote. "It is as likely to be a regular planet moving in an orbit nearly circular to the Sun as a comet moving in a very eccentric ellipsis." Eventually, the accurate computation of the body's orbit, calculated by a number of different astronomers, provided the ultimate proof of its character, and its planetary status was confirmed by Herschel in a letter to the President of the Royal Society, Sir Joseph Banks, in 1783. "Sir, by the observations of the most eminent astronomers in Europe, it appears that the new star, which I had the honour of pointing out to them in March 1781, is a primary planet of our solar system." With that, the seventh planet was born into our story of the solar system. But naming this new arrival, the first planet to require such a decision since antiquity,